Good morning, dear colleagues, dear participants of our conference. The conference section is now starting its work. I invite the first speaker, Dr. Pavlo Kalkovsky.
So, good morning, ladies and gentlemen. My presentation is. Do you see my presentation?
Yes.
Okay. And I will. Oh, okay. So let me present you our work. It's a synthesis, structure, and electrochemical properties of perovskite, lanthan manganese O3. In the last decade, attract a lot of attention. That's the reason why we can use this material as electrode material for supercapacitors. And this material have a lot of advantages because it's cheaper, it's easy to obtain, and we have safety. This material is a safety, and he can work like redox reaction in the like electrode materials for supercapacitors. So our work is based on two steps or two big range. First of all, we obtain this material and synthesize this material, and the second step is to use this material like electrode material for supercapacitors. So on the first steps for the obtaining, we use the salt gel after-combustion technique. And first of all, we obtain the solution with the lanthan manganese, and we obtain the gel form based on for the electrochemical reaction you can see on the slide. And then when we obtain the gel form, we finally use the dried gel, and based on after combustion, we obtain the powder. And according to the XRD structure, this powder it was lanthan manganese O3 material, perovskite structure, with the space group PM3M cubic structure. And you can see the model of the crystal structure of the lanthan manganese O3 view along the C-axis. Based on the Schreier equation, it was determined that we have the particle size and the coherent scattering region is 24 nanometer, and the particle size according is 45 nanometer. Density of this material was 6.54 gram per centimeter cube. So the proof that result was SEM micrographs, which you can see on the slide. And the increasing of the SEM micrograms is approximately 1 micrometer and the 100 nanometer. So the estimation of the particle size on the micrographs, it was determined that we get the powders with the size is approximately 50 to 60 nanometer, which is a good agreement with XRD obtained by previous. So the morphology and the structure of the perovskite structure of lanthan manganese O3 was obtained based on parameter and to absorption desorption isotherms. You can see on the slide A, the figure 8. And the pore size distribution of lanthan manganese O3 you can see on the figure B. It was determined that the surface area is 42 meters square per gram, and the distance between particles it was approximately 5 to 12 nanometers. The second our branch, the big branch, it was use this material and apply this material as electrode material for supercapacitors. And we use 3 electrode cell one of them is from argentum chloride, another one is compare electrode, and the third one electrode was our obtained material, which is we put on the nickel grid, and we use the electrolyte two types. One of them is the potassium, lithium 2SO4, and permanganate OH system. It was determined that we have in potassium OH system, it was a little bit bigger capacitance than in lithium 2SO4. We suppose that it, according to the redox reaction, you can see which we have the big peak than in the lithium 2SO4 system. And it was determined then potential dynamic curves for the lanthan manganese O3 in potassium OH from 1 millivolts per second to 16 millivolts per second. And for lanthan manganese O3 in lithium 2SO4 system, the scan rate much more. It's not much. It's more than less bigger than it's 1 millivolt per second to 20 millivolts per second. And the capacity for potassium OH, it was 40 farad per gram, and for lithium 2SO4 it's 35 farad per gram. So the specific capacity, you can see the graph on the figure. And the next, the proof, this capacity was on the charge-discharge curves, which is presented on the slide. We conduct charge-discharge procedure in the range from 0 to 1 volt for both electrolytes, and it was determined that we got the capacity. It's approximately 62 farad per gram, and 38 farad per gram for the potassium OH and lithium 2SO4. The density of the specific capacity for lanthan manganese O3 in both electrolyte system is present on the figure. And the conclusion for our work is the complex oxide of lanthan manganese O3 was obtained based on the dissolved gel auto-combustion technique. It was determined that the obtained material has a perovskite structure of the PM3M space group with lattice parameter of 3.9 angstrom, and the density of the material is 6.54 gram per centimeter cube. Moreover, it was determined that the average size of the coherent scattering region is 24 nanometers, based on, by the way, Scherrer equation. So the specific surface area of the synthesized material determined using the BAT method is, it was determined that its surface area is 42 meter square, and the morphology of the material was researched, and it was determined that the synthesis lanthan manganese O3 formed by particle with a size of 40-60 nanometer, between which is cavities or distance between the particles from 5 to 12 nanometers, and the electrochemical investigation of the lanthan manganese O3 material in various electrolytes were carried out, and the dependence of the specific capacity of the obtained material on the rate of change of the potential was determined. The specific capacity calculated according to the data of the potential dynamic method and charge-discharge method, and we got the maximum capacity is 40 farad per gram and 38 farad per gram, in this case a scan rate of 1 millivolts per second respectively. And the total capacitance of our electrochemical cell, 3 electrochemical cells, is divided into capacity and the accumulation of the charge in the double electric layer and the fusion controller redox capacitance due to the fast Faraday reversible redox reaction. It is determined that the main contribution to the total capacity is made by the Faraday capacity, which is actually 90% of the total capacity. Thank you very much for your attention.
Thank you for reports. Do you have any questions? No questions. Thank you very much for reports.
Thank you.
Now I invite the second speaker, Sylwia Parzyszek, University of Warsaw, Poland, induced optical properties of semiconductor nanocrystals soft assemblies.
Вот это, да?
Good morning, everyone. My name is Sylwia Parzyszek, and I'm from University of Warsaw, Faculty of Chemistry. Today I would like to shortly tell you about the topic of my research, which is inducing optical properties of semiconductor nanocrystal soft assemblies. And at the very beginning, I would like to shortly introduce you my motivation to conduct this research. Because in our everyday life, polarized light is very important. We use sunglasses which filter amount of light which gets to our eyes, or polarization light can give us informations which are usually much difficult to obtain with unpolarized light, which is very symbolically drawn on this picture. And overall, all polarized light have countless different applications. Just to name a few, it would be encryption, data encryption, imaging, or detectors. And as a basic source of light in my research, I have chosen semiconductor nanocrystals. I don't need to tell about that why nanostructures are useful and why they are very good material to work with. And semiconductor nanocrystals, they are nanomaterials which emit visible light, in my case, because I synthesize indium phosphide zinc sulfide nanocrystals. They have a modulating energy gap, which gives us many possibilities to modulate their optical properties with changing their size, changing their environment, and so on. But to obtain fluorescence anisotropy from semiconductor nanocrystals, I have chose to use mechanical shearing method, which is well-known method used usually for liquid crystals. And mechanical shearing is a method which allows to microscopic orientation of molecules in one direction. We have to let a little bit heat up our material, which is drop casted on any substrate. And when we heat it up, those molecules, our material has lower viscosity, those molecules have higher energy, and we put some pressure on that material and just drag it. And that way we can orient our liquid crystalline molecules in one direction. In the next step, I have chose liquid crystal ligand, which I will use to modify surface of my nanoparticles. I have chose ligand which structure is drawn here. I have chose this particular molecule because a similar one was published before by Joanna Wolska. And in this molecule is known that depending on the temperature of shearing, it can orient in 3 different lamellar modes. So the shearing direction is the same, those samples are chemically identical, but the only factor that changes is the temperature of that alignment. So the main idea of my experiment in this case was to obtain nanocrystals, semiconductor emitting, light emitting nanocrystals, which will be oriented in lamellar structures. And thanks to that anisotropic orientation, I hope to obtain anisotropic fluorescence. So in the first stage, I have synthesized semiconductor nanocrystals, indium phosphate zinc sulfide, which are coated with dodecanothiol. They are slightly tetrahedral, but their size is about 3 nanometers. In the next step, I perform partial ligand exchange on mentioned previous liquid crystalline molecules. I drop casted the material and heat anneal it. And thanks to that, the surface of nanocrystals is coated with 2 different ligands, which significantly differ in size. And moreover, those long liquid crystalline ligands have aromatic rings, which can interact with each other. The organic shell of those nanoparticles is thermoresponsive, and in low temperatures, they form such anisotropic coating, and it results in organizing quantum dots in anisotropic structures, lamellas, for example. And in elevated temperature, after heating up, those ligands can reorganize on the surface and form more isotropic closed packed structures. And I would like to point here that one of the most important advantage of my material over previously reported is that from thermogravimetric analysis we can conclude that the inorganic cores are about 40% in the entire material. It is enormously high content of inorganic part, because usually those previously reported materials, those are liquid crystals doped with quantum dots. That content is usually a few percent or some fraction of percent. Usually it's results of chemical incompatibility of those nanocrystals with liquid crystal matrix. So after ligand exchange, I drop casted my material, my liquid crystal nanoparticles. I drop casted 2 chemically identical samples on 2 different glass substrates. and perform that annealing, thermal annealing in 2 different temperatures in 40 and 80 Celsius degrees. As you can see, those nanoparticles oriented in 2 different lamellar modes. And I measured those samples, examined those samples measuring fluorescence anisotropy. In a typical setup to such measurements, there are 2 polarizers, one between source of light and sample, and the other one between sample and detector. And in my measurements, first polarizer is always in a vertical position. So I measure intensity of polarization within 2 different polarizators alignment, parallel and perpendicular. And we can see that for both samples, those intensities between those 2 polarizers alignment are differ. However, for that sample aligned in 80 Celsius degrees, this difference is much higher, probably because in 80 Celsius degrees, like I said, the viscosity is much lower, so that sample was probably much better aligned. I also performed control measurements. This is anisotropy fluorescence measurements for dodecanothiocoated nanocrystals, so without any modification, and we can see very little, very minor fluorescence anisotropy. And it's probably due to some intrinsic properties of those nanocrystals, their band structure, their shape anisotropy, and so on. But after I was successful in observing fluorescence anisotropy, I wanted to observe a circularly polarized luminescence from my nanocrystals. And to do that, I used such band-core mesogen, which my colleague Dorota Grzelak previously reported yesterday. So I will just shortly remind that such band-core molecules, they form polar and chiral smectic layers, but due to some mismatch between those layers, those layers just frustrate and form such helical nanofilaments. And using that chemical compatibility with liquid crystals, which I obtained in my previous stage of research, I mixed those my nanocrystals with this matrix. This is a SEM image of those helical nanofilaments. We can see how densely they are packed. And I measured my samples on transmission electron microscopy due to very low contrast between semiconductor nanocrystals and that organic part. I know you can't see those helical filaments are coated with nanocrystals, but for this presentation I tried to elevate the contrast. I don't know if you can see it better, but you have to believe me, it's okay. And I examined my samples on polarized optical microscopy. Those are images taken with slightly uncrossed polarizers, usually with when sample exhibits some chiral optical response. When polarizers are crossed, there is just dark image, and when they are slightly uncrossed, like for example 86 degrees and 94 degrees, there are some darker and brighter areas, and those areas which are darker on one picture, they are brighter on the other, and we can see that that flipping of those areas. In cooperation with Professor Maćkowski's group from Mikołaj Kopernik University in Toruń, we try to observe fluorescence from single domains and further chiral fluorescence. However, we can see correlation from wide field fluorescence microscope and confocal fluorescence microscope. We can see that even visually quality quantum yield of that fluorescence is very high. However, measuring CPL from such small structures is very difficult and requires special equipment. We started to cooperate with Professor Fumita Araoka from Japan, from Riken Institute. However, coronavirus pandemic make international cooperation very tedious, especially in sending samples and so on. So we have to look for other options. And we decided to skip this part and see if we can see, even for applications, if we can see CPL on larger scale, on macroscopic scale. To this, for this purpose, I doped my samples with such chiral dopant, which is known from literature, and see if I can see any circular dichroism first, because then if I could see, then I could conclude that I will see also CPL. And I want to show you here that that absorption spectra of quantum dots lies in the same point. It covers the organic absorption from organic, but there is a little band here, and I was able to see some differences between those spectra, and I hope next month to go to Professor Clever group from Technical University in Dortmund, and I hope finally to observe CPL from my samples. And to conclude my talk, modification of quantum dots with liquid crystals allowed me to observe microscopic anisotropic fluorescence, and also allowed me to perform obtain some chemical compatibility towards circularly polarized luminescence. And in future perspectives, I would like to perform some binary assemblies with gold nanoparticles to increase that optical response, and also use some anisotropic semiconductor nanocrystals, for example, small nanorods, which my colleague Zuzanna Levera has presented yesterday. And thank you for your attention, and if you have any questions, I will be happy to answer.
Thank you very much. Do you have any questions? Thank you for that. I invite the next speaker, Alexandra Radchanka, Institute of Physical Chemical Research, Belarusian State University. I invite the next speaker, Dr. Mikhailo Kurmach, Pysardzhevsky Institute of Physical Chemistry of National Academy of Science of Ukraine.
На почте, да?
Good morning. I present my presentation, composite of hierarchical zeolites with basic metals as catalyst for Gewalt reaction. Amino chair fans is widely used heterocycles which can be used in different industries. For example, they are widely used as optical brightness reagents for separation, conducting polymer, and also as drugs. Two amino chair fans, due to their easy preparation method and possible utilization in medicine, is very important heterocycles, which can be also used for obtaining of other heterocycles. Typical method for production of two amino chair fans is Gewalt reaction. Gewalt reaction is a reaction between ketone, malonidinitril, and atomic sulfur. The reaction contains two stages. On the first stage, reaction between malonidinitril and ketone is performed, followed by the second stage, on which the formed adduct react with atomic sulfur to formation of corresponding two amino thiophenes. First stage of the process is catalyzed by both acidic and basic centers, and known as Knoevenagel reaction. But the second reaction is catalyzed only by basic centers. Well-known catalysts for this reaction that's homogeneously basic catalysis, such as different amines, for example, diethylamine. Also, it is known that different basic oxides are very efficient catalysts for this process. The aim of our work is to create new catalysis for this reaction based on hierarchical zeolites doped or containing different basic oxides or elements. In our work, we investigated as carriers different zeolites with mordenite and Ba structure. Composites were obtained both by ion exchange method, that's cesium containing zeolites, and magnesium, zinc, titanium, and cesium containing zeolites obtained by impregnation of corresponding salts followed by their decomposition. Now we shortly, I will told you about carriers. Carriers are hierarchical zeolites obtained with Ba and mordenite topology, obtained by using Gemini type surfactants as structure-directing agents. Those molecules are presented on the slide. Those molecules, due to their structure, allow to significantly decrease the size of the molecular nanocrystal and obtain materials with high external surface and high mesopore volume, which can be very useful for reaction including big molecules. Typical XRD pattern for carriers indicate formation of corresponding structures, and adsorption isotherms and calculation from this adsorption isotherms shows that this carrier is characterized by high volume of mesopores and high external surface. Depending on the structure, in our work we utilized Ba and mordenite zeolites with nanosheet morphology, as you can see on the slide. and which was obtained using SDA containing 2 nitrogen atoms. In case of using 4 atoms of nitrogen, in case of SDA2, we obtained mordanite nanorods, and in case of SDA3 and SDA4, we obtained beazolite nanosponges of beazolite. Obtained carriers are characterized by high concentration of strong acid and base centers, which was determined by pyridine adsorption. Now let's return to our composites. Some composites called caesium beta nanosheets and caesium aluminium beta or caesium beta we have obtained by ion exchange. Typical zeolite contains protons as bronze acid centers. That's bridged hydroxyl group. During ion exchange method, proton was exchanged to caesium, which serve as basic center. As we can see from a figure of pyridine, samples obtained by ion exchange will not characterized by acid Lewis or Bronsted acid sites. But as we can see from the heterochloroform adsorption figure, this materials is characterized by high concentration of basic sites. As we can see, all samples are characterized by 3 types of basic sites. The highest concentration of basic sites was found for zeolites. Those zeolites were tested in Gewalt process using different cyclic cations as substrates. In the main substrate which we can use to elucidate the catalytic activity of samples was cyclohexanon. As we can see, caesium beta nanosheet and caesium beta nanoparticles are very effective in this, obtained by ion exchange method, are very effective in this process. In case of caesium beta nanoparticle, we have obtained the quantity yield of formed density of N. Unfortunately, due to the low concentration of basic centers, we have, in case of mordanite nanosheets and mordanite nanorods, catalytic activity of such materials are not so big as in case of caesium beta nanosheets and caesium beta nanorods. Additionally, doping of caesium beta by extra framework caesium by caesium carbonate will not provide the increase in catalytic activity, but conversion of corresponding ketone is decreased, which can be probably explained by some spherical explanations. Also, we tested some. We tested zinc, titanium, and magnesium oxide composites with zeolites beta as carriers. As I can say, we used aluminum beta nanosheets and aluminum beta nanoparticles. As we can see, for all samples is characterized by the high conversion of ketone, but in case of titanium, due to not enough concentration and strong strengths, as we can predict, of basic sites, conversion is not full, and high amount of corresponding adduct product of the first stage was formed. Also, we can see that magnesium containing composites are very effective in this process, but not so effective as cesium beta obtained by ion exchange method. The most effective catalyst of our process we tested in Gewalt process using other different cyclic ketones. As we can see, the highest concentration was achieved for process when we use as substrate cyclohexanone. In case of cyclohexanone and cyclopentanone, conversion is moderate, but in case of cyclooctanone, conversion is not so, is very small, probably due some diffusion limitation for this process, and probably cesium which are not probably due high concentration of cesium which are located in zeolite micropores. So as we can see, we obtain some a set of titanium, zinc, and titanium, zinc, magnesium, and cesium containing zeolite, which provide high activity in process of obtaining in Gewalt process, including cyclohexanone. For other substrates we obtain moderate activity, but we now this process still will be investigated. Thank you for attention. If you have a question, I'm ready to answer you.
Thank you very much. What are the questions for the speaker? Thank you, Fripats.
Thank you.
I invite the next speaker, Dominique Strazak, Medical University of Lublin, Department of Synthesis and Chemical Technology of Pharmaceutic Substance, Poland. I invite the next speaker, Olga Skurichina, Slovak Academy of Science, Slovakia.
Hi. Does anyone hear me?
Yes, we can hear you.
Okay, nice. Then I will start my presentation. If I understood properly, I should start, yes?
Yes.
Yes.
Okay. Okay. You can hear you can see my presentation, nice.
Yes, we can see your presentation. Thank you.
Okay, thank you very much. Good morning. My name is Olga Skurichina, and I would like to present you our work that we have done in the Slovak Academy of Science with conjoined forces with the Technical University of Graz about pyroxenes as ion conductors. So why we are concerned about pyroxenes? Because as we all know, recently there have been a huge accent on sustainable development and of materials and different kind of technologies. And there are three pillars of this kind of development: and society, economy, and environment. And pyroxenes can be a nice material for lithium or sodium-ion batteries, and they fall into this category of environment with responsible consumption and production and affordable and clean energy, because they can be used as electrode materials for ion batteries. So there are a lot of different kind of challenges in lithium-ion batteries, sodium-ion batteries, and batteries at all. And here we will be talking only about lithium and sodium-ion batteries. And pyroxenes, they are nice alternative for electrode materials of lithium batteries, because they consist of substances common in nature. They are much cheaper and they don't contain any heavy metals that are toxic. So general, give you some overview on pyroxenes. The pyroxenes can have two different general formulas that you can see on a slide. I will be talking only about pyroxenes with the first general formula, and and particularly with lithium or sodium and M2 site, with iron in M1 site, and with silicium and germanium and T site. So how did we prepare our materials? It was 2 steps: ball milling and annealing. For ball milling, we took stoichiometric mixtures, and for annealing, we used the air atmosphere, and it allowed us to receive pure materials much faster than by other conventional methods like sol gel or solid state without any activation or ball milling. So we used a broadband impedance spectroscopy to investigate pyroxenes as ion conductors. It was done in Technical University of Graz during my Erasmus stay. Why actually we used this tool? Because broadband impedance spectroscopy is very good for studying naked material, let's say so, because we studied it in just a solid material without any assembly in batteries. And so similar process is happening during intercalation, the intercalation of mobile ions, for example, in batteries during discharge and charge processes. So we use no-control broadband analyzer. We studied it from 500 kelvins to 293 kelvins or 240 Celsius to room temperature with a step 20 kelvins. We heated our samples 3 hours in inner atmosphere to eliminate humidity, because as it's known, humidity influences greatly to conductivity. And pressed for solid state measurements, we pressed our pellets for 5 millimeters under 0.6 ton approximately, and covered it with cold sputtering. So our goal was to investigate transport properties of mobile ions in pristine pyroxenes that we synthesized, because these materials were studied for batteries but showed very poor behavior. So we wanted to study more deeply what is behind the structure, let's say so. So after impedance measurements, we received different kind of impedance spectra, which we fitted with juncture power law, which you can see on that slide, where sigma DC was a plateau, so-called plateau region of direct conductivity, where the conductivity is not changing with frequency. A is per exponential factor of frequency, and alpha is a power law exponent, has a value from 0 to 1, and is indicator of dimensionality of Hopin process. So is it 1D, 2D, or 3D of this movement of mobile ions? We did it for 3 materials, but I presented here only with 1 to make it shorter. So after fitting this spectra, we received Arrhenius plots for these materials. Here you can see for crystalline sodium metagermanate, lithium iron metasilicate, and lithium iron metagermanate. So here you can see a Arrhenius equation, where from slope we defined activation energy of the process actually of migration. For some of you who are not very familiar maybe with this process, here I have a video where you can see the jump of a mobile ion inside structure. It's very local, and here is a maximum energy, so activation energy. And we can see that our pyroxenes are more or less have the same slopes as studied material, for example, as lithium iron metasilicate previously. And they studied it with NMR, which is a much more sensitive technique than broadband impedance spectroscopy. And the values of activation energy, I will show you on next slide, are in a very close range to this one. So here we can see the summary, let's kind of from Arrhenius plots, where logarithm sigma is a pre-exponential factor and the conductivity of material at infinitely high temperature, slope, activation energy of conduction, and according to Almond-West formalism that studied different kind of conductors and how to quantitatively explain their behavior. They suggested that energy of activation can be consisted of energy of migration, like EM, and energy of creation of defects. And if the energy of creation of defects is equal 0, then this ratio, the activation energy of A would equal this ratio, and we can see that it's more or less in that range. So we suggested in our case that in pyroxenes, as the energy of creation defects doesn't take place during applying electric field, as it's in case with many other materials where there are creation of defects. And yes, so here we can see a closer look at the structure of these pyroxenes of sodium meta iron germanate, lithium iron metagermanate, and literature material lithium metavanadate. And we can see that, I don't know if you see that here the value for lithium iron germanate is 0.86 of activation energy, and for sodium iron germanate it's 112. It's much bigger. So actually our, let's say, goal was first why we studied these materials, because first we suggested that for sodium it would be higher, because sodium is obviously a bigger atom, so it would be harder to move. But as well, I will return back from different kind of neutron powder measurements. In literature, we knew that lithium iron metagermanate would be theoretically better a conductor than lithium iron silicate, which was studied previously for batteries and showed poor behavior. And we can see for energy of activation energy that activation energy for lithium iron germanate is lower, definitely lower than for lithium iron metasilicate, which actually proved our suggestion from structural point of view. And here we, with a green brackets, it's shown one-dimensional path, because we can see that alpha is 0.405, which for oxides corresponds to very low dimensional process, and it's parallel alongside the C-axis in this crystal. So actually, if we would apply electric field perpendicular to C-axis, they act actually as resistors. So that's one of the, let's say, explaining why they are show such poor behavior in real cells. So we try to amorphize these materials, because it's known that the amorphization, or let's say ball milling, most of the time we improve conductivity. But since our materials appear to be very soft, we had a huge wearing from milling material. So here we can see that only for sodium iron metagermanate it was the lowest, let's it was indeed, we saw the improving conductivity, and only for this material we can actually consider this effect of milling, because for other materials, as you can see, after milling, the content of zirconium was almost 50% of the material, so we did not study it after. So we actually proved that the diffusion process in pyroxenes depends on atom in T position. For example, in lithium iron metagramanate, it's much better. Well, it's better in the lithium iron metasilicate. The effect of ion sites, which is known, it was as well shown. And as well, we compared with literature data for lithium metavanadate, which doesn't have this octahedra from iron or from any other, let's say, alien atom. And so we would like to study other materials, also other pyroxenes with simpler structures like lithium metavanadate. And currently I'm doing that in Graz, and we are going to study it as well with NMR for studying short diffusion and long diffusion, because impedance spectroscopy is studying long range diffusion. But unfortunately for pyroxenes with iron, it's impossible. And we would like to test this, the best chosen pyroxenes for application in real cells and struggle cells. It says references, the funding, and thank you for your attention.
Thank you very much. Do you have any questions? I have questions. What special resolution did you obtain by using impedance spectroscopy for the task of ion transports?
Can you repeat a little bit? I don't hear very well. Can you please repeat the question?
What special resolutions did you obtain by using of impedance spectroscopy?
What can I again?
Spectral resolution.
What do you mean by resolution? I don't understand the question.
Maybe any questions? Thank you for it. Now I invite the next speaker, Alexander Pospelov, Kharkiv Scientific Body Lycey, Ukraine.
Dear ladies and gentlemen, I am Alexander Pospelov, a student of School Obdarovanist, Kharkiv, Ukraine. I would like to present you a report, the Point Contact Cyclic Switchover Effect Investigation. This research was carried out on the basis of Department of Spectroscopy of Molecular Systems and Nanostructural Materials of Boris Verkin Institute for Low Temperature Physics and Engineering of National Academy of Sciences of Ukraine. Our modern world surpasses past centuries in quality of life and safety. But there are still many unsolved problems. Environment pollution, diseases, and terrorism. Now these things are among those that are leading humanity to a global catastrophe. But on the base of nanomaterials and nanostructures, sensor devices are being developed nowadays that allow diagnosing dangerous diseases at an early stage, detecting the quantity of pollutants in atmosphere, and timely noticing terrorist threats. Some of the most promising nanostructures for creation of high-sensitivity sensors are Janssen point contacts. Janssen point contact is a contact of nano size that is created between two bulk pieces of metal, touching each other on a small area. Janssen point contact has a couple of unique characteristics. Its main characteristic is that the electron mean free path exceeds its length and diameter. So when the current flows through the point contact, electron energy does not dissipate on unit cells of its crystal structure, and so the temperature of point contact doesn't increase. When the current flows through the bulk conductor, its temperature increasing. At the current density of around 100 ampere on a square centimeter, such conductors melt. At the same time, the current density in Janssen point contact can reach a colossal value of 10 to the power of 10 ampere on a square centimeter without destroying the contact material at room temperature. That characteristic of Janssen point contact is also the result of effective heat discharge by the bulk conductor, which form point contact. All that indicates the possibility of point contact systems use without additional circuit solutions. Another unique characteristic of Janssen point contacts is that electric field is concentrated in the point contact conduction channel area. Such a potential distribution is the main prerequisite for realization of point contact gas sensitive effect and point contact sensors operation. Initially, Janssen point contacts were produced using a needle anvil technique and used to receive electron-phonon interaction spectra at liquid helium temperatures. In the traditional needle anvil technique, formation of point contact is accomplished by approaching of needle toward an anvil. Needle is a sharpened metal wire with point radius of around 1 micrometer. Needle has a well-polished plate at its working part. Needle and anvil are being made of the same material. Our experiments, in contrast, were held at room temperatures, and Janssen point contacts were obtained using a modified needle-anvil technique. In that technique, between needle and anvil, electrolyte is being placed. Convergence of needle and anvil provides by growing of dendrites on the needle surface. In the traditional technique, electron mean free path in point contact often decreases owing to needle mechanical deformations, which makes it harder to form Janssen point contact. Advantages of a modification are that formed point contacts are perfectly nanostructured, and there is no possibility of those mechanical deformations. When the current flows through the needle electrolyte anvil system, dendrites start growing on the electrode active areas of needle surface with the highest density of electric field lines. Dendritic Janssen point contact forms at the moment when the dendrite tip reaches the positively polarized surface of the anvil. When dendritic Janssen point contact forms, its conduction channel can be considered as a gapless electrode system. The gapless electrode system is a monolithic conductor with the potential distributed monotonously along its longitudinal axis. Monotonous change of potential along point contact channel and electric field concentration creates conditions when in that system reductive processes can proceed on the side of the negative pole of power supply, and oxidative ones can go on the side of positive pole. After a certain period of time, the part of point contact conduction channel, which is close to the surface of anvil, will dissolve, and the traditional electrochemical electrode system will occur. In that system, on the needle surface, dendrites will grow. One of them will reach the counter electrode and again activate a gapless electrode system. Cycle repeats in phases of dendrites growth, point contact formation, and its dissolution is exactly a cyclic switchover effect. The recurrence of cyclic changes during cyclic switchover effect is automatic and requires no external influence. Typical resistance dependence of dendritic Janssen point contacts on time, recorded during cyclic switchover effect, displays cyclic changes in the resistance of point contact system. It is the confirmation of cyclic switchover effect realization. Drops in the resistance testify about formation of point contact. Sharp increases in the resistance testify about its dissolution. In the copper-based point contact system, as well as in the point contact systems made of cadmium, argentum, plumbum, and other metals that were studied, the cycles in the processes of growth dissolution are characterized with irregular stochastic form. Only in the tin-based system that personally I has studied, the cycles in the process of growth dissolution have approximately constant frequency. That process is can be described as process of formation of point contacts characterized with the same lifetime. Using standard approach in the Janssen point contact spectroscopy based on Sharvin's formula, we can determine the diameters of point contact region. For tin point contacts, Sharvin's formula can be converted to a simple form. After calculations, we determined that this phase of cyclic switchover effect is characterized with hyperbolic reduction of point contact diameters, up to 3 nanometers. When diameters of synthesized point contacts reaches a level of around 3 nanometers, the frequency of growth dissolution processes decreases. This can testify about transition of the switchover process into a new phase. We suppose it is the phase of polydendritic commutation. Based on analysis of experimental data and model calculations, we can suppose that monotonic increase in point contact's lifetime can be caused with processes of passivation of active dissolution centers on dendrite tin tips, close to the surface of counter electrode. Creation of polydendritic structure is conjugated with decreasing of separate dendrites dimension. In this case, their free energy increases. This leads to the binding the tin dissolution centers with oxygen and the loss of their activity. As a result, a part of electron current, which determines electrochemical current, is reducing. This determines the increase in the point contact's lifetime, because electrochemical current is responsible for dissolution of point contact's conduction channel. Thus, the increase in the lifetime of point contacts at this phase of cyclic switchover effect can be considered as the dynamics of cyclic effect manifestation. That was my analysis of switchover effect in tin-based point contact system. And now we move into use of point contacts for its applications. Typical resistance dependence of dendritic Janssen point contacts on time recorded during cyclic switchover effect contains areas of constant conductivity. You can see there is areas of constant conductivity. They are named conduction steps and correspond to the metastable quantum states in the conduction of point contacts. Conduction steps emerging in a large number of successive cycles of growth dissolution were used to derive conductance histograms, which display the distribution of discrete point contacts conduction values. Conductance histograms reflect the probabilities of certain quantum states in conduction of point contacts and serves as unique energy profile of gaseous medium in which point contacts are synthesized. In different gaseous medium, conductance histograms have different forms. And as it was shown in our earlier studies of copper-based point contact systems, conductance histograms can be used to unambiguously identify the gaseous medium in which point contact structures are synthesized. Similar to copper, we can use other metals, as each of them has its own advantages, to realize cyclic switchover effect and to analyze gaseous medium. So we can say that Janssen point contact is a nanostructure with a set of unique properties which can be used for technical applications at the interface between different sciences, and primarily a sensitive element for gas sensors of a new generation. And also I wanted to add that the team of Professor Komarchuk has already developed a couple of gas analyzers based on Janssen point contacts and cyclic switchover effect function for different purposes. The most important of them is for defense against terrorist threats. It is a nano project that is now going on. That sensors allow us to analyze a breath gas. Emotional state of person can be clearly identified. Terrorists, especially suicide bombers, those like yesterday caused many deaths in Kabul, you know, have visibly changed emotional state. High sensitivity of our sensors allow to detect change of emotional state of single person from crowd. So a couple of them, of sensors, can be set up at, for example, reception state at airport and prevent many terrorist threats and following deaths. On the topic of sensors development for terrorist threats, defense against terrorist threats, the huge article is already almost ready for publishing. Thank you for your attention.
Thank you very much. Do you have any questions?
Yeah.
Thank you for interesting presentation. So you have shown the like atomic point contact structure, and there is a resistance and there are peaks in resistance. So these peaks are due to dissipation processes, right?
These peaks are due to electric to ion current through needle electrolyte anvil system, and low resistances are when point contact forms.
Yeah, because I mean, having narrow channel, basically you don't have so many dissipative centers, right? So in a sense, can you somehow indicate deeper the origin of those peaks? Is there any model, theoretical model, describing that in some kind of deeper way?
There is a couple of articles that Professor Komarchuk and Professor Vakula has published. You can see, I can show you these articles because mathematical models that we have in them are very complex, and they describe in every single stage of point contacts formation, and you can find there like the answer for your question, why do, like I understand you, why point contacts have those small size, and why do they even form? Yeah.
I mean it's, and what's the temperature range under which it's observed?
Room temperature.
So everything is done at room temperature, right?
Yeah.
I see. And is this a ballistic transport?
Yeah, you got it right. Electron mean free path is less than diameter and length of point contact, so ballistic regime is occur.
So what will happen if you switch to diffusive regime? Do you observe similar things?
It will be not Janssen point contact, and Of course, it still be nanostructure. It's still cyclic switchover effect can be obtained in that system, but properties of point contacts with diffuse regime are different from Janssen point contacts, and not so they're not so effective, simple point contacts. And by techniques that I mentioned, modified needle technique, we can obtain Janssen point contacts. Even Janssen point contacts, main characteristic of which is ballistic regime. Yeah?
Thank you.
Thank you.
Another questions?
Next questions, please.
No questions? Okay, thank you.
Thank you very much for the report.
Dear colleagues, thank you very much. Next section, Nanooptics and Photonics, will be start at 10:45, and now all participants of the conference are invited to the coffee break.
Dear colleagues, we can start. First presentation is from Elena Vinogradova, University of Tartu, Estonia, dedicated to fluorescence of neodymium-3 optical centers close to cubic symmetry in calcium fluoride crystals co-doped with natrium ions. Please, Elena.
Good afternoon, dear colleagues. So can I share my presentation now?
Yes. Yes, you can start.
Okay, and okay, so can you see the first slide?
Yes, we can.
Okay, thank you. Good afternoon, dear colleagues, again. I am Elena Vinogradova, a PhD student of University of Tartu, and my today presentation for this conference is about fluorescence of neodymium optical centers close to cubic symmetry in calcium fluoride crystal coupled with sodium. The objective of this work was to study certain single crystals, namely calcium fluorine crystals doped with neodymium and calcium fluorine crystals co-doped with neodymium and sodium by methods of site-selective optical spectroscopy in order to possibly find optical size of neodymium ion with a long relative lifetime and possibly pairs of such centers with weak resonance exchange. For this, we prepared certain samples and implemented laser site-selective and kinetic fluorescence spectroscopy for this study. For this research, we composed a certain experimental setup because the narrowness of the laser line width, which is used for excitation in the experiment, is of particular importance since it defines the site selectivity. We assembled this experimental setup with a really narrow laser line width. To test this setup, we decided to study to initially study optical centers which are well described in the literature, and then to move to possible new findings. To give the general understanding of what we were studying, I would like to give a short overview of types of optical centers of neodymium ions in calcium fluorine crystal. These are single centers with tetragonal symmetry, pair optical sites with rhombic symmetry, quartet optical sites with rhombic symmetry, and single optical sites with cubic or close to cubic symmetry. The first type, also known as L center, it occurs when triple charge neodymium ion replaces the double charge calcium position in the center of a cube face of the unit cell of the crystal lattice. In order to compensate for the excess charge, an extra fluorine takes a place nearby. For the pair and quartet centers, the situation is more or less the same. The difference is the amount of nearby neodymium ions and the compensating fluorines. If we're talking about single optical sites with cubic symmetry, it's a bit different. In some cases, it's possible that the excess charge is compensated by a non-local fluorine, and in this case, the near cubic symmetry is preserved. Here is a general schematic of certain crystal field energy levels of neodymium, which we used for our site-selective spectroscopy. Of course, there are much more of them. Here are only the ones that we were interested in. So this is the ground level, then the excited level, and the so-called metastable level. And of course, here they are shown by single lines, but in reality they are split due to crystal field effects. So what we will consider as fluorescence excitation spectrum, it's the dependence of radiation intensity of the wavelength of frequency of the exciting line. what we consider a fluorescence spectra is a dependence of the intensity of the radiation of the sample after it was excited. Now I would like to get back to our experimental findings. As I have mentioned, first of all, to set our experimental setup, we studied the optical centers that are well described in literature. To spare the time, I won't be going in details about this. I would like to just say that our present experimental findings are in quite good agreement with the different sources. Now to our new findings. First of all, a bit of information about the types of optical centers of neodymium ion in crystals doped with neodymium and sodium. Here we have a little bit different situation than what I have described earlier. The thing is that here we also have the neodymium ion substituting calcium, but also we have sodium ion. Due to the charge of neodymium and sodium, if we have a pair of neodymium and sodium, we don't need a fluorine to compensate for excess charge. So we can have cubic symmetry. So in some cases, we have cubic sites with symmetry close to OH, and when the compensation is non-local, we have cubic sites without inversion symmetry. So what we were able to find during our experiment. We started with crystal field theory calculations that predict that the excited states of nearly cubic sites with symmetry close to OH and C2V could have energy corresponding to a certain wavelength range. So we studied this wavelength range, and we were able to find this excitation spectra, and here we can detect certain peaks that are in good agreement with the calculations. Also, we studied this fluorescence spectrum corresponding to these excitation peaks, and here their values are also in good agreement with the theory. Also, the radiative decaying time of the for F3/2 crystal field level for these optical centers that are situated at these spectral positions, they are relatively long enough, almost 14 milliseconds. So that's why we have attributed to these optical centers as cubic sites with close to OH symmetry. Another optical sites we detected is the C2V type. Here it was the same logic as previously. The fluorescence excitation spectrum found in the area predicted by the crystal field calculations and the corresponding fluorescence spectrum. Also, here is the kinetics, the kinetics for these optical sites, and it also relatively long enough. Here is another interesting finding, actually. As I have mentioned before, we have also C4V single optical site, which is the L center, and its radiative decay time is about 1.5 millisecond, and this C2V optical site decay time is significantly longer. Well, on the one hand, it shouldn't be like this because based on the symmetry of these optical sites, the lifetime for C4V optical site should be longer. But we are explaining this result using a chart-of-field approach. It can be shown that the radiative decay time for this center depends on the distance to the nearest charge compensator. And because of the distance factor, this the radiative decay time for the C2V symmetry site is lower than the one for the site with higher for the site with higher symmetry. In addition, we identified a number of sites with different radiation lifetime. They are characterized by a set of fluorescence excitation lines. The most pronounced are here marked with different colored arrows. Here are the decay times for these optical sites, but studying of this optical sites type were not the objective of the paper and could probably be studied in the further research. So to conclude what was done. The nearly cubic sites of the neodymium ion were symmetrically close to Arch with relatively long radiative lifetime. Of the 3x2 crystal field level were detected in calcium fluorine single crystal coupled with neodymium and sodium at a temperature of 7 Kelvin using selective spectroscopy. Optical sites with C2V symmetry, where then sodium ion replaces the calcium ion in one of the positions adjacent to the neodymium ion to compensate for the additional charge, were detected. And also, we used a chat-offload approach to explain the difference of radiative lifetime of C2V and C4V centers, and to explain the appearance of strictly forbidden lines of the optical centers close to Arch symmetry. And also, we detected several new optical sites with fluorescence lifetime in the wide range. So, thank you for your attention, and please, questions.
Thank you, Elena. Have somebody question to Elena? No question. Thank you very much.
Okay, thank you.
Okay, our next presentation will be held by Professor Jaroslav Szopa from Cardinal Stefan Wyszyński University in Warsaw. Presentation is dedicated to characterization of single micrometer-sized droplets with luminescence nanoparticles levitating in linear electrodynamic trap.
Thank you very much for possibility of presentation results of our TAM work from Institute of Physics, Polish academic size. And Cardinal Stefan Wyszyński University in Warsaw. It is my university. It is a fourth university in Warsaw in the number of students. About 10,000 students study at 10 faculties. I work at the Faculty of Mathematics and Natural Science, but all experiments were carried out at the Institute of Physics, Polish Academy of Sciences. My purpose of our investigation is study of micrometer-sized droplet of suspension of nanoparticles, including luminescent nanoparticles. At the beginning, we adopted dynamic light scattering technique to study the light scattered by single micrometer-sized droplet here. Droplet was illuminated with two laser beams, red and blue laser. This scattered at 90-degree angle light detected by first photon counter system, and next real-time digital correlator that outputs autocorrelation function. Rest part of our setup is for stabilization of the droplet in the static position in electrodynamic quadrupole trap. This is the top view of our setup. And next, it is not so easy with dynamic light scattering. Intensity of the light scattered by single micrometer-sized droplet shows so-called Weiss-Perry-Callery phase, optical Weiss-Perry-Callery phase, like this. It is well known that autocorrelation function of periodic signal is also periodic with the same period. This situation significantly limits the possibilities of analyzing of autocorrelation function and obtaining parameters connected with the Brownian motion of the nanoparticles inside of the micrometer-sized droplet of suspension. Only at the end of the droplet evolution, after evaporation process, we can obtain finally autocorrelation function with exponential. Here, beta is so-called coherence factor, and main parameter of autocorrelation function is also characteristic time. This corresponds to decreasing of autocorrelation function at times 2.7. Autocorrelation function strongly depends on the accumulation time. Here you can see accumulation times 10,000 seconds, number 1, 20.5 second, number 3, and 7 second, number 4. Oscillation on function number 1 connected with Weisbree gallery waves, and only small part of this function here connected with Brownian motion of nanoparticle inside of the microdroplet. That is cure number 2. Cure number 5 is autocorrelation function corresponds to titanium suspension in classical experiment DLS in Kuwait. Insert here shows autofocus image of the mice scattering pattern, and right panel shows example of scanning electron microscope image of final structure of spherical aggregates, nanoparticles obtained after complete drying of microdroplets. Evaporation process of the microdroplets leads to increase in the particle concentration inside of the microdroplets and to formation of the non-rigid aggregates consisting of from several hundred nanoparticles. Here we can see in focus image of the pure droplet, and B, C, and D images corresponds to aggregates consisting from about 100 titanium spheres of 250 nanometer diameter. And based on this in-focus image and also based on movies, it can be concluded that random rotation of non-rigid aggregates induced change in shapes of aggregates and finally to change in scattered light intensity, and we can obtain at the end of the droplet evolution autocorrelation function like in classical DLS experiment. Autocorrelation function is exponential decay, but this function connected with the rotational motion of the droplets, but not connected with Brownian motion inside of the microdroplets. And the next is an experimental setup based on the vertically oriented linear linear electrodynamic quadrupolar trap. The droplet under test in here is a tenter. Droplet was illuminated with red laser and infrared laser power infrared laser. Power is about 1 watt. And this IR laser is used for exciting of the luminescent nanoparticles. And scattered light and luminescent light detected by USB spectrometer. And 2 cameras were used for stabilization droplet in the center of this trap. Next slide is photo of linear electrodynamic trap. You can see here injector, linear electrodes, micro droplet inside, 2 ring electrodes, about 10 kilovolts LC voltage with frequency about 250 hertz, connected on 4 linear electrodes. Macro droplet is here in center. Ring electrodes were used for balancing micro droplet inside in proper position using in focus image processing. Right panel show example of the droplet observed with CCD camera, and a DC field were obtained using feedback loop and gives always static position of the droplet inside of an electrodynamic trap. Here is a luminescence spectrum of neodymium doped gadolinium oxide nanoparticles in 3-ethylene glycol, obtained with USB fiber optic spectrometer, and we can see that bandstop filter, the optical density equals 6, cut off powerful laser radiation, and laser intensity here reduced 1 million times compared to luminescent. Here is the center, and spontaneous emission of the laser media can be also here visible, and maximum of the luminescence spectra is about it's close to 900 nanometer. Here is a sample of the photoluminescence spectra consisting of 6 sharp wavelengths, region of the interest. And we can observe simultaneously temporal evolution of the luminescence at 6 wavelengths. And we can see here a fragment of the temporal evolution from 300 to 500 minutes. And it is difficult to see here regularity in this dependence, but more interesting is ratio of the intensities for 2 close wavelengths. For example, wavelengths of 894 and 892 nanometers here, 2 close lines. And temporal evolution of this ratio show oscillation. Red lines is averaged plot, and show for oscillation connected with Weisbury gallery waves. One period on this oscillation corresponds to change in the circumference of the droplets by 1/2 of wavelengths. And next example, the temporal evolution of the scattered light from red laser and infrared laser. We can see here that red laser oscillation better reflects the changes in diameter of the microdroplet. And we can obtain about 50 such experiments, but results still need to be analyzed. And finally, we have obtained articulation function at the end of the droplet evolution, but dynamic light scattering technique has limited possibilities for analyzing the micrometer-sized droplet. Linear electrodynamic quadrupole trap is better for trapping and to observe a highly absorbent droplet of suspension, and using luminescent nanoparticle gadolinium oxide doped with neodymium ion gives possibility to analyze evaporated droplet of suspension. Thank you very much.
Thank you. We have somebody question to Professor Chopin. Then I have question. Sorry.
Can you please again explain us what is nature of pure microdroplet? You added titanium oxide nanoparticles in microdroplet, yeah?
The new oxide nanoparticles, yes.
Yeah, and what is nature of pure microdroplet?
Pure? Pure microdroplet has no luminescence, no scattered light. Pure microdroplet you can observe using my scattering pattern. That's the oscillation of the intensity.
Then what the microdroplet is? Like it is a kind of material. It is liquid or
alcohol.
Hydrodroplets are here. Tetraethylene glycol. This is high polarity molecules. Is very, very slowly evaporated. The evaporated time is about 5 hours.
And they consist in form of it's just hard for me to understand. They consist in form of liquid or something between liquid and like gas or
form above.
That microdroplet it consists in your trap between electrodes in form of liquid or gas or just ionized gas.
A droplet has electrical charge. This electrical charge droplet obtained in process of injection. We have used also electrical field charger external to obtain high electrical charge.
So microdroplet is something ionized, yeah?
Yes.
Okay, thank you.
You have selected for your investigation tetraethylene glycol, but why tetraethylene glycol? Why not penta, diethylene glycol or other?
No, tetraethylene glycol, because very, very slowly operated. It is very, very important that droplet we can observe long time. The water droplet evaporated in 10 seconds.
Yes.
We cannot observe any results in so short time.
And have influence hydrophilicity of tetraethylene glycol on this experiment? Because normally all ethylene glycol absorb water.
Triethylene glycol or tetraethylene glycol. It is ethylene glycol, tetraethylene glycol, tetraethylene glycol, it's different properties. So.
Yes, I know, but normally all ethylene glycols, from ethylene glycol up to polyethylene glycol, absorb water. And when they not dried, they have maybe different.
Absorb water is normally. You can.
But has no influence on experiment.
Influence, yeah, not really influence. The end of the droplet diffusion is equilibration with water and
Okay, thank you. Somebody have a question? Or we are ready? Thank you. Next presentation from Dr. Svetlana Bogachuk, Institute of Physics of National Academy of Science, Ukraine. Surface confined, optically controlled liquid crystal elements. Please.
Good morning, everybody. I would like to present my report, the surface confined, optically controlled liquid crystals elements. This work is carried out by combining groups from the Institute of Physics in Kyiv, Ukraine, and from the National Aviation University in Ukraine. Nowadays, the dynamic holography is increased very much. Because of it deals with the images, it processing the images and transmission the images. Here is a typical scheme of digital dynamic holography, the recording of images and recovery these images. The important things and applications, very big applications of digital dynamic holography is that the optical images are saved in computer, so it is possible to transmit them by internet. Another huge market of the dynamic holography is the holographic displays. And this technology allows to obtain 3D virtual images. Here is the list of application, the modern application of the holography, dynamic holography nowadays, and it listing completely decreased. Among them is the permanent and dynamic optical memory, optical tweezers, manipulations, microparticles, microsystems, metrology, also optical visualization in biology and medicine. The main element of modern holographic system is the special light modulator. This is a matrix of liquid crystal cells or pixels, and which of them has an electric contact. And the aim of SLMs is the transform optical wavefronts under influence of electric field distributed over the matrix. The mechanism of such transformation is the reorientation of LC molecules under action of electric field. And due to this reorientation, collective reorientation, the refractive index is changed, so the transmittance of light is changed as well. But there is a big problem in modern holographic system. It concerns the response time or speed of manipulation of information. The computer usually operates with frequency regime. This is gigahertz that corresponds operate time nanoseconds. But the reorientation of liquid crystals molecules is in 5 orders less. That is 10th millisecond for nematic liquid crystals or 10th microsecond for ferroelectric liquid crystals. But ferroelectric liquid crystals are very expensive and they require a very big voltages. To overcome this problem, one of the approach is to develop confined liquid crystal systems. And there are two directions. The first one is the creation polymer dispersed liquid crystals, where liquid crystals is confined inside a bubble, inside of polymers, bubbles of polymers. And the another approach is the introduce of nanoparticles of different kind inside the volume of liquid crystal cell. But our research showed that confinement effect can be reached by in the inorganic-organic interface, which consists of a solid surface of different structure and a thin layer of LC molecules. We, in our research, showed that the response time in such system in liquid crystal cells is decreased, and the values of nonlinear optical coefficients are increased. Here is present the method of our experiments, and we use the two-way mixing technique. This is one of the most useful technique in the dynamic holography. The beam from laser is divided on two beams, which are converged on the sample and create a light interference pattern. The periodic lights modulate the refractive index due to different nonlinear optical effects. And this modulated refractive index is actually a recorded grating, dynamic grating. Due to diffraction of recording beam on this dynamic grating, one observes many diffraction orders. Also, one may use a big probe beam from helium lasers, which put on the break angle relative to the dynamic grating. And we can see the picture of many diffraction orders of a probe beam on the output. Also, this technique allows to define nonlinear optical coefficient. G3 is the coefficient of third order nonlinear susceptibility. It is proportional to the N2, which is the coefficient of nonlinear refraction. N2 is calculated from this formula, where in diffraction efficiency in the which determines the intensity in the first diffraction orders. We consider the photorefractive effect of reorientation liquid crystals molecules. This effect is connected with creation of unstable charge and electric field inside the LC cell. Here is the picture of surface-induced photorefractive effect. In the beginning, there is a homogeneous distribution of charge B layer. But under influence of periodic light interference pattern, the charge is distributed. There is periodic distribution of charge due to different mechanisms. One of them is the desorption of charge inside a volume of LC. Then the periodic charge is created on the inorganic-organic interface, and which creates the periodic electric field, and molecules are reoriented along this electric field. So there is formation of periodic director of LC molecules. We propose a liquid crystal cell. The feature of this cell is there is a common surface. In our case, the common surface was gold nano island film. This absorption spectrum showed the surface plasmon resonance on gold nano island. In our first experiments, the layer of liquid crystals was 20 microns. And in this case, we observed that grating have been almost continuous, almost stationary. So the response time of this, the relaxation time of this grating was about several hours or even the days. But we can find the coefficient of nonlinear refraction N2. It was in the order of 10⁻⁴, and I want to point out that the liquid crystals have the highest value of the nonlinear optical coefficient due to this mechanism of reorientation of LC molecules. We assume that response time depends on two factors. One of them is the morphology of gold nano-island field, and second is the thickness of LC layer. So we prepared the composite cell, and the common surface have the gradient gold nano-island film. Here is the same pictures of different points or areas of this nano-sized film, from a small one, then gold nanoparticle have the size tens nanometers, to the big ones, the nanoparticles have the size about microns. Our two-way mixing experiments showed that the best results is for the point 3 and 5, the medium size of nanoparticles. In this case, there was recorded gratings which high relaxation time and the maximum diffraction efficiency. In the case of small nanoparticles, 0.1, the diffraction efficiency was decreased, and in the case of big nanoparticles, points 11 and 12, the gratings have been stationary one. Here is present the typical experiment of the intensities on the first diffraction orders on the output from different points of the composite cells under action of impulse input pulse. And from these measurements we find the time constants for grating recording, turn on, and grating relaxation, turn off. And one can see that time of grating recording that does not depend on the size of nanoparticles, but relaxation time is decreased to the 1-2 seconds, and it depends on the size of nanoparticles. Another experiment, our experiments, have been for two-way mixing when applying periodic electric voltage. We managed to have the frequency of input voltage 20 Hertz. So that corresponds to efficient time of grating relaxation, 50 milliseconds. The graph below shows that there is the optimum value of voltage in where the diffraction efficiency is maximum. Also, this graph demonstrates the effect of energy transfer during wave mixing. So the intensity in the +1 diffraction order is higher than the intensity in -1 diffraction order. And finally, this slide presents our last experiments. We found that the diffraction efficiency depends on the type of the common surface. In our case, that was chalcogenide glass, and some image of it is shown below. And the graphs show the diffraction efficiency for different common surface. And we find when in the case of halcogenide glass, the sign negative, the sign of voltage should be negative on the common surface. This is the blue curves. And in the case of the gold nano-island film, the sign of voltage should be positive on the common surface. This is the black graph. So our conclusion is the following. The response time of reorientation of LC molecules can be managed when creating an internal electric field in volume of LC cells. This local value of electric field can be controlled by creating nanoparticles of different nature, type and shape and size, and which are distributed on one substrate. And then these nanoparticles define different mechanisms to creations of internal unstable charge and internal electric field. This mechanism may be creating excitation of different quasi-particles such as plasmon, for metallic nanoparticles, excitons, for semiconductor nanoparticles, or polaritons, focus nanoparticles. Also, generation of unstable charge and enhancement of local field effector. Our research allows to create a closed model to surface-induced photorefractive effect, and also to develop a technology for creating liquid crystals elements which have ultra-fast response. Thank you for the invitation.
Thank you. Have somebody question to Svetlana?
Уже пришел как раз.
I have a question. Okay. Thank you. With pleasure, I will invite Professor Evgen Glushko from Lashkarov Institute of Semiconductors Physics of National Academy of Science of Ukraine with presentation, local modes and local resonance in photonic structures containing doubled defect applications. Please. Online, okay.
Evgen, can you hear us? Hello?
nets, optical nets, maybe based on photonic crystals and such.
Evgen, we cannot hear you.
Please speak into the phone, because we cannot hear you.
Не знаю, он положил телефон.
And we can go by. Go away. Yes. And now I will invite Dr. Oleg Yermakov. Dr. Oleg Yermakov from Kazarin Kharkiv National University with his presentation Hyperbolic Plasmons at Resonant Anisotropic Metasurfaces. Dr. Oleg Yermakov.
Dr. Oleg Yermakov.
I will invite Dr. Andrei Lin from Institute of Physics, National Academy of Sciences of Ukraine, with presentation Dynamics of Optical Activity of Polymer Stabilized Blue Gases.
Just a moment, we will open. This one's yours, yeah?
Yes, probably. Is it possible? Yeah. Ladies and gentlemen, dear colleagues, I'm very happy to be here, and I'd like to express my greatest gratitude to conference organizers to make such a great event in such a lovely place and in such a beautiful city. And my special thanks go for the best conference coffee I ever had here, so it's definitely. My talk deals with blue phase. It's a type of liquid crystals with some peculiar orienting properties, and deals with dynamics of optical activity of these thin films of blue phase samples. The work was done in cooperation with Institute for Materials Chemistry and Engineering in Kyushu University. Blue phase, it's a type of chiral material which consists of chiral molecules. That means that molecules do not have mirror symmetry, and intermolecular interaction potential is so that it forces molecules to align close to each other, align with a bit, a little angle, a small angle, not well parallel each other. And so when we go in some direction, add more molecules, each molecule turns a little bit further on, and we have a spontaneously appearing axis to which in every point molecules are perpendicular, and while traveling along this axis we can see that molecules change their orientation more or less continuously, but each in each plane perpendicular to this axis it is molecules deemed to be parallel to each other, and so reminiscent of nematic phase, and so these types of crystals is called chiral nematic liquid crystals. When I came to the Institute of Physics more than 30 years ago, I had been told that liquid crystal science is a new type of science with respect to, if compared with laser physics or semiconductor physics. But things are not that simple, because the first ever observation of liquid crystals was made by Professor Julius von Planner. This year we can celebrate 160 years from the first paper published describing the optical properties of cholesterol chloride, and due to these interesting materials, chiral nematics, usually also called as cholesterics. So his paper came in 1861, and I'd like to say that this very time only Maxwell equations were derived and published, and electron identified as a particle much later. So, but what is more interesting is that these experiments were done here in Lviv. Here you can see the picture of Medical Surgical Institute, which belonged to Lviv University. Just the picture taken just around the time Planner was working here. He was a chemist and the leader of Department of Anatomy, and two days ago, you can see here this picture is less than 10 minutes from here. This is now the department, this house accommodates departments of biology and geology of Lviv National University. It's Grushevsky, number 4. Well, so if we consider chiral pneumatic liquid crystal, this schematic sketch of construction of the phase, one can see that while we move along the axis, this axis which makes on optical axis also of this material, the condition to minimize interaction, energy of intermolecular interaction between adjacent molecules is fulfilled along this direction, but it is not that along x direction. Well, when we can see that in every plane molecules are parallel each other. It means that there is no small angle in between them. So chiral pneumatic liquid crystals by definition are belong to frustrated phases. But what we could consider what would happen if we have chirality of molecules, the strength of this turn of molecules higher, stronger. Then we would need the molecules to make this small angle in any direction. Indeed, this makes the sense of blue phase organization when we have, let's say, every single molecule, and while going outside this central molecule in each direction, we observe twist of adjacent molecules, and this type of organization is called double twist cylinder. However, it's better called omni-twist because in every direction from the center outwards there is a twist. And this disc-like constructions could add up, stack up, and make a double cylinder. But because of topology considerations, it is not possible to continuously, infinitely extend this twist outside the cylinder, and the twist ends at approximately pi/4. So these cylinders are limited in diameter, and it is pretty less than 100 nanometers. And all these cylinders are arranged in different configurations, making more or less complex unit cell, as you can see here, and divided by disclination lines where liquid crystalline ordering is lost. This is much more frustrated phase that chiral pneumatics are, and because of that, the temperature range of this phase existence is pretty small, usually less than 1 degree. However, introduction of prepolymer molecules, which are subject to photopolymerization, is possible to stabilize such a phase, and the existence temperature range of phase existence increases greatly, and it makes then sense to work with such materials and to investigate them. Well, so the first observations have shown that these materials, these samples of this material responds to electric field application as with Kerr-type electro-optic effect, which is so the induced electrical field induced by refrigerants is proportional to field square, and it realizes very fast electro-optic response, much less than 1 millisecond. This is for in-plane electric field. But if you look from any point at the unit cell of such composition, we can see that from any direction light traveling through this cell light goes perpendicular to these cylinders, and light sees the twist. Short pitch twist, which is much less than wavelengths of light, but nevertheless such a twist imposes optical activity, imposes polarization, rotation on the light field, and the sample has very well profound optical activity and rotates polarization. So if to measure transmit light, white light through the cell with different polarization of analyzer, we can measure Stokes parameters of light and dependencies of Stokes parameters on wavelengths, and calculate polarization states such as ellipticity and orientation of big polarization axis depending on the wavelengths. We can see here that in the region close to half of double the period of helix, we can see very strong optical activity and change of ellipticity. So just to show that for thin samples, different orientation types of substrates provide quite different, first of all, microscopic pictures, and also we can see that different modes are selected and are seen in optical activity measurements. So if to apply on-axis electric field in such a case and measure transmission through the cell of the laser light, the green laser at 532 nanometers, so if we put between not crossed polarizers, but polarizers is arranged so that we minimize its transmission of the system. So we can see that application of electric field also is accompanied with the modulation, with an increase of transmission. And if to plot a transmission versus voltage curve, we can see quite nice pictures for different frequencies of applied electric field, and with the maximum, with a field magnitude of 100 volts. So this picture is corresponding, such dependencies correspond to elastic deformation, and we can see that we can fit very well, at least at higher frequencies, dependencies with simple rate-dependent hysteresis, where applied the response is phase shifted with respect to applied electric field. And if we further increased voltage up to 200 volts, we can see pure saturation of the signal. And in such a case, we also can say that this is rate-dependent hysteresis, however, which is of the different nature, which is saturated signal, and it has a little bit more complex dependence. What the reason of the nature of such modulation of signal with application of high voltage is that under voltage application, liquid crystal molecules collectively are oriented parallel to electric field applied, and so the twist disappears, and we cannot see optical activities, and then the light polarization change its orientation, and we can see the signal. So can conclude with that it was very interesting system, and we observed electro-optic modulation of optical activity, which is described with ray-dependent type of hysteresis with characteristic times about 1 millisecond and saturation at voltages approaching 200 volts. It is optical activity is modulated with the application of on-axis electric fields. It means it is possible to create special late modulation. Sorry. Yes. Yeah. So my time is almost gone. So it is possible to create some kind of special light modulator which modulates orientation of polarization axis. And as a byproduct, we can see that textures of polymer stabilized blue phase are obviously influenced by orientation. And thank you very much for your attention. And
thank you very much. Have somebody question to Andrei, Helene? Yes, please.
Yes, I would like to ask. So this your description of liquid crystals is by mean field theory in a way, right? So can you give some comment on mathematical models describing the order parameter in space for liquid crystals? What type of fields they are, like scalar fields, complex value fields? You know, it's like in Ginzburg-Landau theory, there is a theory for order parameter, right?
Yes, yeah, I understand.
But there is a control parameter in case of superconductors, it's like magnetic field, and in your system probably it's electric field, right?
Yeah, but I'm not. You're right that there are different descriptions of order parameter in liquid crystals. They work well, but here. We believe that electric field application does not affect the order parameter.
So what does it affect?
It affects orientation of liquid crystal directly. So it's on more bigger scale, not local scale, molecular scale, and probably order parameter is influenced somehow, but we do not see this at all.
The second question is the theory of phase transitions. Probably this is quite complex phenomena with phase transitions in case of liquid crystals. Is it secondary order phase transition or other type of phase transition?
It is called weak first order. Weak first order transition.
What does it mean?
It's soft matter, and there are no exact points. So the phase transition temperature is not an exact temperature, but it's a range around several tenths of degree usually. It's not sharp. It's not the derivative on the order parameter at the phase transition point is not infinitely large. It has some meaning, but all other things behave like first order parameter around, but it's at very point it's not that.
Have somebody a question also? Yeah? I have a question.
Thank you very much.
Institute of Physics ignore me. I have also a question.
Sorry, I don't. I wanted to run for coffee, but I will.
Just a moment. Okay, you can say about stabilization with photopolymerization.
Yes.
Has this influence on reorganization? Photopolymers.
It's better probably to back here. So because of elasticity and strong elastic deformations inside liquid crystal matrix, prepolymer molecules, prepolymer fragments.
I'm chemist, I understand.
Yes. But it's not a molecule, sometimes it's bigger, because, so I am very cautious to name it exactly. So they go into declination lines, like here. Okay. And they, under photopolymerization, this network stays inside these declination lines. So they stabilize orientation, as you have seen for a wider range. So then it definitely, so it is like distributed boundary, surface inside the cell. And under application of electric field, reorientation of liquid crystal between these declination lines, former declination lines, is more stabilized with this. So reorientation changes its character, but we're happy that it's stable in sense that any reasonable field does not destroy the cell, and orientation comes back to its initial state.
De facto, you have not fully polymerization.
Yeah, definitely, yeah. It is almost completely photopolymerized substance. Almost all molecules of prepolymer fragments that came inside this mixture, they are photopolymerized. But they do not make a volume, they are concentrated in these declination lines between double twist cylinders. So it is completely polymerized, but it is not, it is distributed within...
Density of cross-linking is not so high.
Yes.
Okay, thank you.
Thank you. Now, I'm cautious.
Yes, you can go. Now we have connected Dr. Oleg Yermakov, and we can hear his presentation, hyperbolic plasmons at resonant anisotropic metasurfaces. Oleg Yermakov is from Kazarin, Kharkiv National University from Ukraine.
Hello, did you see my screen?
Now you can start.
I started. Let's try again. Now you see?
Yes, yes.
Yes, so I can start.
We can see, you can start.
Okay, thank you. So yeah, first of all, thank you to the organizers. Very nice conference, which covers a broad range of nice topics, nice talks. Thank you today and yesterday's speakers who covered some plasmonic topics, and I will continue. So my talk is devoted to hyperbolic plasmons. And a brief introduction, just classical optical devices such as lenses, mirrors, filters become to seek functionally and fundamentally limited. It emphasizes the emergence of resonant photonics, which uses subvalence, multifunctional structures, which can overcome some fundamental limits. The resonant photonics platform consists of metasurfaces, metalenses, different nanostructures, and nanoparticles, but I will focus on metasurfaces, which are two-dimensional periodic arrays of subvalence scatterers, enabling to manipulate light on demand. So the study devoted to metasurface can be divided into two branches. The first one considers them as the transformers of plane waves. So these are reflectors, refractors, absorbers, lenses, etc. In this case, we are working inside the light cone in this region of dispersion diagram. While for other applications, such as integrated circuits, sensing and chip devices, for any planar technologies, one needs to manipulate light over a surface, almost in two-dimensional space. In this case, we should go under the light cone in this near-field region, and the good candidate for localized light is surface plasmon polariton, which is just a surface electromagnetic wave. The relative applications for surface plasmons, such as sensing, emission enhancement, lensing, quantum physics, optomechanics, etc., and the relative different types of surface waves, but all these types select for tunable wavefront and polarization control, and this is my main goal to discover them. So I will start from the quite simple surface conductivity tensor approach. I will substitute two-dimensional layer by anisotropic conductivity tensor. This approach can be introduced for many different systems and different frequency ranges. And this is one of the possible example of the realization of this metasurface consisting of a periodic array of gold thin nanodiscs with elliptical shape. Okay, let me consider first of all the tropic metasurface. In this, which resonance response of a Drude-Lorentz model. So in this case, we have two regions depending on frequency, where imaginary part of conductivity is either positive or negative, and we can consider. We can consider two modes depending on the frequency, either T or TM, two plasmons here, but only one plasmon can exist at each frequency. We will now go to the anisotropic case as the resonance splits, and the third regime emerges, indeed the most interesting one, which is called hyperbolic, because in the reciprocal lattice vector spaces, the isofrequency condors have hyperbolic-like shape. In this region, sigmas have different signs. One is positive, second is negative. And this approach was verified by using some experiments and numerical models. So it is absolutely relevant. And now I would like to consider this problem when we illuminate the metasurface, describe it within this surface conductivity tensor, which lies at the interface between two media. We can derive the dispersion equation, which is shown here. The left part consists of two factors, which corresponds to purely T and TM plasmons, such as graphene plasmons. And in the right part of this equation, we have some coupling factor. If this factor is 0, we return to the isotropic case. If it's not 0, we have the mixing or hybridization of two solutions, TM and T. So the eigenmode spectrum of this metasurface consists of two modes with hybrid TM polarization. So all 6 components of electromagnetic fields are presented in this case. But only one component is dominant, so we call them quasi-T or quasi-TM. Here you can see the dispersion relation drawn for different propagation ends. This hybridization leads to several nice features. First of all, we can see different regimes of propagation. Here I show the isofrequency contours in the K-vector space, and we can see different shape of these contours: ellipses, hyperbolas, flat lines, eight-like shapes, rhombus, arcs, etc. All this means different regimes of propagation, because the shape of this contour directly inherits the symmetry of the excited electromagnetic fields distributions. So we can see absolutely different field distribution patterns, and let's make some small analysis just to show how it works. So for instance, here we have elliptic-like as a frequency contour, and the field excited by this point-like dipole shown by red arrow looks like just dipole emission, but this is surface wave still. Here we have two contours. The first is hyperbola, and we see the typical cross, and the second is this arc, and we see this less intensive arcs. This rhombus corresponds to 4 quasi-flat wavefronts, and my favorite regime is flat lines, which corresponds to the ultra-focused set propagation of surface waves along one direction. This regime is called canalization. Also, in hyperbolic regime of metasurface, 2 modes can exist simultaneously, which is in sharp contrast to isotropic case. It is supported by the frequency contours field distributions. Okay, it was theory. What about the experiment? As predicted, this hybrid TTM waves, which is called hyperbolic plasmons, because they exist at hyperbolic metasurfaces. So they were discovered in microwaves by a group of Hongjin Chen and Kostas Sekoulis. And then in optical range by our group using this discussed metasurface with gold nanodiscs. We performed using attenuated total internal reflection setup in auto configuration. So we measure the reflection spectrum in internal total reflection regime, and these dips in the spectrum corresponds exactly to the plasmons with great coincidence with theory. And we also performed the experiment in microwave range, where we used, for instance, vertical electric dipole as a source, vertical magnetic dipole as a receiver. So for isotropic case, we should see nothing, but for this hyperbolic metasurface, we can find the non-zero signal and recover the isofrequency contours and define the direction of maximum hybridization. Okay, and last part is devoted to the very recent result, which was indeed published just previous week in very prestigious journal Physical Review X. It is devoted to surface waves and also hyperbolic plasmons at self-complementary metasurface. So what does it mean, self-complementary? This is a metasurface which obeys Babinets principle. So I just remains that, yeah, Babinets principle can connect the diffraction pattern from inverted structure. So you can observe the diffraction from the hole in the metal screen, and it means that then you will know the diffraction pattern from the inverted, so just from this metal pattern with the same shape and size. Okay, so we consider the metasurface, which in simple words consists of inductive and capacitive lines. This is the proper design of this metasurface, and this zigzag-like pattern needs to exhibit multiple resonances. And the main point is that this metasurface obeys this relation, where y, this is the admittance inverse value of surface impedance, so we can just imagine that this is surface conductivity, but for microwaves. Okay, and it exhibits several features. The first one, this metasurface is hyperbolic at any frequency. This is in sharp contrast to any other anisotropic dimensional systems where hyperbolic regime can be observed only in limited range between two resonances. Here, it is hyperbolic everywhere, so hyperbolic plasmons can be easily excited. Secondly, we can see isofrequency contours and find that there are also these flat lines, which means canalization regime, but here they can be switched from vertical to horizontal. And secondly, if we will compare with other systems, we can see that the lines are more flat. So it means that we call this regime extreme canalization with almost no divergence. And finally, in special directions, it is a bit polarization degenerate spectrum. So the dispersions of T and TM modes are absolutely the same. It means that we can switch and change the polarization of propagating surface waves and even create the analogs of planar polarizers for localized light, which were not possible to date. It is also confirmed experimentally. So here you can see the field distribution excited by point dipoles, simulation and experiment, and they recover the frequency contours. So you can see here this hyperbolic-like wavefronts. You can see the switching from horizontal to vertical and again to horizontal canalization regime of surface waves propagation. And finally, we can exhibit the canalization and polarization that generate spectrum at the same frequency, which means that we can transfer the signal from point to point by saving the polarization of the source. So to conclude, I just invite you to refer to the following references describing theoretical predictions with the local effective model, optical and microwaves experiment, the technique to retrieve the surface conductivity of any two-dimensional plasmonic metasurface, and the extraordinary features of surface waves at self-complementary metasurfaces. And I would like to thank my co-author from Mo University, from Technical University of Denmark, group of Professor Andrei Lavrenenko, Yuri Kishar from Australian National University, Kostya Blov from Riken, Japan, Professor Stefano Maccio from University of Siena, and Juan Buen from University of Columbia, and indeed many others. Thank you for your attention.
Thank you very much, Oleg. Have somebody question? No question? Thank you again.
Thank you.
Next presentation is from Dr. Alexander Sorokin, Institute of Scintillation Materials of National Academy of Science. Spectroscopic study of amphi-PIC jet aggregates interaction with bovine serum albumin. I hope that's right. I will try.
Which is connected with spectroscopic study of some type of J aggregation interaction with bovine serum albumin. J aggregates are molecular aggregates formed by different flat plane molecules of different organic dyes. The most known one is the cyanide dyes, and it was discovered in the end of the 30s of 20th centuries, independently by Edward Jelly and Günther Scheibe in England, in Germany, correspondingly, and they was named by one of their discoverers named jelly. So J aggregate is aggregates of jelly. And the most interesting feature of the J aggregates is their very good arrangement of the molecules within this aggregate. And these dye are connected by, first of all, van der Waals, quite small V interaction, and so due to this arrangement, where is the reason? The exciton, friendly exciton formed in these aggregates. So such type of aggregates are some low-dimensional type of molecular crystals. But unlike the large-scale 3D molecular crystals, they have unique spectral properties which can very relatively easily changed by, for example, interaction with different surrounding, changing the solvate molecule, and so on. And to see that J aggregates are formed in your solution, you should see the very narrow spectral line which have excitonic properties, which are shifted to the red relatively to monomers, so-called J band. So this is excitonic band of J aggregates. Sometimes it could be obtained also hypsochromically shifted band, H band, but the luminescent one is only J band state. So this is low excitonic state, and you can see near recent luminescence, quite efficient. And the optical properties of aggregate are strongly correlated with so-called exciton delocalization length. This is also one of difference from the large 3D molecular crystals, because in such crystals the exciton are spread over all crystal, but in G aggregates only small segment of molecular chain take the delocalization of this exciton, and so change this parameter we can influence on the optical properties of aggregates. Very quickly, such type of aggregates find their application. They have very high extinction coefficient, they have very high oscillator strength, and so on. They was found as the best photosynthesizers for photographic materials. Also, they have used as a very efficient photonic antenna for different photoelectronic devices, because they could be used as a very, very thin films. But currently I will tell you about some biological application. So these type of aggregates, some type of aggregates could be used as efficient luminescent probes for biological. One of them, is, for example, is very well-known so-called GC1 aggregates, which form aggregate only when you're on mitochondria, when mitochondria are alive and the cell is alive, and you can see difference between monomer luminescent, aggregate luminescent, depending on the living cycle of the living cell. Another very interesting application that due to this strong red shift of aggregate, it was obtained some type of dyes which form the aggregate which have optical transition in near infrared region, and not only in so-called near 1, but also in so-called near 2. So it's very important for biological application, because the living tissues have much more penetration of light, reveal such, and have not any other signals. So this region is to about 105 microns. Is very important for biological application. So, and it was recently shown that some of aggregates could be formed and have these J bands and luminescence in this near to spectral range. However, one of the problems of biological application as because these aggregates are formed by weak interactions, they could disaggregate in, for example, blood and cells. So we need to understand how it will be stable in such living cells, and it's known that such one of the main protein of blood, such as albumin, could interact with different dyes, could interact with different nanoparticles. For example, forming so-called protein corona around nanoparticles, and could be used as a drug carrier. And this also very recent interest of scientists for this application. However, when it's interact with G aggregates, with those G aggregates who has the transition in near-infrared region, is in most cases lead to disaggregation of aggregate, and it solubilize independent separate molecules within albumin. So when we place such a very interesting potential aggregates to the blood, we can just lost it. And we try to understand if we can find some systems where such interaction will be better for aggregates. So we look for different class of cyanides and choose one of them which we very well known, so-called amphiphilic analog of pseudoisocyanide dye. This PIC dye is very known, but the amphi-PIC, so amphiphilic analog, which has a very long hydrophobic tail, it has other features compared with these PIC dyes. So it have quite wide bands, quite low quantum yield. However, it's very stable in different solutions due to they form the closed structures like these surfactant methyls. And in solution, it can be present as such small cylinders, but they tend to agglomerate individual aggregates to form larger scales. In some cases, they can form such disc-like structures. We have found with our colleagues that it also have different such cylinders which packet in these discs. So we try to analyze is the interaction with albumin will lead to disaggregation or some improvement of excitonic properties of such aggregates. And indeed, we have seen that in the solution which imitate the blood, so it is this bufferic solution. In case of interaction with albumin, we have seen increase of intensity gem bands, but also it's widening. So we have other properties of stone compared with just solution, and all changing the time result spectra. It's the changes are summarized on this table. The main of changes these the delocalization length increasing in case of interaction with albumin molecules, so we have less static disorder, and it's very interesting some increasing of luminescent quantum yield we have found, and also the luminescent lifetime are also increased. But the very interesting result that the physical size of this type of aggregates are strongly changed. We have seen estimated using dynamic late scattering. So in solution we have very large objects, so this we have deal with these agglomerates. Of course, this only estimation because DLS is rather indirect method. But in case of interaction with albumin molecules, we have found very strong decreasing of the this type of aggregates or objects inside this solution. For example, just albumin molecules have dimension about 10 nanometers, and in case of interaction with amphi-PIC aggregates, we have about 130 nanometers diameter size of the objects in the solution. We have analyzed the aggregate properties and low temperature, and we have found that first of all we have not seen any spectra and any bands corresponding to exciton cell trapping, which we have seen for our case of aggregate in just water solution. And also the lifetime strongly increasing. So if for aggregates without albumin we have seen about 100 picoseconds lifetime average, this is average value. In case of interaction with albumin molecules, we have found about 1 nanosecond. It's very drastic changes in optical properties. We have supposed that in case of aggregates which form interact with albumins, we have complexes, and the so-called such effect as exciton cell trapping is rather one-dimensional one, and in this case we have similar results obtained for other type of aggregates without any albumins. So we can apply the results obtained for this aggregate for our case, and we suppose that the main influence of albumin interaction with aggregates that they lead to the some disagglomeration. So we have deal rather with individual aggregates, but not with this large agglomerate. As a result, we have not only improvement of exciton properties, but have found stronger enhancement of aggregate photostability. It's one of the also problem for such type aggregates, because as for application, for example, in as a luminescent probes, but it's also the problem for mostly organic species, that the photostability, especially when you use microscopy setup, it's very limited. And in case of interaction with albumin, we have seen stronger enhancement of aggregate photostability. So we proposed the model when the aggregate interact with albumin, and we have predominating concentration in this case of albumin combined with our dyes. The albumin forms type of protein corona which coat the aggregates, and as a result the agglomeration is prevented, and we have deal with separated aggregate, and this lead to significant improvement of their excitonic properties, for example, for their photostability, due to several type of defects appeared on interaction surfaces, on interfaces between individual aggregates when they are agglomerated. And we can make such conclusions, so we obtain effective and stable complexes of amphi-PIT aggregates with bovine serum albumin molecules, which lead to improvement of exciton properties of the aggregate at room temperature, and we propose the model of chronon formation around the aggregates in these complexes, and as a result we have obtained promising results which can be further developed as for luminescent probes for microscopy. Thank you for your attention.
Thank you very much. Have somebody question to Alexander? Okay, I have a question. You have used the less method for control of size, and but you have not spherical particles, and the less theory is for spherical, not for disk particles.
Yes, but despite it, the less could be provide you some very average information. This is this is estimation. Now we try with our colleagues which work with electron microscopy to obtain that, but some technical problems still. Because unfortunately mostly of these microscopists work with solid stables, with crystals, and there is some features for work with these molecular for molecular species. So we try to obtain the direct imaging, but it's not still realized up to now.
Okay, thank you. More questions?
Thank you.
Next presentation from Dr. Krzysztof Pomorski, Krakow University of Technology. Quantum information processing in nanostructures in photonic Tice-Winding model. Please.
Should I use my laptop or your laptop?
Feel better to use our laptop.
Oh, okay, this presentation over here.
Okay, thank you.
At Krakow University of Technology. I'm also founder of a quantum hardware system company that deals with quantum technologies, and I would like to give a short introduction to technologies related with single electron devices that are currently under implementation. So basically, last 15, well, let's say. In quantum computation, the dominating trend is to use spin degrees of freedom for encoding the quantum information.
Just a moment.
And maybe from my laptop it doesn't have this. Okay. And however, this spin degrees of freedom require very control of magnetic field over space, and the systems controlling magnetic field over the space takes a lot of space. So it was already introduced by Likarev and Fujisawa, single electron devices. And in such case, one small nanowires, metallic nanowires, and the system size can be very small. Just to give you the number, the current CMOS transistors that we are using in this laptop, like here, has 10 nanometers of channel length. And currently, under implementation, there are CMOS transistors with 3 nanometers of channel length. So those devices can be very small. And yeah, so basically, so here we have typical view of okay, just try to plot, okay, try to see the pointer.
On the bottom of the
yes, here, right? Okay.
Yes.
All right, so what we have is typical CMOS transistor. So it has a source and drain, and this channel length is in range of 10 nanometers, or let's say even 2-3 nanometers in most recent technologies. And basically, we can think about change of paradigm. So we can treat source and drain as a quantum dots. So if we inject a single electron to, let's say, source, those quantum dots can be interconnected, are relatively interconnected, and this interconnection is controlled by a gate, potential of the gate that is on the top. So basically, we're dealing with a tunable quantum dot system. So if we inject a single electron to left quantum dot, what will happen? It will oscillate back and forth. There will be characteristic oscillations that will be proportional to, that has frequency proportional to difference of eigenenergies in the system, under the condition that at least 2 levels of eigenenergy are occupied. So, and so this is the so-called Wannier qubit, the qubit that is not right now most dominant, but still right now it's there is a lot of work from Riken, Jülich, and other centers to utilize CMOS technology for the purpose of a quantum computation. So, and then we can use this scheme of 2 single electron lines or 2 qubits for generating the quantum entanglement due to electrostatic interaction. So yeah, so that's how it is, and so this is a scheme that is very favorable for semiconductor industry. So just to give you comparison, one Josephson junction requires at least 1 superconducting or 2 superconducting coherence length. And this is pretty much like 300 nanometers. So we are talking about devices that are principally 2 orders of magnitude smaller. So yes, and then what's physics of Wannier qubit? Obviously, we can deal with Schrödinger equation, wave packets, and so on and so on. But we can reduce this. The most simplified version of this model is tight binding model. It's like the degenerate version of Hubbard model. So so basically, we have occupancy of electron on left and right. So we encode the information in a Wannier functions. The concept which is borrowed from condensed matter physics, maximum localized wave functions. So we are using left and right maximum localized wave function that are orthonormal, and then we encode the information. So this is not encoding in eigenenergy base, but this is encoding in Wannier base. That's why I call it Wannier qubit. So we have a very simplistic model. So let's say, okay, so we have a localized energy on the left quantum dot, on the right quantum dot, and the Hoping constant. And then we can identify very easily the eigenenergies and eigenstates, and so on. So basically, the beauty of this concept is that we can have, so we can everything do in electrostatic way. Of course, we can also use magnetic field and additional degrees of freedom, but we want to skip it. So we want to have a qubit operational at 4 Kelvin. So basically, we have this. We can control the connectivity of a quantum dots by applying special voltage to the gate that is in between. So we can have time-dependent quantum graph, right? So we can inject single electron or single electrons, and we can conduct quantum operations on that. All right. So what I'm going to talk about today, it's quite recent topic of photonics, right? So photonic tight binding model. So the idea is that, yes. So for example, how to deal with quantum communication. So what you need to have is you have okay. So if you subject the, let's say, position-based qubit in proximity to a quantum electromagnetic cavity, that could be, for example, superconducting cavity, what will happen is there will be interaction, like James-Cumming model, right? And there will be entanglement between those two objects that emerges from via interaction. However, if you make 2 holes in a quantum resonant cavity, you can subject this qubit to interaction with resonant cavity and also the second qubit to resonant cavity. So they could become entangled on a distance. So this is also a schema for a quantum communication. All right. So I'm going to talk a little bit on that. All right. So coming back to this Wannier qubits concept. So basically, I mentioned to you that. Okay, we can have 3 gates, voltage gates, for example, controlling the effective potential of 2 quantum dots. So obviously, we can deal with various landscape of potentials, and we can identify various types of eigenstates. As you can see, some of them can be like this one localized on the left quantum dot, second on the right quantum dot. So this is what I was talking to you about before. Okay, and now let us go into slightly more advanced stuff. So this is the case of 2 single electron lines or 2 Wannier qubits interaction. So the most simplistic Hamiltonian is this one basically. So and it has analytical solutions, and then quite naturally we can obtain entanglement. And the interesting thing is that in quantum nature, there's occurrence of anticorrelation and correlation at the same time. That's rather absent in classical picture, because only classical picture will promote only anticorrelation of 2 positions of electrons due to electrostatic repulsion of electrons. All right, let me move on. Okay, so this is again. Now let us move towards this photonic model. So this is the Hamiltonian of a qubit, Hamiltonian of a cavity, and there is qubit-cavity interaction. So this is done by electric dipole generated by position-based qubit. and there's of course electric field. So one needs to know how to quantize so basically, if you deal with a quantum electromagnetic cavity, you have this analogy with a harmonic oscillator. You have a square plus b square the fields sum up into energy. So this is pretty much analogical to harmonic oscillator. All right. So then you obtain very simplistic Hamiltonian for the case of single Van der qubit interaction with a quantum electromagnetic cavity is of that structure finally, and of course you can continue into further generalizations. So now what I want to do is to use instead of so before there was a picture, there was one qubit, a hole in a quantum electromagnetic cavity, and another qubit in a hole. So now I can replace each of these qubits by two single electron lines, and in such case, by interacting them, I can obtain teleportation of a state of, for example, quantum swap gate on the distance, since each of these single electron lines implements a quantum swap gate. So this is pretty much working in this direction. So yeah, we are dealing with slightly more generalized version of previous model. That's still a kind of work in progress. So what I can say is that this model, which I'm describing, is not only describing this quantum communication, but also is being used in so-called geometrical quantum computation. So this is because, maybe I will move back to, so basically if you have such Hamiltonian as here, you can recognize that this is like a quasi-spin Hamiltonian. So in a sense that if you compare with a model of electron in a magnetic field, here we don't have an explicitly magnetic field, nevertheless it's a bit similar. You can have this AP1 equal to minus AP2, so in that sense, this will encode the spin Hamiltonians. So this is quite beauty and power of this electrostatic quantum computation. Okay, and then there is a concept of so if you change the direction of magnetic field in space slowly, so if you have a cycle, under one cycle there is some phase imprint. So you can do the similar thing here. So by cyclic changes of AP2 and these constants, you can have a imprinted phase due to a kind of quasi-spin rotation. And what is important with this concept is that this is, in such case, the qubit is quite resistive against external decoherence. So this actually goes into direction of a geometrical. So this is so having this anti-correlated qubits interacting with a cavity, we can have a system that is less vulnerable to quantum decoherence. So this is essentially the concept of geometrical quantum computation. All right, and maybe very last thing. So we have various possible geometrical topologies of Van der qubits. Here is like open loops, but we can also consider with a closed loops. So what I want to say is that everything is quite much analytical. So we can deal with description of two single electron lines. So one single electron line interacting via quantum electromagnetic cavity with another single electron line. So the model is quite analytical. Well, it's quite spacey. So here what we have is eigenenergies of two single electron lines, and then there is a cavity eigenenergies. So it's lengthy, it's time taking, nevertheless it's analytical. All right. So and of course the presence of decoherence you can account by changing. By going into this tight binding model, so let's say, so you have these eigenenergies, that has real values. If you shift domain from real values into complex domain, you can account for possible quantum decoherence. And also in that case, let's say in a case of Hamiltonian that is coherent, that describes the coherence, you will not have this hermicity property. All right, so I believe I somehow summarize my topic. So basically, so there's a lot of work in progress. One of the aims is to create a Qiskit software for electrostatic quantum computation. So to generate such libraries, and let's say, so everybody knows that the winner in room temperature electronics is semiconductor electronics. So we hope that this approach will also be effective at low temperatures. It's very remarkable that most CMOS transistors maintain its functionality much below 1 Kelvin. This is due to the fact that there is a very big gradient of electric field, and in current CMOS technologies, there is this big gradient of electric field generates carriers. So there's electric field carriers generation that is present. So anyway, that's end of my talk. So there are various publications in press already published. I'm open towards questions. Thank you.
Thank you very much. Have somebody question? Krzysztof? Okay, no questions. Thank you very much for your presentation. And now we try again to have a presentation from Professor Eugen Glushko.
Thank you. Thank you, Chair. Thank you to the organizing committee for opportunity to present photonics subject at this conference, local modes and local resonances in photonic structures. Institute of Semiconductor Physics. My name is Eugene Glushko, and photonics, semiconductor structure photonics department at this institute. So, a short outline of my talk. What is photonics applications? A fabricated sample will be demonstrated, and properties of free diffracted and metallized photonic crystals I want to discuss here, and some applications of this very interesting media and devices. As to the photonic crystals, it's a very widely implemented structures with guiding technology as used as bridges between parts of optoelectronic nets, as in all optical computing structures, as some logic gates, and as lensing, so this very thin flat lenses. As to the applications, I want to point out several promising applications. The first one being collimators in using in siege lights of infrared irradiation and up to terahertz irradiation. So you can see applications based on these photonic structures, as angle and frequency filters, also from visual to terahertz logical elements of all optical computing sensors of movement. So the structure containing defects or thin metallic layer exhibits very thin peaks of transmission, angle and frequency dependent. So the sensors of movement, therefore, metal film with detection in densitometry, so the up to one very sensitive devices can be constructed up to one atomic layer, and terahertz systems of vision using siege lights of terahertz irradiation, and as also means of metrology and sensoring. By the way, this subject was discussed on the NANO-2021 conference in Kiev, and as to the applications, optical metamaterials, one-dimensional, two-dimensional, three-dimensional, very widely discussed in literature and in technologies. Very expressive technologies exist, and one of promising structures in metrology are pneumatic photonic structures. These can unite at a platform several scales of measuring for example, to measure pressure from 1 bar to 1 millibar, one scale from 1 millibar to 1 microbar, and second scale can be inserted in these structures from 1 microbar to 1 nanobar. So these different windows differ with elasticity. In all optical logic gates, two-dimensional photonic structure can be can serve as a logic gate end, and so a combination of this separate logic gate on one platform can serve as a optical adder. So this R scheme, R scheme means that a signal of intensity 2 in logic in digital byte 2 is reflected by a separate logic gate, and application is an optical logical adder, so using nonlinear covering of this structure. So this scheme is is also presented at the previous conferences, and so the signal, a signal of intensity can be 1 or 1 or 2, and then after the passing this system, we have a logical a sequence of signals. So the other based on pure optical qualities. And as to targets, frequency region, this slide represents a structure, photonic terahertz photonic resonator containing defect layers, and this the second this slide is the arrangement of measuring procedure, where the terahertz structure occupies the central point. And as to this, the terahertz or infrared or visual frequency region, it depends on the size of separate layers. So here is presented two double defect containing one-dimensional photonic structure, and in the spectrum calculated by transfer matrix method, gives two panels for this structure. So this silicon 100 microns width, and air 20 air voids 20 micron, 200 microns width. So the spectrum exhibit inside the total internal reflection region very very interesting structure containing local modes with very sharp, very thin transmission in vicinity of this very thin transmission peaks in vicinity of this local mode. So T is transmission equals to 1. R is total reflection, perfect reflection, and for a signal of intensity 2, a signal of intensity 1 is transmitted through the structure, signal of intensity 2 is reflected, and signal of intensity 3 is reflected also. So TRR system, TRR system of logic gate construction can be used in to build an optical adder. Very an optical adder containing very small logical digits, much less than that shown before. So the lower panel represents a reflection map of this structure, and number 1, number 2, number 3, 4. So 4 very thin, very sharp peaks of transmission, which are depending on the frequency and angle. So at the general picture of transmission spikes in interval from 0.256 and 6 terahertz, and for a structure based on the polypropylene area on gold. So then, depending on the gold film thickness, so we have you can see the process of creating very thin peaks of transmission. So with the reflection. So reflection peaks inside the windows of reflection for free photonic structure. It's a very general effect. One more subject in defect-containing structures. It's phase dependencies of the phase dependencies of the field inside the air or gas containing photonic structure. So to beginning on the geometry of the structure, we can build the structure with the field with very useful gradient of field. So this gradient of field can be used in systems of extracting, of dividing different fractions of gas and so on. So that all things I want to show at this conference, and the photonic structures and photonics methods give a very wide perspectives of using in solid state physics and different other different other areas of science. Thank you very much for your attention.
Thank you. Have somebody question to you again? Yes, please.
So thank you for a nice talk. So you have presented the scheme of quantum gates. So the question is, what's the operational temperature for these quantum gates, and what's the time of decoherence that can be observed or predicted in those quantum gates?
No, that was not quantum gates, but logic gates, and the coherence is very high here, and which can be reached by usual pulses of optical laser sources.
So only logical gates, not quantum gates, right?
Not, of course. This the discussed subject is all optical signal processing, and of course, quantum the all optical computing promises the velocity, the frequencies of and the velocities much larger than electronic and optoelectronic, and therefore they should occupy a place between quantum computing and today's electron and optoelectronic computing. Thank you.
Thank you. One more question? No questions. Thank you very much again.
Thank you very much for your attention.
Шановні колеги, тут така поступила пропозиція, що ми завжди робимо конференційне фото на початку першого дня, і були образи, що дехто приїжджає в другий, в третій день. Тому давайте просто повторимо, ну не повторимо, да, а зробимо конференційне сьогоднішнє таке заключне фото. Зараз я прошу там, це остання, правильно, доповідь була?
Yes.
Тобто я запрошую всіх в хол, ми зараз зробимо фото для тих, хто приїхали в другий і в третій день. Дякую. Sorry, now we will do a conference photo. So I invite you to hall.
Start our next session, and we invite Yulia Mucha from Chuikoy Institute of Surface Chemistry with presentation formation of gold colloids with tunable size of nanoparticles. Please.
Thank you for kind invitation. This work was done in collaboration with three organizations: Institute of High Technologies from Taras Shevchenko University, Lashkarov Institute of Semiconductor Physics, and also my institute, Chuikoy Institute of Surface Chemistry. And it was supported by National Research Foundation of Ukraine, and deals with gold nanoparticles that find very wide use in nowadays nanotechnologies, especially in biomedicine, in such directions like sensing, imaging, drug delivery, and therapy of different disease. And efficiency of these nanoparticles in such processes strongly depends on the size and shape of nanoparticles. And if we talk about colloidal solutions, also it's very important to consider their stability, because different processes like interaction between nanoparticles, association and aggregation can greatly affect on them. And among known methods, while electron microscopy can measure accurate size and shape of nanoparticles, size distribution of nanoparticles can be observed by dynamic scattering data. And these are three main methods to study nanoparticles in colloids. Electron microscopy, DLS, and also UV spectroscopy with the main characteristic of nanoparticles, the band of localized surface plasmon resonance absorption. And also almost everybody here know that the position of the maximum of this band is size sensitive, and any features about shape and distribution is long wavelength region. And I would like to point on the dynamic scattering method, as it is very important, and exactly this method allows us to predict the stability of the colloids and adjust the size in the synthetic procedure, because it shows three bases, three canals of information. There's a number, distribution by volume of in the whole system, and also intensity of scattering of these nanoparticles. And every basis, every data from collected should be analyzed in detail to predict the processes of stability of the colloids and so on. And even such very known method like Turkevich method or Sight-Right method to obtain gold nanoparticles is very challenging sometimes, because every experimental feature play a great role in the whole system, like ratio of reagents, concentration, temperature of reaction, and duration of heating as well, order of the reagents. So this work is focused. And this work is focused on the colloids obtained from Sight-Right method, considering every experimental parameters and the effect on the properties of whole system. Starting from the previous picture, this is dependence of the size distribution of gold nanoparticles from boiling duration. What does it mean? It is known that when we want to have these nanoparticles with Sight-Right method, we should boil it. And duration of boiling, like 3 minutes and 30 minutes, play a crucial role, because if we heat too much, in the distribution by intensity basis, we see that a great fraction of aggregated nanoparticles, it rise, while the average size stays at between 10 and 20 nanometers. And so we can conclude that prolonged heating causes more intensity aggregation of previously formed nanoparticles, and the stability lost. When we consider heating temperature, it also plays a crucial role. For example, using 55 degrees and also classical 100 degrees, we can see the great difference between these two samples. For example, when we lower the temperature, the fraction of small nanoparticles is formed. Maybe it's not reduced, all the ions. And in the intensity basis, we see that the fraction of bigger aggregates more than we have before. And we can conclude that lower temperature is not enough to activate rapid reaction of the reduction of gold ions. And in the result, it causes total aggregation of nanoparticles in time. So we see the blue power on the bottom on the flask. Next one, ratio of reagents. Ratio is usually known fact to affect the size of nanoparticles. But we see in this system, the dependence is not linear. We have a correlation between localized surface plasmon resonant band with DLS data. For example, the most shifted position that is usually caused by the bigger size really shows the bigger size in this distribution. But we can not just simple to fix every step of the sizes. So it's not so easy to get it. The bigger shift, the larger nanoparticles, yes, but it's not so. It's very challenging to get different size, like 5 nanometers or 60 nanometers, and so on. And also, we studied that more concentrated colloids, like usually used concentration like 3 and 10 in -4 molar concentration, it cause not larger particles, but larger fraction of aggregated nanoparticles. And also, in the future, it aggregates, it decreases its stability. One more, among known mechanism for such system, mechanism of formation of nanoparticles, include such steps like nanoclusters, formation of nanoclusters less than 5 nanometers, then formation the networks of nanowires built from these clusters, and reduced reduced metals, ions, and further the fragmentation and further rippling. And this transformation usually is seen like the very sharp change in color from blue to red. And from our data, we can say that if the ratio between components is too small, we can stop at this stage. When the temperature is too small, we can stop this, but we should reach this step. And also from our data, we have known that there is one more stage. When it's too long heating, we can stop here. But also, we can affect the whole system on this stage, and mainly this is because of the pH of the solution. For example, when we use high pH, the reaction could be very, could be very slowed, maybe. And upper line indicate the characteristic of nanoparticles in colloid just after the synthesis, and this line is the same colloid in a week after synthesis. And we can see that the intensity of localized surface plasmon band, it rises in a week, and the average size goes to 20 nanometers against less than 5 in that moment. And also very interesting fact that some fraction of small nanoparticles and aggregated nanoparticles that is related with this networks of nanovirus, they escape in a week. So increasing the pH, we can slow down the nanoparticle formation, and this continuous growth, this proceeds through the Ostwald ripening. Also, it's very important to consider the way to inject the reagents in the reaction, the order, especially in high pH. For example, here we see the difference between the same system when the gold was added to the citride and vice versa when the citride was added to the gold. And we see the great difference also in the optical spectra and the distribution by intensity, just because at high pH, this reagent, this is a complex structure of the gold, it can form hydroxy complexes with tight binding between ligand and the metal, so it's much more harder to activate the reaction. So also this should be considered when we obtain the nanoparticles. And for such molecules, small molecules that can play the role of reducer of ions and stabilization for nanoparticles, pH play a great role. For example, in the system with tryptophan, there is a great difference. For example, for pH 2 and 6, we can estimate the kinetic parameters for that process, analyzing the rise of the intensity of the band of localized surface plasmon resonance. And in this case, the process can be analyzed by a sigmoidal function, and for 10 pH, high pH, it's better to analyze with exponential function, and it means that with different concentration of hydroxy ions, there is a different stage that plays a key role. For example, for high pH, the main reaction is a reduction of metal ions, and for neutral pH, it's formation of new phases after the reduction. And as a conclusion, we can say that mechanism of this particle growth in this system goes through the formation of nanovirus, and depending on the parameter, that nanovirus can be fragmented or separated, fragmented to form stable colloids of nanoparticles, or interact between themselves and aggregate. And experimental parameters that greatly affect the size distribution is the most important parameter is pH, because it influences the rate of reaction through the forming protonated or deprotonated form of such molecules and the hydroxy complexes of gold. And just changing the ratio of components, it's not enough to get different size, because we should consider that the same molecule plays 3 roles, like reduction of ions and binding to the gold nanoparticle surfaces, and also it should form the charge of the whole nanoparticles. So it's much more easier to get some or use some additional reducer. And when we use sodium borohydride, we can reach in a reproducible way 2 different sizes. For example, it's 5 and 20 nanometers. That is shown from wall. This methods like optical spectroscopy and DLS measurements, and also electron microscopy. So thank you for your attention.
Thank you. Have somebody question? Yes, please. There is Tamara with the microphone.
I can hear you.
Okay. My question about Oswald repelling. Usually it's two-way for such process. It's growth of particle or partial dissolution of small particle and recrystallization from solution into large particle.
Yes.
Which way can realize in your case?
If we talk about classical method, this is the second one, when they dissolute and then go to the surface. When we use high pH, it's rather reduction of ions on the surface of nanoparticles.
And second question, what about crystallinity of such nanoparticles? Have you some data about X-ray diffraction for film which can prepare for such?
On the surface?
Yes, some surface.
No, for that moment we didn't study. But maybe classical.
It's crystalline or?
Yes, of course it's crystalline.
Thank you. Have somebody more question? No. Okay, then I have a question. Yes, I have a question.
Okay, sorry.
You have told about low stability and aggregation of your particles. Do you use some emulsifiers for stabilization of colloids?
Emulsifiers? What do you mean?
Tenzit?
No, just we can correlate the stability with pH, and because of the pH, the molecule go to the deprotonated form, and it provides the charge of the nanoparticle near 30 millivolt. Through the zeta potential is near the 30, so they don't aggregate when interact. They just have repulsion between nanoparticles.
Okay.
So no other.
No other emulsifiers. Thank you.
And we have one question from YouTube channel. Do you have experiment with biological object? How do you solve the project of delivery of gold nanoparticles and the ERTEC system?
Okay, we have, and usually when we work with mouse, for example, just the right injection, but also we can synthesize magnetoplasmonic nanoparticles and apply magnetic field to reach the special place in the body.
Okay, thank you for your answer.
Thank you. With pleasure, I will invite next presenter, Adrian Augustiniak, West Pomeranian University of Technology in Szczecin, Poland. Pseudomonas aeruginosa and its reaction to sublethal concentration of carbon nanomaterials. Please.
Good day to all of you. My name is Adrian Augustiniak. I currently realize my postdoctoral research at West Pomeranian University of Technology in Szczecin and partially at Technische Universität in Berlin. I'm always happy to be at the Nano conference. I also thank you for the opportunity to have this talk. And it will be a bit different. I'm always happy to see that some studies with nanomaterials are being done on biological environments and with bacteria, for example. And I'd like to show you some cases when nanomaterials may not be as bacteriostatic or antibacterial as we want them to be. And even more, sometimes the bacterium can fight back. Usually it will be when the nanomaterial is not given to the bacteria in the ideal state or in the ideal environment, and in the environment that will be favoring bacteria, because if bacteria can fight back, probably it will. That's why the subject of the study is Pseudomonas aeruginosa and its reaction to sublethal concentration of carbon nanomaterials. What we already know about nanomaterials, of course, they can be antibacterial. There's no doubt about it. They can be antibacterial, they can cause some leakage of cytoplasm, they can cause membrane stress, they can interact physically, chemically, they can cause oxidative stress to bacteria, but sometimes we see that the effect is only bacteriostatic, so bacteria is alive, still is alive, and it will get favorable conditions, it will grow back. And even there are some works, and this is our main interest, not to study only toxicity, but sometimes, in some cases, maybe study stimulation of bacteria by nanomaterials. It's completely different, it's opposite direction to what is being done usually in these studies. Of course, there are some mechanisms, for example, with graphene oxide, basically if the material can basically cut, for example, through the bacterial membranes. And of course, what can it cause? It can cause some proteins dysfunction, usually through reactive oxygen species that arise in bacteria. And of course, it can lead to some mutations because of the genotoxicity, for example. There are at least several different ways of work for these materials. But as I said, bacteria can protect itself sometimes. So for example, here it's shown maybe not in these bigger materials like carbon nanotubes, but usually on nanoparticles. But in some of the cases, I will show you that it may be quite similar. So they can change efflux, for example, they can sequestrate these materials around them, sometimes between the membrane and the cell wall. They can reduce uptake, they can change the metabolism, they can make some bypasses to survive in the environment. And that's why the aim of the study included Pseudomonas aeruginosa and included carbon nanomaterials. Pseudomonas aeruginosa, why this bacterium? Because it's phylogenetically is quite old. It has many different mechanisms to protect itself. It can be found, for example, in the soaps in hospitals that contain alcohol and glycerol because it likes it, so to say. This bacterium, as I'll show you, has some interesting features when it comes to contact with nanomaterials. And the nanomaterials that were used in these studies were carbon nanotubes with copper nanoparticles, graphene oxide flakes, and some graphene oxide flakes with cobalt nanoparticles. Unfortunately, I will not be able to say much more about nanomaterials because I'm the biology guy in the team, but of course you can check our publications or speak about it. It's quite agglomerated, I know that. I see it in your reactions. The methods that we are using mainly are culture methods, spectrophotometry, some microscopy, flow cytometry, and of course we do many repetitions because of the carbon materials. They change optical density and optical features of the media, so we do a lot of repetitions to get some answers, and of course for that we need statistical analysis to compare them. And just to see, of course, these are only microscopic slides, so we could choose, right, what we see here, but usually in physiological conditions the bacterium looks more or less like this. But we can see, for example, here and here that not only agglomeration is being done, especially agglomeration here and here, some of the cells are being just destroyed, especially when we had copper nanoparticles, it was the case. And here, basically, more or less ideal conditions, so bacteria does not have any means to defend itself. It's in deionized water. similar to nanomaterial. The nanomaterials were not stabilized with anything. Yeah? So because we wanted to have it not ideal, and this was deliberate from us. But basically we see that if the conditions are good, especially with materials that have these particles, metallic particles, and graphene oxide, the reduction was there, but bacteria was not killed entirely. What we can see from flow cytometry analysis was that especially with this nanomaterial with copper, maybe I should show you that this is the population. Yeah, so this is the population of either one strain or two strains, because I haven't said that we also used to do it more tricky. The same bacterium but two different strains, and they behave differently. So this is the bacterium, the population, and from the fingerprint we can see that especially when copper was there, here we see that something was building, and this is basically a debris. Cells were just being destroyed, completely destroyed, which wasn't the case. For example, with this carbon, let's say, graphene that we used. And here, what happened about 24 hours, but in the case where bacteria got their environment to grow. So nanomaterial, of course, we know that there were some problems, of course, with agglomerating of nanomaterial. We've been there. But what we can see is that not only the bacterium usually is not killed, except of these, but sometimes the reaction is that it even grows more, especially with carbon nanotubes. And here we can see by fluorescence we can see the viability, the respiration of cells afterwards, and in this material it skyrocketed up high. Which means that if we create the environment for bacterium, sometimes it may fight back. And here, there was 24 hours. After 24 hours, we did some tests. Here, the tests include some more physiological features. The results were partially done by my new PhD student, Kamila Dubrowska. And here we included measurement after 6 hours, 12 hours, and 24 hours. You can already see that some of the results look quite a bit different than the previous one. Especially here. Yeah, for example, when we see the fluorescence, yeah. So when we increase the concentration, the fluorescence went back, which means it stopped producing pigments. Here, the fluorescence is the pigment production, which wasn't the case, for example, here. With this nanomaterial, in some cases, it was producing more pigment, which means that it may produce, for example, more pyacyanin, which is a virulence factor, which is not good, for example, if you wanted to use these materials for some medical applications. And what's important here and with this material, when we repeated it with some more repetitions, yeah, we got quite high excess of biomass in our cases. And here I'd like to show you something that is quite interesting. That even though we could see that some of the bacteria are being killed, and the biomass sometimes, of course, were lower, which we could see, especially in 6 hours here. Yeah, that for the first 6 hours it was inhibited. Yeah. So what is interesting here? It was inhibited, but later on, after 24 hours, we see that it's very close to the control. So the population basically went back to where it belonged. Why it happened? We hypothesized that when the excess of biomass is appearing in the system, then basically it covers all of the material. It may, of course, agglomerate it and agglomerate together with nanomaterial because this one also produced biofilm. And then basically it cuts off the material from the environment, which of course allows it to grow then. And here one of the most interesting results that we have on this stage is that basically control is here. Then after the test we try to see what will be the dynamics of this respiration that we measure within Alamar Blue tests. And we can see that in the control, here is the control on this one, in the control is quite worse than the rest of them. So where the when the nanomaterial were, we have basically higher respiration rate that we had in the controls, except of that one, because probably here the concentration was way too high for the bacterium to maintain its respiration rate. So to conclude, the physiological reaction on the bacterial model depends on the nanomaterial, of course, on the concentration. We know also it depends, of course, on the dispersion of material. With these, we had a lot of problems. The sublethal doses of nanomaterials can produce a stimulative environment to enhance, of course, in given conditions. I would like to express that clearly. Environment to enhance the growth rate of studied bacteria, viability, pigment production sometimes, and biofilm formation can be affected. Basically, the bacterium may use material as a scaffold sometimes for the biofilm production. Of course, tracking these changes in physiology, we feel that it's quite important, especially for the biomedical applications of nanomaterials and maybe some environmental ones, because there the interaction between the cells and materials is quite extensive. So the tracking changes in physiology is crucial, and we should go deeper into this direction. Of course, I'd like to thank all of my co-authors, including Asia Jabłońska, who is also participating in the conference with us, my new PhD student Kamila Dubrowska, Paweł Sikora, my great friend who introduced me to this conference, for which I'm very grateful, Krzysztof Sendrowski, who is our nanomaterials guy. So if you want to know more about these nanomaterials that I show, this is the guy to talk to. Bartłomiej Grigorcevich, a genius in the lab. I can ask him for everything if I don't know something. Paweł Nawrotek, my promoter from PhD studies, and Rafał Rakoczy, our professor in the lab that I work in Szczecin right now, who is giving me a great opportunities to develop on these topics. Thank you very much for your attention. If you have any questions, then I'll be happy to answer.
Thank you. Have somebody question, please.
Thank you for your talk. The question is, how big is your materials, or are your materials, compared to the bacteria cell, and how they go inside the cell, the mechanism, maybe some ideas?
Well, if they even go inside, they have to do it mechanically, because it's in comparison to bacteria. Of course, the agglomerates were bigger than bacterial cells. Yeah, we could see it there, for example. So here we can see some agglomerates. Here we can see an agglomerate. Of course, it's a lot bigger. Yeah, but still, when we did during my PhD studies some TEM analysis, of course, nanomaterial was also in the nanoform, and then single plates were, of course, smaller than bacteria.
So maybe the first stage, just the maybe changing the membrane, interrupt the membrane. It's not idea, just asking.
Yeah, for sure. But as we could see, this interruption was ongoing mostly when nanoparticles, metallic nanoparticles, were there.
So what we could see here. Yes. They don't destruct the membrane, they go inside.
No, probably not. Here more from these ones, I would say that the nanomaterials did something like this, trapping. Yeah. So because the results show that rather it was trapping and covering between the nanomaterials and cells than disrupting the cells. Yeah. Except of this copper materials, which we could see that really there was something, because the cells on flow cytometry, the cells were just destroyed. Yeah.
Next question, please.
Thank you for your presentation. Actually, I would like to ask you if I understood it right. You said one of the conclusions was that nanomaterials can enhance the bioproductivity of the bacterial population. What is the main, well, I forgot the right word.
Reason?
Yes. What is the main reason for this? Is it just a normal physiological reaction of bacteria?
That's a great question. That's a great question, because one of the mechanisms may be that they are scaffolding on material. Yeah. So the agglomeration comes and nanomaterial stops being nanomaterial, in fact, and then the agglomeration comes. But we know perfectly that nanomaterials can cause oxidative stress. And there is a work, I have it cited somewhere, here by Professor Lemire and his co-authors, which shows that sometimes with this oxidative stress that they can have, it may stimulate them. Because, and we can see it from the fluorescence was in Alamar blue test, which is dependent on the respiration. And this particular component is being transformed by a reductase which is NADPH dependent, and this is the one that is produced more once bacteria have this oxidative stress. So basically, it's not like if they have oxidative stress they will die right away. Yeah, they have mechanisms to defend themselves, and sometimes, as Professor Lemire shows, they can even produce some more biomass, some ATP. They can produce so energy from the excess of this oxidative stress, which is, I think, very important, especially for biomedical applications.
No more question?
How you control purity of your nanomaterials?
Well, the nanomaterials that I showed are produced in the nanomaterials department. So basically,
very interesting.
Yeah.
Because what I want to ask you, you use different technological process for fabrication, and maybe present contamination after fabrication, which influence on the result.
Well, what I can say...
I use washing procedure for pretreatment.
Yeah, they are washed, and what you could see, for example, here we had these materials. Yeah, this is basically the same material, because I don't understand it fully, but it was metallic organic framework. Yeah, that's why cobalt we have. And for example, this one, this doesn't have cobalt because it was washed from the material. Yeah, and here the cobalt is at the surface because it stayed. Yeah, so I know that my colleagues are doing some procedures to clean them up, but you should speak more with them to get a better know how they do it.
One more question? Okay, I have a question.
Yep.
In our institute, we developed antibacterial coatings with graphene oxide, for example, for hospitals, for different high traffic surfaces. Which maximal concentration of graphene oxide that we have antibacterial properties? Can you prognose?
Well, it's very tough to answer because we could see also in the results that the concentration is not always the thing that is important, because at some concentrations, especially the highest ones, the nanomaterial may stop being a nanomaterial because it's just being stacked. Yeah, and it's very hard to tell about the concentration because, as I showed here, we had Pseudomonas aeruginosa and Pseudomonas aeruginosa, and they already behave differently to the to the nanomaterials. So I wouldn't risk naming a number, a concentration, especially that, of course, graphene oxide and graphene oxide also can be different materials.
Yes, it depends from producer.
Yeah.
Okay. Thank you.
But of course, I invite you to speak more. Yeah, we can also discuss it after the session.
In general, when we produce coatings, it's a hard system, then we cannot mix very high concentration of nanomaterials because we have very high viscosity. It is not processable. But maximal nano very good when we have very small amount.
The problem with nanomaterials that I see in the lab all the times is usually that if it's new and before it's covered in some biomass, it's okay. It's antibacterial, it works. But once the biological surface is being formed, basically it protects the rest of them. And that's also something that we've observed.
Thank you. No more questions? Okay, with pleasure I invite Dr. Ruslan Marichuk from University of Prešov, Slovakia, with his presentation, Photosynthesis of irregularly shaped gold nanoparticles, peculiarities, challenges, and future perspectives.
Thank you for introduction. Good afternoon, ladies and gentlemen. Thank you for the opportunity to present some recent results and actually introduce our project to society with hope for some cooperation, for some contacts. I represent the Department of Ecology, so I will dilute your very physical society and maybe chemical, so my results will be represented a little bit in a different way. It's not perfect as wet chemistry can do or as physics can measure, but it's real objects as cheap, easy available projects. They are not perfect. We try to learn how far we can go with them as it is. And generally, the idea is as development of green methods. I mean, without using of some toxic compounds, without using of toxic surfactants mostly or reducing agents, and in the same time we have to fix the most important parameters, like we have to be able to control the size and shape of resulting nanoparticles, and to be able to prepare the stable nanocolloid solutions. In the same time, if we talk about green, it's normally we're thinking about low price. It's connected with availability of material, and to this preparation expected to be friendly to environment. But it's not all. Our next point, is important point for application, is to make these nanoparticles biocompatible. That's very important, and it's connected with previous aims, because we normally study the medical plants actually as source material, and we expect the final product cannot be toxic or expected to be not toxic in general. And by requirements of people from medicine, we are mostly interested in objects which shows a response in near infrared range. So in this case, it's application for different kind of hypothermia or bioimaging, but to have response in infrared range. Generally, the optical properties, here of course we're thinking about the surface plasmon resonance phenomena with nanoparticles. This surface plasmon resonance band can be managed with size, but for example, in this case, the shiftment is small, relatively small. I mean, this is just shift of size. Normally, if you're thinking about the introduction of the nanoparticle into the cell, we have to think about relatively small nanoparticles. By some criteria, it's expected to be smaller as 60 nanometers. If it's larger, then there is a problem through that this nanoparticles can enter into the cell, and then this effect is lower, expected effect is lower. However, more achievements can be received if you manage the shape of the nanoparticle. In this picture, I show it as from quite old publication, but it shows you that when size of nanoparticle is approximately the same, but the shape influences the position of this gap, and from this case you can see that actually the same non-spherical nanoparticle will absorb, this absorbance will be in infrared range, so there is a chance actually to manage with this. What is one of the main criteria for this? Because we have different shaped nanoparticles, there is plenty of different kind of shapes like stars, triangles, hexagons, cubes, and so on. The one of criteria which is normally accepted in this case is this called aspect ratio. It's like ratio between length and width. This unsphericity, let's say, and this influences properties. And if we move to application in medicine, there is a statement about existence of so-called therapeutic window when actually organic matter is transparent for infrared range, especially in range between 650 nanometers till 1250. So the top is limited with strong absorbance of water, so it's why it's not possible to go there if you work with water solution. However, these two windows, the people from medicine also divide them, split them into first and second window, which have own advantages and disadvantages because the energy of infrared radiation here is higher here, but penetration depth is lower, and in opposite case, the second window is more preferable. So, and here I just put some simulated UV spectrum of gold nanoparticles, spherical, purely spherical nanoparticles. You can see that we actually mostly out of this range. The physicians also describe some second and third and other harmonics which produce some absorbance, but normally in real spectrum we cannot see it or almost cannot see it. So in this case, I just want to show that, for example, this perfect case when we have different aspect ratio, and we can see that how this shift can be, this red shift stronger when you have higher aspect ratio. Of course, modern wet chemistry have developed a huge amount of different protocols for preparation of non-spherical nanoparticles, and some of them collected in this picture. That's starting from spherical, you can see nanorods. You can see nanoshells, nanostars, nanocubes, and other shapes, and it's not a complete list of this. And if you look on these protocols, they are always the most successful protocols and most reproducible and trustable protocols. Unfortunately, always contain something toxic. It just happens that you need or reduction agent or mostly the surfactants, the capping agent. They are always toxic, and then there is a huge problem for biocompatibility, because I remind you that this nanocolloid system, it contains metal, nanoparticles, and organic environment which stabilizes the system. And sometimes this organic environment defines the toxicity of the final product. It's something what we would like to manage, what we would like to avoid. And I concentrated on photosynthesis. I told in the beginning that actually we try to use easy available medical plants with hope that final product will be toxic. From first point of view, it looks simple, and actually it's well known. I think the first synthesis were described by Faraday in 19th century. He prepared the silver nanoparticles. He knew that it's nanoparticles, and the second brief came when human came to this nanovolt. And from first point of view, it looks very simple. You cook the tea, just you prepare the normal extract, then you add some source of metal, And then you have bioreduction, you have reduction of bioorganic molecules, and finally, if you have correct ratio, concentrations, temperature, pH, and another plenty of parameters, if you're lucky, of course, because sometimes I'm kidding that even weather in New York influences synthesis, if you do it here, so many factors affecting, and then you actually have particles. Here is huge area with management because it needed a lot of experiments to find the right conditions, but if you find them, then you can have some interesting results. I just want to show this. This is a number of publications in Scopus database, and you can see that at the moment there are over 4,000 publications in the last years which related to photosynthesis in general. You can imagine how many publications which are not cited in Scopus, because there are a lot of information, sometimes, not sometimes, often very contradictory because of different preparation of extracts, different conditions for synthesis, different access to devices, to characterization, and as a result, different interpretation of results. So here's a field where we have house in information, and it's complicated to find some what is true and what is just accident and what is all. It raises some very common, it's only few of them, the plants which we use it, and for example, just typical synthesis can be in non-ideal systems that actually we have some spherical nanoparticles. If it's a mixture, if extract is a complicated mixture of different organics, it's complicated to manage with size. But it's how it can look. In this case, it's simple but quite boring because of spherical. But sometimes you can have systems where you have different shape nanoparticles. It depends from this extract system. Heavily depends from this. And here, even our attempt to separate one extract on different fraction by different criteria, you can see that from parts of the same extract, you can receive different result. So where we move deeper, so one of interesting results was received, is we used invasive plant, which is easily available, unfortunately, everywhere, because it's why it's called invasive. And here is a possibility actually to receive the materials with absorbance in infrared range. And here I just want to show that it can be even managed if you fix the most of parameters, because we invest a lot of time to study the extract before the synthesis to manage with this. For example, this picture here, the idea is that if you change the ratio between components, you can shift the maximum of the absorption. So we still have, unfortunately, the spherical nanoparticles. We have a big fraction of non-spherical particles which are absorbed in the slide. Normally, this, the dominant non-spherical nanoparticles, nanotriangles, very thin. It's 3-4 nanometers, and it arises the expected radio for this material. Only the point which had to be controlled, it's size by different reason, and then it's managed with this size. And so here, maybe you can see better how huge this mixture. Of course, by variety of different parameters, you can increase the fraction of non-spherical particle or decrease, but unfortunately, we always have all of them. Maybe we studied it better for a system with peppermint, where we can actually clearly see that with increase of the initial content of gold, we have increasing the size of spherical nanoparticles, but here we can influence actually the position of this maximum, and we can find the optimal conditions, and then these nanoparticles need to be separated from this massive solution, and then actually this property is going to be more stable. In this case, what I can just show, we started the test. I cannot present it here because it's not published yet, but we started some tests where we consider different systems, which you can see actually perfectly sits with these windows. Of course, this actually, for this case, I can tell that it's dominantly triangles, and in this maximum second window is dominantly hexagons. And of course, size is important, so there are still a lot of limitations, but we are moving in direction of the test of photothermal phenomena and these samples, and previous tests looks very interesting, looks perspective. And so here I just want to show that depending from the extraction system, the increase of the gold content, you can have actually two different cases. First one, you just have higher concentration of gold nanoparticles, spherical nanoparticles, or if correct system, then you actually, with increase of gold content, you have shift of second peak, and you can stop it wherever you want if necessary. For this case, actually, after testing of different extracts, I was really surprised that for some system we can have almost ideal spherical nanoparticles. Just for real system, it's almost impossible. And on this picture, you can see we use elderberry and from left side silver nanoparticles and gold nanoparticles. Of course, gold is always more grateful reactant. It's easier to work with gold as is with silver. And one would ask why I show it here, because it's only spherical. But there is other possible application. So it's another case. Clove oil, sorry, it's still spherical nanoparticles, but this case is special because of clove oil as natural object, expecting to be mixture, but clove oil, it's on 75% is one compound eugenol. That's why it's interesting, because you take natural object, almost pure. This is a very simple purification, but still, unfortunately, in very spherical, but then we can go deeper into the science to understand what's going on if we have only one natural molecule, and we can make some simulations to understand better what's going on. However, how it can be used, how spherical nanoparticles will, it's as a part of our project. We start from silver nanoparticles. We use galvanic exchange with aim to obtain hollow silver nanoparticles, which actually can be used, for example, for drug delivery systems. And so here our colleagues from Institute of Physics in Kyiv, they actually started to do this chemically synthesized, traditionally chemically synthesized, and just give you an idea, and we received a very interesting result with green spherical nanoparticles, starting from green spherical silver nanoparticles, moving in direction of empty hollow silver nanoshells, which shows absorption maximum in second therapeutic window, what is actually much better, as you see it on this picture for classical synthesis. And I would like to say thank you to my colleagues from my university who work hard in this direction, and colleagues from Kyiv National University, Taras Shevchenko, and colleagues from Institute of Semiconductor Physics, and for support from Ministry of Education for a project which is run now actually in this direction, in green preparation of nanoparticles with response in infrared range. And of course, thank you very much for your attention.
Thank you. Has somebody question? Please.
Thank you very much for your presentation. I would like to ask you about 2D nanoparticles, which you show, and like a triangle, like.
And hexagons. Yeah.
Yes, hexagons. Tell me, please, about I see polydisperse.
Yeah.
Yes, polydisperse. How you solve the problem of polydispersity? Because probably you achieve absorbance spectra with different maximum, and I think that 2D flat nanoparticles have absorbance in near infrared region of spectra. And if you told before that you are interested in reaching a therapeutic window. So nanoparticles will absorb in near infrared region. So a flat nanoparticle has such absorbance. And how to separate these flat nanoparticles, 2D nanoparticles, from the spherical nanoparticles? Which way of separation?
Okay, thank you. Yeah, that's actually the key question for this project for next steps. What we do is, the separation is complicated. For example, the easiest separation will be centrifugation, but it doesn't work because of it's fixed, it's connected with the weight of nanoparticles and not with the shape. There are many ideas in literature that people modify the surface, and then when you modify the surface, you make some of them heavier, some of them lighter, and then you can separate them. And the membranes are involved, but generally it's a quite complicated question. But when I talk with physicians and people to medicine, they tell me that maybe it's not necessary. You have huge adsorbents in a correct way, and if you use a standard medical laser, for example, with 809 nanometers, and if you have huge adsorbents here, who cares what's going on in other range? So it's interesting. We would like to do it. We do some first attempts, but it still doesn't work. But there's also hope that we can use them as it is. Because actually, as I told, that actually, if it absorbs here, huge absorbance, maybe it's not a problem that it's not absorbs in other range.
One more question, please.
About the same nanoparticles, they are big but very thin, and even if we don't have to use centrifugation because they aggregate, how do you prevent the interaction in the initial colloid? They, like a plate, they can aggregate.
Okay, the simplest way, just centrifugation and remove them from the initial solution and dilute it, for example, in distillated water. We will have all of them together, but separated from the solution.
I don't mean the separation, but the interaction between each other, between all these big nanoparticles.
Okay,
because they interact like a plate, you know.
Okay.
Usually on TEM images, they are very packed, very close packing.
No, I cannot answer it because we didn't study this, and I wouldn't trust the TEM images for this point because, you know, a TEM image is made for heavily treated sample already. So it's not like it's in solution, and it's way...
Okay, and one more question about...
It was dried.
Yes, thank you. About the experimental procedure to estimate the toxicity of the products.
Okay, so we deliver it to actually microbiologists who test it. But I immediately can tell because we work with silver and with gold. And with silver, they can find something, and with gold, they always answer there is nothing. Nothing to show, actually. And it's good news for us.
No more questions? I have a question. How high is your reproducibility by the synthesis? Because bio-based materials is always
always different.
Always different. Yeah, you cannot be sure that you have in this batch 25.00% of organole or other components.
Yeah. So initially, I also worried about this because even you cannot prepare. Everyone knows that you cannot cook the same tea twice because it always will be different. I mean, in half an hour you do the same, but it will be a little bit different. And in this case, if you prepare as extract different types, if you take another portion of plant material from another place, from another drugstore, or something like this, it can be different. But we even go deeper. We tried the different strategies for preparation of extracts, and then deeply studied the difference between them. And you're right. In some cases, actually, if we compare the composition of extract prepared, for example, in traditional tea cooking, I mean 100 degrees. And sometimes we use lower temperature just to keep the thermally unstable compounds inside. So we use the lowest like 60 degrees. We cannot go lower because there is no extraction, and we can go higher because we will destroy some compounds. If you compare, in some cases it's heavily different. In some cases there is no difference. Another point is that generally extract is it's very seldom that there is dominant product. If you compare, if you just look on the chromatogram, you will have very low intensive peaks, but thousands of them. And sometimes difference between these compounds, it just like isomers, where you have same functional groups located in different sites. And in objects what we are studying, the reproducibility is very high. I think it's because of if you have different isomers of the same compound, this influence on reaction is minimal. There are definitely some influence, but it's quite low. For some systems, if we prepare extracts in different way, we see, for example, we still have this non-spherical nanoparticles, but in some, for example, if extract prepared with ethanol extract, ethanol water, aqueous ethanol, and then ethanol removed, then the reaction finishes in 7 minutes. And if you take just water extract, normal water extract, it takes 2 hours or 24 hours. But normally the result is the same, approximately the same. So yeah, it's a very complicated problem, but there is hope to manage with this. I cannot explain you in details because it's why I told if it's in this case I'm just kidding that if it works then it's in industry, if it's complicated then it's in science. So and this is a science.
Thank you. I invite Dr. Marusek to to stay here and make moderation of next section. Thank you very much.
Ladies and gentlemen, we start the next section, which is entitled Nanostructured Surfaces. And my pleasure to invite Dr. Oksana Koplak from Institute of Problems of Chemical Physics, Russian Academy of Science. The presentation entitled Laser Modulation of Amorphous Praseodymium Dysprosium Iron Cobalt Borate Microwires. It's online, so let's contact with our presenter. Our presenter is here. Good afternoon, Oksana.
Yes.
You hear
us?
Me? Okay. So who shares the presentation? Yeah, you share. Okay. So the floor is yours.
Okay. Thank you very much. Good afternoon, dear colleagues. I think that you're so happy to be in this very beautiful place and very beautiful city. Unfortunately, I can use now just online this modern opportunity by Zoom. So let's start. The title of my report is Laser Modulation of Amorphous Microwires. This is a very complicated composition, consists of 2 metals, rare earths and transition metals. Let's continue. First of all, I would like to remind you that laser-based processing has been widely used for creation of functional device. Laser radiation can be used as source of ablation, annealing, patterning, crystal growth, etc. As you can see on this sketch. Main idea to use laser heat for transformation from amorphous state to crystalline. Very simple, yes? But selective laser melting. It is a very accurate method, also known as additive manufacturing technology, has already been used to print permanent magnet of very fine macrostructure with programmable shape and stable magnetization. So what is this? It's a 3D micromagnet printing technique. The fully magnetic 3D printed magnets basically allow one to develop technology of micro and nanomagnets necessary in medical and biological application. As you can see this example from Nature journal, these people create some micro robots, magnetic micro robots that can be transport cell, drugs or genes due to the magnetic field. So magnetic field propel and direct to the helix, and these micro robots can move in human body. So it's very, very, it's fantastic. It's fantastic when science goes to the human body. But question is which materials we can use, we should use. One of the magnetic materials, it's famous magnetic materials with a very high coercitivity field, it's permanent magnets. And well known, the magnets with composition neodymium iron boron, the phase 241, very famous phase. It's with a very high value of coercitivity field. Yes, and you can see this history, this loop of this permanent magnet with very high coercitivity up to 1 Tesla, 1 kiloampere per meter. Yeah, due to the 3D printing technology, it becomes possible programmable grain size distribution. For example, around 1 millimeter. It became possible to control of microscopic sample size, and finally you can enjoy freedom of shape of hard magnets. As you can see this example, when you create the rings with special roughness by 3D printing of these materials. We combine these two ideas for create some magnetic modulation of amorphous microwire with a very complicated chemical structure that consists of rare earth and transition metal. Attractive magnetic properties of rare earth and transition metal materials can be used for many modern applications. I think that you know. So we create magnetic microwires with this composition: praseodymium, dysprosium, iron, cobalt, boron, by pendant drop melt extraction technique. This is sketch demonstrate this possibility. If it will be interesting, I can explain later because I doesn't have a lot of time. We found a lot of new advantages of these microwires. It is first of all micro tweezers, magnetic tweezers. It can be used for biology application, for manipulation of magnetic cell, magnetolabeling cell, without any mechanical treatment, without any mechanical touching, so without a mechanical action, just due to the gradient of magnetic field of these microwires at the end of these microwires. Second one, it's micro refrigerators that based on magnetocaloric effects. Second one, it's modulation of magnetic structure. In this presentation, I will show you. So our idea was how we can use local laser treatment of the micronized areas of the microwire, where initially amorphous material is converted to microcrystalline state. In this case, we can change coercitivity field locally because heat conductivity is time limited and small volume of the microwire is rapidly heated, extremely rapid. Conditions of crystalline are created. On the slide, we can see our experimental results. First column, it's some images of microwires, two types of microwires. First and second, it's amorphous microwires that was created by with different cooling rate. For example, first it's 55 meters per second, and second 25 meters per second with cooling rate. Third and fourth, it's these microwires, but after thermal treatment. Thermal treatment was done by just special heat, vacuum heat at 900 Celsius degree during the 30 minutes. Second column describes us the structure that was done by electron pattern, electron diffraction by we used TEM microscope, transition electron microscope, jewel And you can see that completely amorphous state was in initial microwires that confirm the STEM images. But when we decrease of cooling rate, so it's a small amount of very small crystals appears, as you can see this example. But on the magnetic structure, it's not influence because the hysteresis loop was squared and no any changes in coercitivity wasn't observed. But when we, after annealing of these two samples, you can see that the situation completely changed. You can see the spots that corresponds crystalline state, and it's very beautiful. These crystals are shown here, and you can see the latest parameters. And this value corresponds as a hard magnetic phase 241 and phase 41 and 24. And this phase gives the very high value of coercitivity field, as you can see here and here. These differences corresponds the differences in initial state of these microwires. You can see that this situation more squared hysteresis loop, and this one with slow steps, because create two phases. Okay, chemical composition and structure of these microwires, of course, were attested by a lot of techniques. As you can see several examples. It's X-ray diffraction, it's electron backscattering analysis, and EDX, electron dispersive X-ray analysis, and the spectrum. We monitor. So what we are looking for? First of all, we should confirm initial amorphous state and appearance crystalline structure after annealing, and local distribution of elements. And you can see this map, and of each elements was distributed on the surface, on the cross section, and transversal cross-section, and this map scanned along the microwires, so it was homogeneously the distribution of each elements, and not any additional impurity it wasn't observed. Okay, but now I told about integral properties, but we are looking for very delicate, very local changes. Yes, and we need this technique. We used FIB, focused electron beam. For cutting, for cutting the special lamel in the individual place of microwires, and you can see this experiment, our results, and. Due to this possibility, we can control the changes locally. For example, when we use local treatment, laser treatment, we can measure crystal structure in different places. So it's very interesting. Okay, and now you can see these results. You can see microwire after laser treatment with non-irradiated and irradiated areas. This is the same images, and analyzed atomic structure of the lamellar microsamples cut off from non-irradiated and irradiated areas that labeled 1 and labeled 2 and circled by dashed lines. Electron diffraction patterns in non-irradiated and irradiated areas respectively, and you can see here, and TEM images of irradiated and non-irradiated areas. Laser spot was over 8 or 10 microns diameter and moved perpendicular to the main axis of the microwire, imprinting alternating bands on the microwire surface. So you can see that structure of these two places very different, yes? Continuous halo corresponding to atomic order in the nearest coordination spheres is revealed by TEM diffraction in the non-irradiated area 1, while discrete electron diffraction patterns are found in irradiated microwire area. The presence of nanocrystalline grains, the size over 20-30 nanometers size, with different lattices, period 0.87 and 1.27, as you can see here, is revealed instead of structureless background corresponding to non-crystalline low-ordered material in non-irradiated areas. You can see that just gray images. So analysis of the lattice parameter of the crystalline grains shows that there are hard phase 241 and another phases 141 and 1, 2, a lot of paramagnetic phases in irradiated areas. These phases you can see on the slide. As I said, one of them is hard phase 241 and there's one, and their atomic structure you can see here. And what differences? It isn't not just name phase so well, because this phase have different magnetic properties with different coercitivity. And please note that praseodymium and dysprosium can replace, can be substituted instead of dysprosium or praseodymium for example, without change of the atomic structure as well as in other phases. These changes, crystal changes, yes, can be affect to the magnetic properties, as I said, and we confirm this by a magneto-optic technique. On the slide, you can see our experimental results that was done by magneto-optic Faraday effect, based on Faraday effect. Yes, значит, the reflection of polarized light from the film, how to say, we used in this technique, Moif technique, to establish what changes in the magnetic state of the microwires are caused by laser radiation. A film of yttrium garnet, you can see here, yttrium garnet film, coated with mirror layer here, has been deposited on the microwire surface. The reflection of polarized light, you can see here, from the film indicate a perpendicular scattering field of microwire, radial component. And we can see this reflection as changes in this contrast, black and white, and green with any magnetization. And left side of in left side of the slide, you can shows periodical dark and light areas corresponding to the series of magnetic dipoles imprinted to the microwire surface. So you can see these places from laser annealing, local laser annealing, and this is source of creation of these dipoles. Thus, the laser irradiated areas have a perpendicular radial component of magnetization in contrast to non-irradiated amorphous areas of the same microwires. Because you can see for this non-irradiated, these various spots, it's irradiated place. It was the analysis of the local hysteresis loop of longitudinal normalized magnetization recorded by mock of magnetization in the over over 500 Ørsted in the non-irradiated areas of the sample on 10-20 Ørsted. You can see this blue and orange lines. Blue is before and orange after irradiation. Since contribution of shape anisotropy is constant, the enhanced saturation field in the irradiated areas corresponds to the appearance of magnetic crystalline anisotropy, this 500 Ørsted. But this results corresponds surface magnetization, yeah, and we interested in what happens in bulk. For this one, the field dependence of integral magnetic moment of the whole wire was been recorded by squid magnetometer quantum design up to -5 Tesla. Before and after irradiation. Although 20% of microwires was irradiated, a smooth saturation of magnetic moment, normalized magnetic moment curve has also been found. As you can see, blue one it's before and red one it's after irradiation. And you can see this smoother, anisotropy field was the same, 500 Ørsted, and was similar with that determined from local measurements in a Kerr microscope. Okay, and now we compare these results with bulk treatment, thermal treatment. For example, you can see this two hysteresis loops. One of them corresponds initial state amorphous microwire, labeled 1, and second one this wire after thermal treatment. As you can see, the coercive field increase, change in crystal structure can be very clear. You can see here, and creation of the hard phase 241 was confirmed by TEM microscope, and you can see this TEM image. And the size distribution of these crystals show us that mainly crystals with size 0.2 microns create at thermal treatment. But when we use laser irradiation, we create the same phase, but the size of this crystal so smaller, just 10-20 nanometers, and this explain why our coercitivity not increase so much, because the size of this phase so small, nano sizes, and this is a reason why the changes that was observed just 10-20 Ørsted. But we did it. We changed locally the coercitivity. And these conclusions, maybe I was so fast, I'm sorry for that. Main results I already said. First of all, that single laser impulse cues the transformation of the amorphous spin glass alloy into the nanocrystalline structure with this phase, hard phase 241, and another one with this low size crystals. So it's a reason of change of local magnetic properties is appearance of crystalline anisotropy in these nanocrystalline areas subjected to the laser irradiation. I would like to thank for all of you, and thanks for your attention. Thank you.
Thank you for interesting presentation concerning this interesting phenomena, magnetic phenomena in borates. And we have space for 2 questions, if any. So we don't have questions here. Thank you again.
Thank you.
And goodbye.
Bye.
presentation and I still not.
So we will start it. So now we switch to next presentation. Next presentation
Which one is
from
yours? Presentation.
Так, папка 2011. О, не вот это, да.
2021.
21.
The next presentation will be done by Professor Katerina Muzika, and the present from Kharkiv National University of Radioelectronics. The title of presentation is laser-based non-structured materials for electroanalysis. And the floor is yours.
Thank you very much. Dear Chairman, dear participant, it's a big pleasure to attend this conference, especially in face-to-face format. And I would like to present a recent work of our Laboratory of Analytical Optochemitronics devoted to quite new materials, laser-induced periodic surface structures on glassy carbon. So you can see the same image of this structure at this slide. What is laser-induced periodic surface structuring? It's a simple one-step surface functionalization process which help to obtain nanostructures and a different kind of materials such as metals, dielectrics, and semiconductors. These techniques create nanostructures in lines with different shape and different spatial period. Depends on the parameters of laser irradiation, polarization, depends of duration of laser irradiation and number of pulses. So, as you can see, an example of laser-induced periodic surface structures, which is available on recent review. So, why do we need to glassy carbon nanomaterials functionalized with nanostructures? Glassy carbon is widely used in electroanalysis material in electrochemistry, and my topic is about application laser-induced modification material in electrochemistry. So, to enhance a detection efficiency of glassy carbon is typically modified with different nanomaterials such as carbon nanotubes or graphene. And preparation of well-reproducible and well-defined surface for which surface structure and electrochemical behavior may be correlated is a great pleasure. That is why using femtosecond modification of glassy carbon is quite promising for activation and functionalization glassy carbon materials in turn of increasing surface of this material and improving sensitivity of further electroanalytical application. So, which advantages of glassy carbon irradiated by femtosecond laser for electrode application in comparison of our form of nanostructured carbon nanomaterials such carbon nanotubes and graphenes? First, it's a one-step functionalization. So, in contrast with functionalization glassy carbon with carbon nanotube, functionalization using femtosecond laser looks quite similar, simply. So other advantage is lack of contamination, because we didn't need to use any binder in order to link carbon nanotubes to the surface of carbon electrodes using femtosecond irradiation. And thus, its laser texturing allow to produce high reproducible surfaces that, in contrast, for example, for immobilization glassy carbon with carbon nanotubes, reproducibility is, I think, is lower than in case of obtaining periodic structures using femtosecond laser irradiation. And also it's very important and enhance electrochemical active surface area and enhance wettability. These two parameters is very important from the point of view of electroanalysis. So, the main goal of this work is shed light into the nanostructure characterization of this new material. It should be noted that laser-induced periodic surface structures have been investigated from the point of view of changing mechanical, optical characteristic of the initial material. But there is lack of information, lack of research about changing electrochemical properties using nanostructuring with femtosecond laser. That is why this work it's our first step in this direction. And first we start from nanostructure characterization using atomic force microscopy. Second task of our work is investigation electrochemical behavior of these glassy carbon materials, nanostructures with leaves, and determination further direction of research. So, as you can see at this slide, it's atomic force microscopy image of on the left of the glassy carbon modified with LIPSS structures, and on the left is reference glassy carbon electrode without any treatment. So what we can see? We can see some special we can see structure, some periodic structure, and the spatial period is around 600 nanometer. That is less than wavelength of incidence laser irradiation, which is 1030 nanometers. So this periodic structure is perpendicular to the polarization of the laser wavelength. Next slide, it's also devoted to atomic force investigation, microscopy investigation of the depths of this nanostructure. Why it's important from the point of view electroanalysis? As I told before, for electroanalysis is very important increase electroactive surface area, and of course electrochemical surface area related to geometric surface area, and when we increase the geometric surface area, it's with a high probability we increase electrochemical surface area, and this help to reach higher signal and reach higher sensitivity of electroanalytical investigation. So these pictures, this FM photograph scans help us to determine depths of the irradiated structures. So we can see that the structures of glassy carbon after irradiation with the femtosecond laser has a form of nanoripples with approximately the same depth, which around 500 micrometers. With around 500 micrometers, approximately the same depth, and we estimate that such structure enhance geometric surface area approximately 2.5 times. But it should be pointed out that enhancing of geometric area is not always equal to enhancing of electrochemical active area, because Faradic process cannot appear on all surface of electrode, and that is why it is necessary to investigate in more detail, but is beyond the scope of this work. So the next test is the wettability test. As you can see on the left is a reference glassy carbon electrode, and the wettability is the contact angle is near 79 degree. That is significantly higher than the wettability contact angle of LiPSS structure on glassy carbon. This means that LiPSS functionalization help to reach enhance hydrophilic property of electrode, and it's also important from the point of view of electroanalytical application, because depend on wetting adhesion, because adhesion of water to the surface electrode it's quite important, and it's help to increase probability of analyte reaching to the electrode surface, and that is why increase in wettability is advantages of these LiPSS structures. And as you can see from the picture, optical properties is also changed, because you can see dark, it's a glassy carbon, and color change, it's glassy carbon with LiPSS structures. So the next step of our research devoted to the electrochemical investigation of this LiPSS structure, and we start from investigation of background current and potential window of this electrode. So we can compare glassy carbon without modification and glassy carbon with nanostructured with LiPSS, and we can say that the potential window is comparable, but the background current for LiPSS is higher. The second step is the investigation of intrinsic electrochemical properties in example of determination in a sphere representative species, ferrocyanide, redox couple. This couple is not sensitive to the surface oxide, and what we can see that electron transfer for the electrode modified with a laser-induced polymeric periodic surface structure is faster. So from the further analytical point of view, it's advantage. So we can say that LiPSS has an advantage over the glassy carbon. So other kind of species is outer sphere kind of redox species, ruthenium hexamine. So also we can see a different kinetics in comparison with the reference glassy carbon electrode, and we can see that the capacitance currents is also high. That is can mean that absorbance occur of this species. So here you can see investigation of hexamine ruthenium in more details, depend on the scan rate from 25 millivolt per second to 200 millivolt per second. And conclusions, what we can say? We can summarize that nanostructure in glassy carbon with LIPS is allow to fabricate surface with enhanced surface area, geometric surface area, enhanced wettability, that it's from the electroanalytical point of view, its advantage. Second conclusion that outsphere type of redox species, an example of hexamine ruthenium, which are representative molecules that undergo outsphere electron transfer, was just easy detected on LiP surface structure than ferrocyanide, which is classified as the inner sphere redox structures. So redox species. So this means that depends on the behavior it depends on the type of electron transfer, outsphere of inner sphere. We can detect different species, for example, dopamine, ascorbic acid, and its behavior, its kinetic will be defined of the kind of electron transfer, and LIPS applicability will be also determined by the type of detection analyte. But it's also direction for our further research. So, and LiPSS structures can be prepared not only at glassy carbon, at also on other materials such as platinum, gold, or other materials, electrode materials that usually have been used in electroanalysis. So it means that it's quite big area for further investigation, not only for our group, but for other scientists with multidisciplinary areas. So, acknowledgement. This work was supported by National Research Fund of Ukraine, and authors of this presentation also acknowledge Nanolab company, which located in Lviv, with a special thanks to the directors of this company, Yaroslav Gnilitsky. He is here, and I would like to thanks to all my colleagues that helped to obtain the result which I reported during this presentation. Thank you very much for your kind attention, and you are welcome to Kharkiv, to our university, to our laboratory of analytical optochemitronics.
Thank you for the presentation. So, do we have questions in the room? Okay, no questions, so thank you again.
Thank you very much.
Okay, next speaker. The next presentation according to the program is cancelled, unfortunately. And the next speaker, I would like to invite Dr. Sergei Sologub from Institute of Physics of National Academy of Science of Ukraine with the presentation Electronic Magnetotransport in Pristina and Adsorption Modified Epitaxial Bismuth Nanofilms. Presentation.
Presentation.
Yes, it's here.
Yes, it's here. I have already downloaded. Okay, thank you.
Dear colleagues, I'm glad to attend this conference again, and I'm grateful for this opportunity to present our results here. And the aim of my talk is to attract your attention to investigations of transport properties of ultra-thin bismuth nanofilms, electronic transport properties. These films are quite interesting objects with unusual properties, and I will present a short overview of our and not our experiments in this field. But first of all, I'd like to remind you some specific properties of bismuth, which is related with thin films. You know that bismuth is a heavy element of the periodic table. It means that spin-orbit coupling is very important for describing its properties. And in particular, it reflects in the structure, electronic structure of bismuth surface states. You can see these pink lines. This is Fermi surface of bismuth surface electronic states for bismuth 111 surface, for the bismuth 111 surface. And these electronic states are spin polarized. Spin polarization exists also on the surface of bismuth nanofilms. If you grow nanofilms on the surface of some, for example, in this case, this is germanium, you have nanofilm with spin polarized surface state. But bulk properties of bismuth is also very unusual, are also very unusual. You can see that both electrons and holes from these regions contribute to conductance of bismuth crystal, of a bismuth crystal. And conductance exists due to overlapping of two energetic bands located in different points of K space, of inverse space. But if you reduce thickness of the crystal and form bismuth film, you show that a gap opens on the Fermi level and bulk states became quantized. Therefore, we can consider bismuth nanofilms as a quantum well with surface energetic levels. Just a moment. This transition that I showed earlier, transition from semi-metal to semiconductor, is confirmed by car-result photoemission techniques. You can see, you can see these gray lines in photoemission images. This is that quantized level that I showed earlier. And you cannot see it for thicker films. In this case, the spectrum is continuous, almost continuous. But as regards to the surface of bismuth, I show again this Fermi surface. This is results of an experiment. And this surface states, as I said, are spin polarized, and arrows, these blue arrows, show the direction of spin in these surface states. This picture of these arrows, sometimes it is named as a surface texture, surface spin texture. But very important consequences follows from the existence of surface texture. It's impossible to scatter electron or holes within this space, within this surface electronic state, without change of spin of the electron. It means that it reminds us a little topological insulators, but bismuth is not a topological insulator, but the material with reduced scattering. And we tested experimentally how adsorption, for example, magnetic and non-magnetic impurities influences on the transport properties of such films. But first of all, on this slide, I show details of our experiments. You can see that the experiments are ultra-high vacuum. We grew our films on silicon 111 surface, and with 7x7 reconstruction, and all processes, measurements, growing, and control of the spin of the structure of these films, surface structure of these films, were made in situ. Oh, sorry. And this is our experimental results. You can see these curves. They present dependence of conductance of film of different thickness on temperature conductance. And we fit these curves using this simple expression containing two parts, metallic and semiconductor conductance, and can determine dependence of width of energy gap on thickness. You can see that this value is rising dramatically when the thickness is decreasing. But then we performed next experiment. We measured dependence of conductance on the film thickness for two temperatures, about helium temperature and about room temperature. And you can see that in this region for thickness less than 50 bilayers. Bilayer is about 4 angstroms. One bilayer is about 4 angstroms. And in this region, the conductance is almost the same. It gave hints that the surface and bulk electron states in the films are connected, are coupled. We performed next series of measurements. This is magnetoconductance measurements. We measured both magnetoconductance and Hall resistance, and performed fit of the experimental data with these simple expressions of classical theory of magnetoresistance, and in this way we obtained dependencies of concentrations of holes and electrons and mobilities, dependence on film thickness. You can see that non-monotonic behavior is attributed to complex non-monotonic behaviors. It's attributed to film with low thickness. It again could be considered as a connection between surface and bulk electron states. Not bulk, but surface states of this quantum well, which is a film of bismuth. And no more interesting and important results we obtained were analyzed quantum corrections to the magnetoconductance. Left panel shows that we again have this fitting for magnetoconductance, and difference between classical curve, fitting curve, and experimental data is shown here. We use this expression of theory of Hikami-Nagaoka-Larkin, which describes this quantum correction anti-localization in this case, to determine two parameters, phase length L and parameter alpha. Phase length is the length at which electron doesn't change its phase. It means that if you have a film of bismuth and the thickness is less than phase length, electron could move from upper, for example, surface or interface to lower interface or backward without change phase of the phase. It means that these two channel of conductance, these two interfaces are connected. And if you have a film with large thickness, they are disconnected. This conclusion is supported by a result of determining parameter alpha. According to the theory Hikami-Larkin-Nagaoka, the parameter would be should be about minus 0.5 for one channel of conductance and about minus 1 for two channels. 0.5 minus 0.5 for every channel of conductance. And you can see this transition between value which is close to 0.5 to value which is close to minus 1. Therefore, we have a situation when coupled surfaces or interfaces is decoupled after the increasing of thickness of the film. And in the end of my talk, I'd like to tell you something about adsorption of different atoms on the surfaces of these bismuth nanofilms. In this case, these nanofilms of 8 nanometer thickness was used. You can see that the most strong scatter is chromium. This is a magnetic element. It would be predictable because this magnetic atom break time reversal symmetry and allow these transitions between the states with different directions of spin. And antimony is not magnetic material. It is the more or less efficient scatters in this set of adsorbates. But the interesting question is about three adsorbates: iron, cobalt, and bismuth. Bismuth is not magnetic material, additional bismuth on bismuth, I mean. But these two materials are magnetic. And we found answer for this question in the magnetotransport measurements for the films covered with different amounts of adsorbed bismuth and iron and cobalt. There were very small amounts, less than 0.1 monolayers. And the conclusion is as follows. Yes, magnetic atoms have a noticeable influence on scattering. But sometimes charge transfer between adsorbate and substrate has a more strong effect on the conductance than these effects of magnetic atoms. It depends. It depends. And in conclusion, coupling of surface and quantum well states of bismuth 111 nanofilms does not allow a separation of their contribution in a strict ways, because when we change thickness of film, of bismuth films, we change positions of these quantum well states inside the film, and therefore we can provide conditions for transitions between surface electronic state and bulk electronic state. And bulk electronic state has less mobility than surface, and everything is connected. And one more. Conclusion that the concept of breaking time reversal symmetry in the presence of magnetic impurities on the bismuth crystalline surfaces is too simple. Thank you for your attention.
Thank you. Thank you for just nice excursion into the world of nanofilms and phenomena. Yes. Thank you, it's interesting. And do we have a question in the room?
No.
So, thank you again. And unfortunately, we are out of time, so we have to continue without coffee break. The next presentation will be done by Dr. Viktor Kisluk. Is he on the line?
Nету.
The next one is Professor Andriy Horyachko. Is he here?
He was here. Yes, he was. I was here.
We're doing 3 minutes break. 5 minutes? Let's make a 5 minutes break, and we will continue at 16:20, half past 4. I invite the next speaker, is Dr. Viktor Kisluk from Kurdimov Institute of Metal Physics, with presentation PV encapsulant material mechanical properties. So the floor is yours. Can you hear me? Yeah, the floor. Yeah.
Do you hear me and everything is seen?
Yeah,
is it clear?
We can hear you.
So then, may I start?
Yeah, you can start now. Could you please switch off the YouTube translation on your computer?
I'm sorry, I just turned off the conference. Yeah. Everything is seen. Yeah, is it clear? So then, may I start?
Мы сказали. Can you please switch off the YouTube translation on your computer?
Okay.
I'm sorry, I just turned off the conference.
We cannot see your presentation.
Okay, do you hear me?
Yeah, we hear you and we see you and your presentation
okay.
too.
So sorry for this delay. Let me start. And good afternoon, dear chairman and dear audience. First of all, I would like to give thanks to organizers for this unique opportunity to present our research entitled Photovoltaic Encapsulant Material Mechanical Properties, Peculiarities and their Microscopic Mechanisms. Made predominantly in the Institute of Metal Physics, named after Kurdimov, and the objective of our research is twofold, and we have the current objective, which concerns the commercial material, ethylene vinyl acetate, used in photovoltaic modules as a cover material, even encapsulates the photovoltaic module. And we could restrict ourselves to this topic, but there is another one which could not allows us to be calm, and it attracts most of our attention, is how to predict the actual service lives of materials on the basis of mechanical tests. And this is my intention to convince you that we can approach to this problem with this rude, for the first glance, mechanical methods. And why we so sure? Because molecules are not stupid, and matter consists of molecules, and thus if they are not stupid, they are predictable. And so we try to use macro level tests to get information from nanoscience, and moreover, now one of the main approach how to improve materials is usage of many nanostructured materials, nanocomposites, and which modifies the property of the initial pristine matter. So our technique is intended to monitor these changes induced by the additives to improve their property. So it's my pleasure, first of all, to introduce my colleagues. This is the researchers from Kurdimov Institute of metal physics. This is the head of department, Professor Serhiy Kotrechko, Department of Physics of Strength and Structure of Materials. Dr. Yuri Polushkin, Dr. Vyacheslav Shivanyuk. We also applied for the help to researchers from neighboring institutions, the Technical Center and Institute of Macromolecular Chemistry with Dr. Volodymyr Trachevsky and Svetlana Ostapyuk to make additional independent study of the matter to be sure that we deal with the material with properties declared by commercial providers. So what is the matter we deal with? It's the ethylene vinyl acetate copolymer, because it consists of two parts, the polyethylene part and vinyl acetate. And vinyl acetate content usually is around 30% for the successful usage in the photovoltaic cells, photovoltaic modules. And this is also a kind of elastomer because of the special curing agent which initiates the cross-linking of this between the adjacent skeletons of polyethylene chain. And the nuclear magnetic resonance distinctly demonstrates the presence of all the counterparts declared by the provider. And in addition, we also find the appearance of tiny, narrow component which appears after curing. Curing is the process of annealing at enhanced temperature, and it leads to the formation of crystal amorphous medium. The nanocrystallines of polyethylene is surrounded by the amorphous medium of the rest of the copolymer, linked with cross-linkage initiated by this linking agent. And after annealing, probably we associate this line with the increased freedom of the end CH3 group in this material. And also we have the fingerprints of infrared spectroscopy demonstrating the presence of all the necessary, all the declared components, CH2 groups, and the component responsible for the acetate group. And so why the photovoltaic modules failed? And the main reason demonstrated here in this diagram briefly shows that the main purpose, main reason of the failure is originates from the degradation of laminant. It has the ethylene vinyl acetate film surrounded by this module. Because it's normally, it's logic, because it's the frontier of the solar flux, and it first takes the impact of the solar radiation. And what is the remarkable fact for us, that the degradation, which is accompanied by discoloration, proceeds predominantly at the central part. It is at the part where the mechanical stress is the highest. This stress is the reason of the stress is a thermal expansion, difference between two or even three adjacent components. The glass, the film itself, and the silicon module. So what about the second task? The history knows several approaches to prediction, and we'll leave alone the some astrological and psychological schools and concentrate on the mathematics and physics and thermodynamics. And the first who tried to make, probably one of the first, because there are many scientists look at this problem, was this one Arrhenius, who proposed his well-known formula, and this formula contains the information about the time, because the rate of chemical reaction is reversely proportional to the time of the process, and it is expressed in the terms of activation energy. And this idea was then transformed into the representation of the time of the process, and it was actively developed by Zhurkov and represented in the form of the also dependence on the activation energy with the reduction of the barrier by the action of external mechanical stress. And the well-known diagram in terms of the A ring, the free energy versus reaction coordinate, we can represent very briefly and schematically the first approach is represented as the solid line with the constant activation energy barrier, and the reduction induced by the unidirectional stress applied to the material is proportional to the stress, and the proportionality factor has unity of volume, and activation energy, the normal activation energy of in the absence of the external field. So we can try to adopt a mechanical tensional testing machine to proceed to measurement and to apply these approaches for prediction. And the first mode usually widely used in this type of machine is the creep mode, when the force remains constant along the whole the testing. And actually this mode is directly related to the formula of Zhurkov, since to some extent we can consider the stress to be the constant, but only to some extent. I will later explain our position on this. And then the second mode is the constant strain rate, but the problem is the strain rate of the grips. Usually the operational parameter of the mechanical testing machine doesn't equal to the rate of the strain of the base, the parameter which we are interested in because it contains the real physical meaning. We have made some preliminary study and found out some approximation for the initial phase, initial state, and it is in good correspondence with the experimental data. And another obstacle is concerns that in most data represented in literature, there are some changes of the geometrical size of the sample is neglected, and representation is made in the terms of engineering value of the strain. So we have made our measurement, the violet line, and to our surprise, we discovered that the literature data the blue one, is very close to our data represented in the engineering notation. It's far from the physical meaning, and so we need for such a large displacement, such a large strains, we need to use true value, this one. And so what we did, and there is also another obstacle to concerns the change of the cross-sectional area. And to follow these transformations during the experiment, there are two ways. The one way is to refer to some tabular value of this coefficient. The coefficient of Poisson represents the ratio of transversal strain to longitudinal one. But the matter is that during our study, we found out that the real value of Poisson ratio is also doesn't remain unchangeable. And here it is. Let's consider two limiting cases. The first one, very slow rate of strain and very fast rate. And we can see the very huge difference between these two lines. And in general, it can be concluded that the Poisson ratio doesn't remain unchanged. And in some cases, its value even exceeds 0.5, which is some demarcation line divided two regions, the upper region corresponding to the reduction of the volume and the lower one of the increasing the volume. And fractograms demonstrate remarkably the nature of the changes after the failure. You see the big voids representing the huge increase of the volume. But by the way, how to approach the problem of prediction? And we use the known Bayes criterion for probability of the changes of the material. It represents the loss of durability during some time, delta t, if the fluctuations rate of fluctuations time constants is tau if. So the probability for this elementary act can be represented in this way, according to this criterion, and which is represented in integral form, like this equation, with T1 is the time when the process is completed. So we look at our curve, the true strain, true stress curve, and find out that it follows the power-like dependence with two distinct regions. The first one has one slope, and another one has another slope. And for some preliminary, from some preliminary discussions, we find out that the first region corresponds something like scrolling out the ball, because the polymer it entangled, the polymer skeleton entangled with each other, and for this initial stage, there's some unscrollment proceeds, and then the failure itself proceeds at the second stage, when the shortest skeleton remains to fail. And we concentrate on the first process and apply this formula. And due to as a result of some calculations using our preliminary work on how it proceeds with the strain rate, and we get the dependence where we can calculate the activation energy and the factor, some structural factor responsible for the time constant in the well-known Zhukov formula. And the activation energy is somehow surprisingly a little bit higher than we expect, but it can be explained in the main idea that in the well-known experiments in this topic, activation energy was estimated for the material without cross-linking. And our cross-linking strengthened the system, and that is why the activation energy is a little bit higher. So, as a conclusion, I would like to state that our technique we developed on the basis of Zhukov formula and modified for the mode of constant grip strain rate is very rather in rather good consistency with the data received for the ethylene vinyl acetate material. This material behaves like appropriate material for this reason. I hope this technique can be applied for another modifications of the encapsulant, improved by nanoparticles and another nanospecies, and we can also proceed our application of our technique. And also some discovery was also surprised. The Poisson ratio doesn't remain the same during the mechanical testing, and it contains, I suspect, much more information about the technique. And also the results relate also for predicting the service life and finding activation energies for huge class of materials with power-like dependence of strain-stress dependence, and also the problem of recycling. So instead of the epilogue, I just propose you to quote the Svante Arrhenius, Nobel Prizers, and who states that humanity stands before a great problem of finding new raw materials and sources of energy that shall never become exhausted. In the meantime, we must preserve what we have, but must live as much as possible for coming generations. So, thank you for your attention.
Thank you for presentation. And we have time for questions. Do we have questions in the room? No, so thank you very much again for your presentation. And now I invite the next speaker, is Professor Andriy Goryachko from Taras Shevchenko National University of Kyiv. With his presentation is cerium oxygen on molybdenum structured surface. The floor is yours.
Yeah, thank you. Okay, you have already seen my talk in its entirety. Good afternoon, ladies and gentlemen. Now I will present my talk, surface structure in cerium oxygen films on the molybdenum 112 surface. And this research is a joint activity of the Institute of Physics of the National Academy of Sciences of Ukraine and of the Faculty of Radiophysics, Electronics and Computer Systems of the National Taras Shevchenko University of Kyiv. Actually, my talk will be about epitaxial films, in fact, one monolayer films. And when we speak about the epitaxy or epitaxial films, we always know that there is a kind of a struggle for the structure between the film and the substrate, because they both, in the most general case, have different lateral periodicities. So one is trying to impose its periodicity and structure on the other, and vice versa. And a lot of interesting phenomena, in the first place structural phenomena, but also electronic phenomena can occur due to this. The rare earth materials, rare earth atoms on molybdenum substrates, in particular molybdenum 112, are extremely interesting because from one point of view rare earth elements are a little bit alike, but on the other side they are quite different. They can form very different structures depending from one element, if you go from one element to the other on the same substrate. And just to give you a couple of examples that were investigated in our group, there are, for instance, gadolinium. There are gadolinium chains. This is a 3D model of 5x1 superstructure formed by these chains. Or, for example, in the case of dysprosium, there can be a very big, very large variety of different structures and supercells and superperiodicities on the molybdenum 112 substrate. Also, quite recently, we have investigated cerium, such element as cerium, on this substrate, and this is our very recent work where we reported that there can be such a superstructure, periodic stripes with a periodicity of several nanometers. The interesting part in that was that a half of monolayer of cerium atoms, if it would be atomically clean, would form so-called C2x2 supercells. And for those of you who not specialized in surface physics, I would just explain that this multiplication, like 2x2, 5x1, and so on, they just mean that the periodicity of the placement of the supercells of the surface unit cell crystalline structure in the film is, for instance, 5 or 1 or and so forth times larger than the intrinsic atomic periodicity of the material of this surface, of the material of this substrate. And if you add just a little bit of doping by oxygen, as you can see here, then the same half monolayer amount of cerium atoms can already form a P 2x1 superstructure. P and C, they are referring to the symmetry. So we see that again this is another rare earth element, and again it gives different periodicities and different superstructures and different symmetries and so on. So we have decided to investigate it further. The methods, this is an experimental work, and the methods of investigations are, first of all, the and the method of investigations, first of all, is low energy electron diffraction. So in fact, we just irradiate the sample with electrons coming from the electron gun at energies like several tens or several hundreds of electron volts, and we use the crystalline grating of the surface basically as a diffractional grating, similar like an optical diffractional grating for the laser beam. And so by finding out what are the directions of the diffracted beams, not optical beams, but the beams of the de Broglie waves, we can find out what is the periodicity of the placement of the atoms, or the supercell periodicity on this film adsorbate system, film substrate system. And that's how the low energy electron diffraction image or pattern, we call it, looks like. So this substrate, molybdenum-112, it has such a structure that consists of deep so-called troughs and a little bit elevated ridges. And here you see the periodicity of the atomic placement along the ridge and perpendicular to it. That's 0.273, 0.445 nanometers. So we absorb cerium, for example, cerium on top of this substrate, and it sits inside the trough. And then if you have a periodic arrangement of these adsorbate atoms, then, for example, if they are 2 times farther away from each other than the atoms of the substrate, then in the lead pattern you will see the diffraction spots 2 times closer. That's how we know that this is a 2-by-1 periodicity, just to give you an overview of what these experiments are all about. And we have carried out, of course, all of our investigations in ultra-high vacuum environment at 300 K, so that means at room temperature. But these samples were prepared by adsorption of cerium and oxygen, and later on annealed at 1400 K, as you see, and later on cooled to the room temperature and investigated with our experimental techniques. Another experimental method is Auger electron spectroscopy. So you see there is an Auger effect. We irradiate our material with the primary electrons, in our case with 1900 electron volt kinetic energies. Then, as you know, the Auger effect takes place, and the Auger electron is ejected. And as you know, its kinetic energy is very characteristic, like fingerprints of the element, and by comparing this energy with the tables of kinetic energies of Auger electrons, we can really clearly identify which elements are there. And for this, we of course take the spectrum of the electrons coming from the sample. If you have a peak of, for example, at approximately 503 electron volts, we for instance know this is oxygen originating from the KLL Auger transition, and in a similar manner for molybdenum and cerium and so on. And then this is how the peak of these Auger electrons in the spectrum of the secondary electrons emitted from the sample looks like. If you differentiate it, then for example you can have the difference between its highest point and the lowest point as the measure of how many atoms are on the sample per square unit area. And then if you compare it with some known reference sample, in our case that was a very well known and largely investigated structure of 2-by-1 oxygen molybdenum on molybdenum-112 on the same substrate, which contains a half monolayer of oxygen, then we can then use this reference to calculate the amount of oxygen and of course of other elements like cerium in our actual samples. And we also have investigated the work function. We did the work function measurement by this method. It's actually, we are using a thermoelectron emission, or thermoionic emission as it's often called. We basically have 2 electrodes. One is an investigated electrode and another is some reference electrode. If we hit one of them, then the thermoionic emission of thermal electrons can take place. However, due to equilibration of the electronic systems and establishing of the single Fermi level over the entire system of these 2 electrodes, there will be a contact potential difference between them, actual electric field or the difference in electric potential on the surfaces of these 2 electrodes. And then it can happen that the electrons face the potential barrier and cannot go from the cathode to the anode. So you will have to apply some additional so-called backing potential in order to compensate for this, and the potential at which it exactly compensates, that will be the point where the thermoionic current or thermoelectronic current appears, and you will know that this potential is the difference between the work function again of some reference electrode and the actual investigated electrode surface that you're using in your experiment. And as you see, one of the reference electrodes, we can use a 4.36 electron volts. This is the work function of a clean, of a pure molybdenum-112, and then we can compare the work functions of the samples containing some cerium and oxygen adsorbers on top of that, and see how this adsorption influences the work function of the sample relative to the pure molybdenum-112 substrate case. Then, using all these experimental techniques, we have established such a general picture how the structure of thermally equilibrated film, and as I have mentioned, this includes the 1400 K temperature for thermal equilibration. So how the structure of the first monolayer of cerium looks like, and again, all this relates to the case of the almost pure layer of cerium containing at most several atomic percent of oxygen impurity. So first we have this already reported nanostructure consisting of parallel stripes. Then if you increase the coverage, and here you see the definition of coverage, is actually the areal concentrations of either cerium or oxygen divided by Z of the concentration of molybdenum atoms in the molybdenum-112 crystalline plane. So if we have the coverage less than 1/4, then basically this superperiodic structure grows, and we can call it an island growth, because if you increase the coverage, then you get a larger and larger area of the molybdenum sample occupied by this superstructure until it occupies the entire surface. And after this happens, and we add even more cerium to the system, then what happens is the periodicity of this superstructure starts to grow, and we go actually from this 6-point-something nanometers and essentially into infinity. So when the coverage approaches 0.5, we have so-called I call it superperiodic singularity, and of course after this, when we reach the singularity, the superperiodicity of these stripes becomes infinite, and essentially after this the entire surface is covered absolutely uniformly by the cerium film with the 2x1 supercell in the adsorbate substrate system. And then what happens next? So we go here from 0.5 uniform 2x1 coverage of the surface, and then there is a cerium film contraction in one dimension. So the cerium atoms gets closer, they get compressed, but after we reach 0.75, there is relaxation in the first layer. So basically the atoms of cerium in the first layer, they get back into their 2x1 position, so that is relatively far away, and the excess atoms of cerium, they get ejected and form the second overlayer. And I would like to focus on this contraction phase further a little bit in larger detail. For instance, the first stage, the first stable, highly symmetric structures that we have found in this process was C8x4 superstructure. Here you see the cerium substrate, this molybdenum substrate with cerium atoms, and the supercell. This is a C8x4 supercell. It corresponds to the coverage of 0.64 and the reduction of the work function by 1.9 electron volts relative to the pure molybdenum-112 substrate. Then there is a C 1.44 times 2 superstructure. Again, you see here the supercell. Again, the placement of the cerium atoms, and you can notice that along the ridge or along the trough, the distance between two neighboring cerium atoms gets smaller, and that corresponds to the coverage of 0.7 and the reduction of the work function by 1.8 electron volts relative to the pure molybdenum-112 substrate. And then this stage, this is really the final stage of contraction. It happens at a coverage of 0.75. We have even a smaller decrease, of 1.39 electron volts relative of the work function relative to the molybdenum-112 substrate. And then we have the smallest possible distance between the two neighboring serum atoms along the trowel. And here you see this smallest supercell. So then we have established that the serum film cannot contract any further. If you add even a little bit more serum, then all the extra serum atoms will be ejected and form the unordered second layer of the film. But the interesting effect happens when you add oxygen to this substrate. So if at the same serum coverage, 0.75, we add oxygen in the same amount of it. So that is, you see the serum coverage is 0.75 and oxygen coverage is also 0.75. And then the oxygen atoms are designated by small red balls over there. Then we have a dramatic reconstruction of the surface superstructure, and it becomes C4x4. Yeah. Well, this we have established by means of low energy electron diffraction. But the most intriguing and yet unexplained effect is this, that the reduction of the work function, see, it's 1.42 electron volts lower than the pure molybdenum substrate, is almost identical to what was in the previous case when we had the same amount of serum metal atoms. So you see, in fact, what we did, we oxidized, essentially we have oxidized this adsorbed serum layer. And oxidation, of course, as physicists and chemists know very good, it's a rather dramatic change of the electronic structure, yes, because you're redistributing electrons from metal atoms to oxygen. And you would normally expect rather strong difference in such electronic parameter as the work function, yet in this case, there is almost, this influence is almost negligible. It's barely noticeable, like 0.03 electron volts difference of the work function of the surface relative to the molybdenum-112 substrate. And so I can go to the conclusions. So the equilibrium structure of serum monolayer on the molybdenum-112 substrate at 300 K after annealing at 1400 K in ultra-high vacuum depends on the serum coverage theta, and for theta less than 0.5 there is island growth regime where you observe the 2/n superstructure and n is increasing up to it reaches superperiodic singularity where n nears infinity. Then exactly at theta 0.5 we get there's a mistake here, there is not 2/n but 2/1 serum molybdenum-112 superstructure uniformly covering the substrate. And then when you go further from 0.5 to 0.75, there is a lateral, so-called lateral contraction regime where you have a succession of the superstructures designated as C8/4, C1.4/2, 1.33/1. And then have a lateral relaxation regime where you have again a 2/1 serum molybdenum-112 plus the unordered second layer of serum atoms. And the influence of substantial amounts of oxygen, like when it's equals to that of serum, is manifested in dramatic rearrangement of the surface unit cell. It becomes C4/4 serum or molybdenum-112, so it's a kind of a stoichiometric serum or oxide. And adding oxygen atoms, essentially which is an oxidation, should presumably change the electronic structure of the surface. However, surprisingly, it produces only a negligible, very small influence on the work function of the adsorbate substrate system. And so it is clearly obvious that the ab initio DFT calculations are needed to verify the crystalline and electronic structures of the reported film substrate interfaces. So if there are some theories getting interested, you are really welcome to cooperate with us. Thank you for your attention.
Thank you for interesting presentation. Do we have questions? Yeah, we have question. Please, microphone.
I have two small questions. And first of all, what's the reason when you choose exactly rare earth ions, not transit metals and so on? And the second one, it's a very nice picture, but is it could be something applied? Because it just look like you do it just some picture for yourself.
Thank you. Yeah, very good question. Actually, your first and the second part, they are interconnected. It's essentially the same question. To be honest, I cannot really pinpoint any potential practical application of this. And as you see, this research is a kind of a basic research which goes on already for several decades. To me, even if we don't find any practical applications, and I'm honest with you that we haven't found one up to this moment, still this is a basic science, and where it's valuable would be really in this last conclusions that where I have invited this series to investigate this. The point is, the calculations of the configuration of many electron systems, and these are essentially very many electron systems, because the periodic unit cell contains a great number of electrons, are still an open, so to say, it's an open question in modern physics. So there are a lot of methods to simulate many electron systems and extract their physical parameters. And such experiments are, in fact, one of the possibilities to compare the results of the calculations, which are not even unambiguous up to this point. Different functionals, different methods would predict different structures. And actually, to test these many electron theories, you would need some particular experiments where you can compare the calculated and the measured parameters. And that's where I see its application, if you would allow. Thank you. That's what I wanted to say. Yeah.
Why exactly theorem?
Well, it's because I haven't given you the entire literature overview, but almost all other rare earth elements were investigated on this molybdenum substrate. Well, some of the experiments use a different crystalline Mueller indexes orientation of the substrates, but 112 is one of the most popular ones. So it's a kind of a self-amplification effect when already a lot of serum atoms, a lot of rare earth elements were investigated on one particular substrate. Then again, in terms of this previous comparison, how theories nicely, or not very nicely, predict the results of experiments, it is then very convenient to continue working on that same substrate, but then with a slightly different system that contains, like, say, one more extra electron per unit cell, or a couple of extra electrons, or 2 or 3 electrons less, and that's why we have chosen to add to this database of experimental knowledge, so to say. Yeah.
Other questions? No questions. So thank you again.
Thank you very much for your attention.
And I invite next speaker is Professor Yuri Zholudov from Kharkiv National University of Radioelectronics, with his presentation entitled Electrogenerated Chemoluminescence in Thin Polymer Films on Smooth and Nanostructured Electrode Surfaces.
Thank you very much, Mr. Chairman. It is my great pleasure to be present at this wonderful meeting in the city center of Lviv, to be present physically and not online. So, first of all, I would like to say that my presentation will be not perfectly directed on the nanoscience. The nanoscience will be only in the end, and it will be more than a question rather than an answer to some problems and difficulties. I'm representing the Kharkiv National University of Radioelectronics, and first of all, I will give a brief introduction to the field where we are working. This is the field of electrogenerated chemoluminescence. This is an analytical technique used for electroanalytical technique used for chemical analysis. Just few basics. The ECL itself, the basic principle of ECL, is the electrogeneration of reactive species in the course of electrochemical processes in the solution on the electrode surface. And then, depending on the system which is employed, this electrogenerated species can recombine to create the excited state and the light emission from the excited state of some label of fluorophore. And this technique is growing in its popularity starting from somewhere 1960s when it was first discovered, and now it comes already to practical applications in the form of clinical ECL immunoassay, which is currently widely used, and it is actually claimed as the most sensitive detection technique on the medical clinical area. The reason for that is the essence of electrogenerated chemiluminescence. So we have a light emission, so optical detection is nowadays extremely sensitive. We can detect down to 1 photon with using such detectors like PMT or APD. At the same time, there is no excitation, optical excitation of this emission. There is electrochemical processes. Of course, to be honest, in every system there is always present some side reactions, and still there is some background signal present, but it's not comparable to the optical excitation, of course. As a result, it gives extreme sensitivity, let's say. At the same time, despite of these commercial applications with ECL immunoassay, where everything is fine and working and commercial, there is a lot of research going on with the ECL sensors, where reactions occurs at some specifically modified electrodes, so it's not homogeneous reaction. So this is homogeneous reaction in the solution. When we talk about ECL sensors, we talk about some kind of electrode modification where either fluorophore or correctant or some other components of the reaction are immobilized on the electrode surface. And nowadays, the majority of research in this field is actually aimed at enhancement of this kind of reaction formats. And one of the areas of effort is development of new modification systems, new fluorophores, new efficient correctants for exciting this ECL, development of new electrodes in order to load more reactive species. There are used different kind of foamy conductive electrodes, carbon nanotube meshes, graphene immobilization to create some porous, conductive, redox active materials. And that's where we will come in the end of this talk to nanotechnology again. So the subject of this particular research was design of some new and simple modification of the electrode to create some new ECL system. Actually, the motivation was mostly fundamental research, even it has some practical applications for the sensors development. It was the potential goal. So let me say a few words about how this modification was done. So the ECL was itself generated on this kind of so-called disc electrode, so the glassy carbon disc electrode immersed into the polymer matrix, polished from this surface. The films that were deposited, this was a polymer film of PVB, polyvinyl butyral, that was impregnated with the organic fluorophore of polycyclic aromatic hydrocarbon type, the diphenylanthracene, highly efficient fluorophore, which is well known and studied in optical sciences for decades. The deposition was made from the solution using the simple spin coating technique from this mixture of this polymer and DPA solution in ethanol. At the same time, in order to generate the ECL on such modified electrode, there was also employed some new correctant, the species which is present in the solution, and that reacts with the oxidized or reduced fluorophore in the film on the electrode to give it, like to inject some high energy electron to create the excited state. And actually, this particular work was done with some proprietary correctant that was also discovered in our research lab, and that is especially suitable for exciting ECL on these modified electrodes when the fluorophore is immobilized on the electrode surface. This is so-called tetraphenyl barate correctant. Some mechanisms discussion of its operation, but for the moment it's maybe not important. What you should know is when the fluorophore is oxidized, loses some electron, it will then oxidize the tetraphenylborate species, which will decompose chemically and will create some strong electron donor, which will inject electron to the oxidized molecule of fluorophore to create the excited state. Singular excited state that will emit light later. That's the basic step behind this reaction scheme. So these studies were made on a polished, smooth glassy carbon electrode, disc electrode. It was found that the films deposit nicely and the reaction is quite efficient. It is possible to, when electrode potential program is applied, so the so-called simple cyclic voltammetry, when electrode potential is scanned from the zero to some potential with respect to reference electrode and backwards, there is a nice ECL waves which are observed corresponding to the two processes of reaction. One is just what I have explained about correctant, another one is not important for the moment. Spectral studies show that emitter is the same for both processes, and this is definitely definition anthracene, which is emitting at the boundary of blue and violet, and partly ultraviolet, which is also a nice achievement because in the field of ECL there is often a problem of such blue emitters due to the lack of reaction energy which is released by correctants. So that's what is going on schematically. So correctant, oxidized fluorophore, so electron transfer once, twice, and then you get the excited state. When this ECL scheme was in the development, it was found that the reasonable and useful ECL emission occurs only within a very narrow range of parameters for deposition this film. For that moment, the idea was that probably we deal with quite thin films, and when the thickness is not enough, we just don't have enough fluorophore on the surface. When it is more than necessary, then the film itself is essentially insulating, so there should be some interplay between the conductivity of the film and emission from the surface. It also depends on many other factors, but this is what you should keep in mind for the moment. It was also found that this particular system is extremely efficient in terms of generation of ECL when a very fast potential pulse is applied. So using cyclic voltammetry, it was found that depending on the scan rate, the emission is just exponentially increasing. So the system is very fast and is especially efficient for the fast processes. So the pulsed mode should be used, definitely. The potential should be just pulsed from zero to this reaction potential and backwards to get the maximum output. And in this mode, it was shown that the reasonable and strong linear response of this ECL system, light response, is present when the correctant concentration in the solution is down to dozen of nanomolar moles per liter concentration range, which is quite sensitive. It's not common for ECL reactions with correctants, so the system is extremely efficient from this viewpoint comparing to other existing. So this was a kind of introduction to the ECL and this system when we come to the part which is related to micro and nanostructuring of electrode surface. So the question was, okay, we have this efficient system on the film modified electrode, and when we talk about ECL sensors creation, we always think that we want to load more material, we want to make some kind of developed surface with rough surface which has more reactive sites and so on. And we were, in one of the approaches was already kindly presented by my colleagues, is this laser-induced periodic surface structures on the GC, glassy carbon, the same glassy carbon. Here is just briefly shown just to remind you what it looks like. So periodic structure of the period of about 700 nanometers. And the same films were deposited on glassy carbon that is not the same type of structure and size and nature of glassy carbon that was not modified by laser, and the one that was modified. We were expecting different phenomena, maybe some enhancement, maybe not, who knows. But the result was absolutely not expected. What we get here, there is absolute absence of ECL emission from such a modified system, a modified substrate. it's not like some reduction of emission, maybe some quenching or something else, but there is nothing, absolutely nothing on the level the PMT can detect. So absolutely, the signal just disappeared and gone. It's like a black hole for the ECL on this surface. Despite of the fact the regular electrochemical properties of this modified electrode, okay, it's a new material, maybe some kind of chemistry of the surface change or something, maybe it's not conductive or redox active, but when we just talk about it as a regular electrode, there is a reasonable redox chemistry of redox active species, so it is conductive, it is redox active. There is a regular background current which just has higher capacity because of the higher surface area. This is expectable and natural, but the ECL is completely absent. Okay, so that's quite unexpected and gives us only questions and pushes us to the just question what is the reason, where to search for it, and just saying in advance we don't have a complete answer to this question. So then we just came back and just compare what we have when we talk about homogeneous ECL reaction when the reaction is in the solution. The regular RubyP, classical RubyP system with TPA correct entry propylamide, so oxidized on the electrode, then correct and oxidized on the electrode, then they diffuse in the solution near the electrode surface, and that's where the reaction occurs. And what we observe on this LIPS modified electrode structure, there is comparable current of this, just almost the same, of the correctant oxidation and the fluorophore oxidation, but the ECL is reduced something like more than a dozen of times. But in this case, the reaction is already near the electrode, not on the electrode. And we can estimate the reaction zone where light emission occurs, something like in the range of several micrometers. And this brings us to some unexpected conclusion. We need to think back from the basic roots of ECL emission. And also we have to rethink this result that we were observing when we were optimizing the position parameters. Honestly saying, this what starts now is kind of a speculation, that's just some assumptions, but we don't have any real proof of that it is exactly what we think about it. In the field of ECL, it was historically well known that metal surfaces are quenching light emission on them, conductive surfaces. But mostly we talk about metal. That's why when we talk about these kind of sensors, not many people are saying about that, but most people prefer to use non-metallic electrodes. Carbon electrodes, first of all. Glassy carbon is the most widely used for different kind of surface creation, modification. Other carbon materials like these nanowires deposited on the same glassy carbon, maybe some kind of graphite nanosheets and other kind of developed materials, they are widely used. And nobody was very carefully studying this problem, at least I have no idea about that. That probably the quenching of emission also occurs on glassy carbon material, but maybe it's not so drastic, so we still get some signal and it is quite measurable, it is enough to get the best sensitivity of the detection. But if this is the case, and due to this nano-developed structure of LIPS modified electrode, the interaction between the electrode and the film is just increased in terms of its quenching, then probably the same quenching must be present on smooth electrode surface, but maybe less efficient, and that's why we get some reasonable signal. And this just gives us an idea that, first of all, we need to make more detailed study of this problem, and the other, a kind of potential benefit if we are right. It means that by reducing this factor, probably we can increase the sensitivity of ECL detection of all these formats, maybe dozens of times or more. If it happens that the signal that we are getting is just some small remain of what could be there due to the strong interaction with the electrode surface. But this is a speculation, as I say, the last conclusion, because we don't have any direct evidence and we just think how to... We tried to eliminate some possible explanations, but there are still other possible. Okay, and finally, okay, I made the conclusion already. So just maybe the acknowledgement, the work was conducted for quite a long time in the framework of different projects, including the research fellowship from Chinese Academy of Science, bilateral Chinese-Ukraine projects, and the National Research Fund of Ukraine projects. Thank you for your kind attention.
Thank you. Thank you for your presentation. And do we have questions? Yeah, we have questions.
Thank you for your talk. The question is, how thick is the polymer coating on the surface?
Film.
Film, yes.
Yeah, a great question. To my shame, before we get this result of complete quenching of ECL, we were never thinking about it. The signal was there, it was quite enough to measure anything with the extreme sensitivity. My brief rough estimate without direct measurements says that it should be in the order of like from 50 to 160 nanometers. That's my estimate. Very rough estimate based on how much polymer, the mass and concentration of solution and the aliquot which was dropped, without considering how much was thrown away.
Maybe this is the point, because less than 5 nanometers you have quenching.
Of course, that's why we're thinking about it, but we don't have direct proof that it is the reason. Probably it is the reason, but...
Another question? No questions, so thank you again. And now we switch to the next section, a section of nanoscale physics, and we invite the new chairman.
Thank you very much. Okay. Thank you.
Hello everyone, I am glad to open the nanoscale physics session. The first presentation will be done by Professor Darina Matulka from Lviv Polytechnic National University, and she presents report Features of Optical Characteristics of Nano-Objects. Please.
Good afternoon, dear colleagues, and I want to present for your attention my our work under the such title as we see in the slide. Our work was made in Lviv Polytechnic National University. I represent that university, and Department of Applied Physics and Nanomaterial Science. So, as we know, nano-objects have unique characteristics that are produced by their properties, such as quantum dimensional effects and others. Nano-objects have different applications in modern science, in medicine, and others applications. Also, we know such a wide application of nano-objects as in modern electronics and modern power engineering. Our laboratory, research laboratory of nanophysics and molecular power engineering, which I also present here, investigate such nano objects, such materials for application in power engineering. Our laboratory has near 20 years, and main activity of laboratory is to investigate materials for application in power engineering. Here is our areas of investigation, also methods of investigations, and basis materials with which we work and what we investigate. Here we see the scheme of intercalation reaction and 3 intercalated systems, and also molecular engineering systems are here. Important moments of our research which we present here. The aim of our research is quantum dimensional effects that we can have in nano objects. For investigation, we have choose objects such as quantum dot. As we know, quantum dot is spherical, with the image to be a spherical object which have dimensions near a few nanometers, little dimensions in all three directions. Spherical tell us that dimension is size is equality similar in dimensions 3. But for our investigation, we have choose rectangular parallelepiped quantum dot, and the dot was anisotropic. It has different size in 3 directions. In 3 directions, it have different size. Also, I want to say that quantum dot for our investigation was anisotropic quantum dot and semiconductor quantum dot. We have received optical properties and influence the quantum dimensional effects on optical properties. For our investigation, we choose such optical properties as absorption coefficient. The formula equation for calculation of such coefficient we have here. We know that n is the factor index of medium in this formula, and other we have m with index 0 is the mass of electron, and volume of crystal is cursive omega. Omega little is the angular frequency of electromagnetic wave. Also we here the summation over all states that we can have in our object, and we see the initial states of electron in the valence band. I demonstrate here such structure, such energetic structure of our object, and we see it here. Also, we see here the formulas and final stage of in the conductor band. A multiplier which we represent here describes the occupation of corresponding states, and f as function a is the Fermi-Dirac distribution. We choose distribution at the temperature equal 0 Kelvin for our investigation. Also, we know there is the delta function, which indicates that states must be separated by the energy equal photon energy according to the law of conversation, and this multiplier. Sorry. This multiplier gives us information about transition between states caused by a polarized light. Let's see this momentum matrix element in 3D space. We can write this in such form as represented in this slide. Psi is a wave function of the state of our transition. We have right here. Now, also I represent the potential energy of our and potential structure of our investigation. We have chosen to our investigation a parabolic structure. potential energy. We see here the potential energy of in 3 different crystallographic directions for our object, and we can write the potential as the summation of independent potentials in 3 independent directions, and we represent here. M is, with index 0 is effective mass, and this index is effective mass of electron in conduction and a whole invariance band of our structure. Also, I must to say, we choose the parabolic value has depth v with index 0 we have, and also we can write here the its size and effective mass write it with index with such equation as which is represented in this slide. Let's now we know information about our structure, about this potential, so we can write the energy states of our structure. This is well-known formula, and here we see all its indexes. Also, our anisotropy of our structure is in these equations, these square roots, we have information about our anisotropic structure and effective mass. Our effective mass of our electron and is in these square roots which we have here. Also, we can write the our function, wave function of structure. This is right here. Square momentum matrix element of alpha polarized light is right here in this. This slide we have information of our square root. Also, I must say that we can analyze this function, this equation, and we have do some conclusions that when this square root mathematics element will be non-zero in the case when our mu beta and mu beta prime plus mu beta prime and mu gamma plus mu gamma prime are even, and in the same time mu beta and mu alpha and mu alpha prime plus mu alpha prime is odd. We consider the transition between states of which we have here. Also, I must say a few words when we will have most intensive transition. Most intense of transition will be between states, ground states in valence band and fast excited states in conduction band. So we consider such transitions, Fourier transition, under the polarization of our situation. In general case, we can find the frequency of such transition according to this formula which we have presented here in this slide. We must remember that non-zero will this sum of mu alpha plus mu alpha prime must be odd. So we write transition, we analyze the most intense of the absorption coefficients. In the case quality of effective mass of in conduction band and valence band of which we have here. So we write our matrix momentum element, squared matrix momentum, and we have write here our absorption coefficient, which we present in which we used for our calculation, numerical calculations and investigation. Similar consideration here we have write under the such polarization x00. Similar consideration are valid also for others two polarization of the light. So we have light, and here we have present spectral polarized dependencies, which in this slide. What we have here? We have see here that our absorption coefficient have line structure, which we have here. Also, I want to say that green, this is our anisotropic object, which we have here our quantum dot. For comparison, we used isotropic quantum dot, which quantum dot have effective mass equality in three different cases, three different dimensions. We have here, this is blue line, and in this slide we have different positions of our lines, which is consequence of the polarization of the light and of the our structure, anisotropic structure, degree of anisotropy give us information about the position of these lines of absorption, and also give us information of degree of such structure. Also we see here at the isotropic case we have such two transition as one line, and this namely particular such two transitions, second and third transitions are here present as one line. And in anisotropic quantum dot we have there is split of this transition, and the split is predicted of both as polarization of the light and degree of anisotropy of our structure. Conclusions: line structure absorption coefficient is a consequence of the discrete spectrum of carriers. As we know, in a quantum dot, spectrum is discrete, so we have such structure. The position of the peaks of absorption coefficient in identical transition in anisotropic quantum dot shift to the right or to the left. Relatively their position in the isotropic quantum dot. Such shifts are and their magnitudes are determined both by the degree of the anisotropy and the polarization of the light, and as we see in isotropic quantum dot, nano object, regardless of the polarization of the light, absorption coefficient peaks take same value in two transitions. In the case of anisotropic nano-object, we have doublet splits by the certain value, which depends on degree of anisotropy and polarization of the light. And thank you for your attention.
So, thank you a lot for your valuable presentation, and now we have time for questions. Are there some questions in the room? So, again, thank you for your talk.
Thank you.
For the next presentation, we invite Dr. Natalia Rusinchuk from Taras Shevchenko National University Institute of High Technologies from Ukraine with a report, Physical Description of Near-Field Interaction of Nanoparticles with Microorganisms.
Thank you. Good afternoon to all. I would like to thank organizers for this conference, and I would like to thank all who are still here, and I'll try to take less than 15 minutes. My talk will be devoted to the part of the project which is financing by National Research Foundation of Ukraine. This is the complex study which is conducted by our university, the Institute of High Technologies, in collaboration with Lashkarov Institute of Semiconductor Physics, Chuiko Institute of Surface Chemistry, and the Bolotny Institute of Microbiology and Virology. And in the frame of this project, we try to study how the nanoparticles parameters influence on their antibacterial, antifungal, and antiviral properties. And we try to conduct this study in complex because, as it was said previously by other speakers, the parameters of nanoparticles depend much on their production. So we have a group which synthesizes nanoparticles, and we can control their parameters. And my part of the work was devoted to the theoretical models of the interaction of the nanoparticles with the bio-objects. And here I will talk about the interaction with microorganisms. However, previously we studied the interaction with viruses. And these models are simpler because the outcellular virus with some assumption may be considered as nanoparticle, but we cannot make some assumption in case of microorganisms. So what was the main idea of our studies? We tried to construct the model which will allow us to receive some analytical results. Of course, they are not take into account all the parameters, but we try to obtain the results which give us which give us qualitatively correct results. And why this is important? Because nanosystems are too complex, and interactions in such systems are studied mainly with numerical calculations, and it is hard to analyze too many results of such calculations, and it would be great if we have some formula to look at it and to understand what are the dependencies. And why physics? Because I will talk about physical near-field interactions. Of course, in such systems, when nanoparticles interact with microorganisms, there are many types of interactions. But we, as we physicists, we study mainly the near-field interactions, because these interactions depend much on the size and shape of nanoparticles. And we all know that antiviral, antimicrobial properties and other interactions with living objects also depend much on size and shape, and we may find some interesting results in the field of near-field interactions. Firstly, we would like to understand where these interactions may occur and what type of systems we need to consider. Here are a few samples of not our studies, where we can see that the nanoparticle may I code laser point. Okay. Yeah, and we can see that the nanoparticles may interact with the surface of microorganisms, or they may interact with some structures on the surface, or they may penetrate into the cell and interact with some intracellular structures. Also, there are results, for example, when nanoparticles can block the DNA replication inside the cells. So this may also, the first stage of such interaction may be due to the near-field interaction. When we study such a case, this may be with assumption considered as the nanoparticle interacted with the surface. When we consider this case, this may be the nanoparticle which interact with some nanostructured surface. And when we consider the case of intracellular interaction, they in brief may be considered as nanoparticle with nanoparticle interactions. I would like to point out that these interactions that we study occur at the distances that are higher than several nanometers. So this is the previous study for adsorption and further chemical and other interactions. And what are the main ideas? We need to consider these types of systems, and we want to calculate the energy of interaction and the forces which occur in such systems in order to understand maybe orientation of such, some nanocomposites and so on. So we need to study the energy of interaction, and it depends on the electric field, on the polarization of the objects. Main ideas that we used is the green function, which allow us to calculate the electric field in some systems. But in this case, we have the self-consistent equation where the field is both on the right and on the left sides of this equation. So the next step, it was the concept of effective susceptibility, when we use the not material characteristics but the object characteristics, which depends on the size, on the shape, on the material, and so on. And in this case, when we use such characteristics, we can receive the equation where the unknown field in the system is just on the left side. Further steps is how we can take into account the nanostructures, the non-even surface, for example. This is the pseudo-vacuum green function idea. When we start to study the simplest system, for example, with the even surface, and then we add more and more nanostructures on this surface, and we obtain the green function of new system from the green function of the previous system, and so on and so on. And at least we may neglect influence of some nano-objects using the quasi-point-like nanoparticle assumption. So due to this calculation, we may find that at the some distance from the nano-object, its shape does not influence much on the energy, and also at some distance, its influence on the local field in the system also may be neglected. And we have many models, many descriptions, calculations for different systems. Here I show some results. For example, we have a simple formula to analyze at what distance two nanoparticles do not interact to act on each other. So we may find out at what distance we may neglect other nano-objects. The other result is, for example, for some nanocomposites, when two nanoparticles of different nature and different size are connected, and we may calculate the forces and to assume what are the probable orientations of such nanocomposites close into the surface. And for example, we may explain why the stabilizer of nanoparticles influence on their action, because the stabilizer is something like a shell of the nanoparticle, and the properties of this shell are inside its effective susceptibility. So we may consider such system and reveal where the force will be higher. Also, there are some other results. However, we plan to work further, and we would like to combine physical interactions with chemical, and to apply these results for explanation of experimental data. We have partly done this for antiviral experiments, but are working now on antimicrobial experiments. And the main idea is to give some recommendations on the nanoparticles, choose of nanoparticles parameters for some reasons, for some purposes. And maybe that's all. Thank you for your attention.
Thank you a lot for your important report. So now we have time for question.
So, thank you very much for your talk. A question. You introduce the green functions. They are usually a method to solve some differential equations. Yeah. But which differential equation are you actually solving?
It's the differential... if we talk from the start point, there are Maxwell equations. And from there we go to Lippmann-Schwinger equation for electric field, and there we introduce the green function.
Okay, thank you.
Actually, I have the same question, because when you introduce new functions successively, so you have to solve a series of differential equations. Yeah. So actually you have to solve the problem, harmonization of this problem. Right? You have to solve, you find the effective green function of new medium.
Yeah.
So I don't understand how you do it. This is many particle problem.
Yes.
And you cannot add one by step by step.
this is not our idea of pseudo-vacuum green function, and we do not just summarize this interaction. We not add them this idea is when the new green function is not just sum of two.
Yes, you solve these equations. These equations should be solved, and this means you have to harmonize the system. You have to find the effective properties of this system.
Yes.
So actually, it's the final solution. You cannot do it step by step. You understand? You have to solve this equation. So you just, how can you solve it? You say you add one more, so you use the iterative procedure, and you just transcade this series. So that's it. So I don't understand how you can do it. From the math point of view, this is not correct.
Maybe I.
So check it out.
Okay,
just the same,
we will
I'm
check.
doing the same thing.
Thank you.
And you know this is something wrong.
Okay.
So, other questions? Thank you. So, thank you again for interesting discussion. The third contribution in the work of our session will be done by PhD student Svetlana Balika from Odessa Meshnikov National University with the report Role of Interface Effects in the Formation of the Electrical Conductivity of Electrolyte-Based Suspensions. Thank you. Please.
This is not mine.
Okay.
Sorry.
Okay, just a moment.
Just a moment.
Yeah. Okay, please.
Good evening. This work is done in co-authorship with my supervisor Miroslav Sushko, and we studied the problem of electrical conductivity, which has been researched for many years, but is still far from its complete solution. The reason is that suspensions belong to random heterogeneous systems, and electrodynamic homogenization requires taking into account various many particle effects and the adjacent electrical double layer. Traditional approaches usually are restricted to use one particle approximation, but even in this case, when different electrokinetic theories are used, there are a lot of parameters involved whose contribution to electrical double layer or electrical conductivity is difficult to track. So there is no consistent theory for electrical conductivity, in special for concentrated suspensions. We try to describe electrical properties, in particular electrical conductivity, and to take into account the adjacent electrical double layer. We try to show that it has an important role, and it is possible to restore the effective parameters using the electrical double layers properties. So the main questions of these presentations are as follows. First, we'll consider the problem of theoretical description of existing theories, and then the proposed our model based on the compo group approach. And after that, we'll test our theory by applying it to two types of systems, to suspension with high surface potential and concentrated system. Concentrated suspension, actually. Traditional methods such as Maxwell-Garnett or Brueggemann assume that the properties of individual component in the system do not change after the system is formed. But actually they change its properties, and the electrical double layer forms around the surface of particle, and we should take it into account. For example, the most advanced theoretical methods for describing electrical conductivity, also known as electrokinetic models. Right, how to switch on this? Yeah. Oh, okay, thank you. So I've been talking about electrokinetic models. They write such a system of equation. Here is the Poisson-Boltzmann equation, the Stokes equation, the continuous equation, and the law of conservation of charge, and some postulated boundary condition. The effective conductivity is calculated in this way. The coefficient of proportionality between average current and average electric field. And they resolve this system and obtain some results. But in spite of the fact that this theory has good results for low concentration, there are some serious drawbacks. And these drawbacks are as follows. For example, one particle approximation. So the influence of particles is ignored. Other point is potential distribution in the diffuse part of electrical double layer is extrapolated to the surface of particles. So the role of electrical double layer is disregarded. To resolve this system of equation, they linearize it system, and under the condition that surface potential should be smaller than unity. But the results obtained typically contradict this condition, and surface potential is greater than unity. So we try to avoid such drawbacks and to take into account the formation of electrical double layer, and we would like to take into account the structure of electrical double layer, because it has complex structure. It contains the inner part and the outer part, also known as the diffuse part of electrical double layer. The inner part is called the Stern layer, and the Stern layer has its own complex structure. It consists of the inner and outer Helmholtz planes. The model of suspensions, how we model it. We assume that our suspension consists of a collection of hardcore inhomogeneous penetrable shells, and microstructure is modeled in terms of electrical conductivity distribution in this system. Also, these shells are electrically inhomogeneous, And if we have penetrable shells, these shells may overlap. So in the point, in the region of overlapping, we propose such a rule of dominance. The effective conductivity in the point of interest is determined by nearest surface, by nearest distance to the surface. So the volume concentration for the shells is represented here, and also we take into account the many-particle contributions using the method, compact group method. By compact groups are defined as microscopic regions with sizes much smaller than the wavelength of probing radiation, but yet large enough to retain the properties of entire system. In such a system, we should model the effective the permittivity. So the permittivity distribution you can see right over here. It is determined in is calculated actually in terms of effective permittivity and plus delta epsilon, which represent the deviation from effective permittivity, and this delta epsilon represent the contribution from the such a compact groups. So we have the average electric field and average complex current, and the result of calculations of these equations is this formula for effective conductivity. So we have this basic formula, this basic equation, and we would like to apply it to a particular system, to one strong electrolytes, suspensions based on strong electrolytes. Here we have zeta potential and U asterisk as the main parameters of our theory, but here in this work we use this zeta potential from experiment, and U asterisk is the fitting parameter. As we have strong electrolytes, we assume that our layers are thin, and then we can use Gui-Chapman distribution for the electrical potential. Here is the formula. Also, this distribution is used beyond the distance U asterisk. In this outer part of electrical double layer, we use this formula for modeling the effective conductivity. And we also take into account the inner part of electrical double layer, and we consider different types of behavior of electrical conductivity in this interface layer. We have some results for these cases. So the main, if zeta potential, unitless zeta potential, is smaller than unity, and U asterisk goes to 0, we have this result for effective conductivity, and this formula represents the Maxwell-Garnett equation. If we have high conductive and low conductive layer, and the unitless potential is greater than 3, we have these results. If this lambda coefficient lambda is equal to unity, there is no electrical double layer effects, but the deviation of lambda from unity means that electrical double layer plays important role in the formation of effective conductivity here. Next, we apply these formulas, these results, for two types of experiments. First, to suspension with high surface potential, and here we have suspensions of latex particles in aqua solution of hydrochlor. Here is our theory, and the point represents the experiments. You can see that here this theory fully describes the experiment, and it restores the results and coincides with the numerical solution of electrokinetic theory. Here we use the zeta potential from experiment, and the U asterisk is the fitting parameter. The second application is to concentrated suspension. Here we have our theory, and the dashed curves represents the Maxwell-Garnett type fitting. We have these results. So the main differences between our theory and the Maxwell-Garnett approximation are as follows. We use many particle approximation, while Maxwell-Garnett represents one particle approximation. And we take into account the inner part and the outer part of electrical double layer, while Maxwell-Garnett approximation does not show this result. And also we have here non-conductive particles, and in the Maxwell-Garnett theory they use conductivity of particles as fitting parameter, but it has different values in different samples. So I can say that the main results of this work are as follows. We proposed a theory for electrical conductivity of suspension, effective conductivity, and the main results are that we consider the inner part and the outer part, and we show that outer part plays important role. The inner part also are pronounced, but and it is not noticeable. And we demonstrate these results for 2 experiments. Thank you very much for your attention.
Thank you very much for perfect presentation. And other questions, Sam? Thank you again. Yes.
Okay, you can eject. Okay, help you.
Thank you.
So, we are going to the end of our session, and I would like to say for everybody, thank you for attention and contribution. And now we invite the head of NANO-2021 Conference Organized Committee, Dr. Olena Fesenko. Please.
Everything that has a beginning has an ending. This year our conference is coming to the end, but let's summarize some statistic data of the conference. This year the organizing committee of NANO-2021 received about 700 application forms of participants from more than 25 countries of the world. More than 70 plenary and oral presentation were present during the 3 days of conference. Also, about 300 poster presentation were also presented during 3 days of the conference. Our conference started in 2012 and now become the biggest international scientific conference in Ukraine. Let's together see some moments from current conference. I want to congratulate my team for the high level and professional organizing this conference. Thanks very much to Yevhen Kifyuk, Тамара Цибрієнко, Андрій Яремкевич, Павло Голуб, Анастасія Кловчик, Наталія Давиденко, Оксана Будник, Максим Ральєв, Віталій Ткаченко for organizing this event. You are the best, and it is a great pleasure for me to work together with you. First of all, the conference consists of participants. That's why thanks to everyone who took part at our NANO-2021 conference. I hope you like our conference, and after returning back to home, you will share the information about conference and your impression about the conference with your colleagues, and we'll invite them to take part at our next conferences. In 2022, the Nano conference will be jubilee. The 10th anniversary of Nano conference will be held in the last week of August next year. As usual in September, this year you will receive the detailed instruction where you can publish your scientific results which were present during this conference. The live broadcast recording of Nano 2021 is already freely available on the website and on the Facebook page of the conference. You can see and share it. Now allow me officially to the end of our conference. I wish you to be healthy and see you the next year. Let's grow together. Thank you.